I'm going live again.
Okay.
Okay, now it's better. Oh, no, wait. I have the wrong link. So how is now the audio quality? Let's test it for the stream. Okay, that's quite good. Then we can mute and Zoom and we're going to go live in at 9 GMT plus 00.
Yeah, that's fine.
Okay, perfect. This works.
There are so many things running.
Okay, good. Hey, David, you should now be a panelist, so you can test if we can hear you.
Hi there, how you guys doing?
Perfect. Great.
All right, so I think I used Zoom before, so should be fine. Let's see. Let's do this. That's me. Anyone else? My name. Let's go short. I cannot share screen, so someone but
It's because we are currently sharing like this waiting slides.
Yeah, but let's try it. I think we can try. So now you can share.
All right.
Yes.
All right. So there you are. Hey guys, how you guys doing?
Hello.
All right.
I mean, shouldn't be any different than any other Zoom meeting, right?
Perfect.
So you see,
Yeah.
Vanilla PowerPoint slide. Yeah. Hello.
Yeah,
Perfect.
we can see it.
Yeah, you can see it. Okay, so I'll take that as a does work.
Perfect. Then we're gonna have a short introduction at 9 from Martina, and then we're gonna give it up to you.
Yeah. Thanks. So.
Hey, Julia.
Hi.
Hey, Julia.
Okay, thanks. Bye.
Right, Martina, I think you can resume the slides.
I'm doing it right now. I think we can wait other 2 minutes and then we start. Hi, Jiang.
Hey, Martina.
Hello, good morning.
Yeah, afternoon. So can I also check my slide or later?
Yeah, you can try it now and then we start.
Okay, I just check.
So I stop sharing and you can try your slides and then we start.
Yeah, maybe I can do it later. I cannot find the link for sharing my slides.
Okay, then let's do it later.
Okay.
Okay, perfect. So I think we can start. So okay, so hi everybody and welcome to this ICRA 2021 workshop on representing and manipulating deformable objects. So thanks first of all for being here. And first I want just to quickly introduce who we are and why we decided to have this workshop. So it's a quite a huge team composed of different groups from different universities. So it's me, Martina Lippi, from Roma Tre University in Italy, where I am a postdoc. Then we have Michael Welle, Anastasia Varava, Hang Yin, Florian Pokorny, and Danica Kragic from KTH University in Sweden. And then we have Rika Antonova from Stanford University in the USA, and Yanis Karayanidis from Chalmers University. Ville Kirki from Aalto University in Finland, and Alessandro Marino from the University of Cassino in southern Lazio. And finally, we have Ville Malenia, Giulia Boras, and Carme Torras from the Istituto de Robotica e Informatica Industrial. So first, why we decided to organize this workshop. So basically because deformable objects are everywhere. So if we want to deal with real world applications, we also need to deal with deformability of objects. But then the problem that arises is that the large configuration space of these deformable objects causes traditional modeling, planning, and control approaches to fail. And in particular, so far, we are not able to clearly represent the state of deformable objects, but also we are not able to define the dynamics of these objects since it's extremely complex and it's highly nonlinear. And this leads to the fact that currently there are no unified solutions for deformable objects manipulation. And we mostly have really highly domain-specific approaches which can solve some particular tasks. And also, of course, we also have lack of general simulation environments where we can actually test if the approaches are valid or not. So here we are at our goals with this workshop. So our first goal is to collect state-of-the-art solutions. And that's why we have a set of really experts speakers in this field of deformable objects. And it's a pleasure to have them here today. Then we want to identify some possible research directions and some promising ways of addressing these challenges of deformable objects. And finally, we also aim to connect people from different areas of robotics, such as the perception, simulation, control, and mechanics, in order to effectively overcome the challenges from these deformable objects. So that's why we defined a quite broad set of topics that range from the representation and state estimation to simulation and modeling up to application-specific challenges like in cloth folding or surgical tasks. But we will have time to go into these topics and into the details of possible solutions for deformable objects during the entire day. So now I just want to provide some technical details about the workshop. So we'll have 8 invited talks, which will be divided in 2 sessions. So we'll have the morning session and the afternoon session. And each invited talk will be around 25 minutes plus 5 minutes for question and answers. And then we'll also have 2 discussion rounds, one in the morning and one in the afternoon, where we will have our speakers and also some organizers. We also have contributed extended abstracts, which are available on our website, and we had 13 accepted works, and each work will be presented through a 5 minutes presentation that is pre-recorded, and then we'll have a 1 minute question and answer that will be live. And here we are at the schedule. So we start soonish with the first invited talk by David Navarro Alarcon from the Hong Kong Polytechnic University. Then we'll have Yisheng Lee from Tsinghua University at 9:45. And then we'll have the first session of Spotlight Talks at 10:15. At this point, we'll have a short coffee break at 11, and next we'll have the other 2 invited talks of the morning that are by Zachary Erickson from Georgia Tech Institute of Technology and Giulia Boras from the Istituto di Robotica e Informatica Industriale. And we'll close the morning session with an open discussion round at 12:15. And then in the afternoon, we will resume at 14. So we'll have the first invited talk by Dimitri Berenson from the University of Michigan. And then we'll have Wenzen Yuan from the Carnegie Mellon University at 14:30. And then we'll have the second spotlight session that will take 45 minutes, and we have 6 spotlight talks. And again, we'll have a short coffee break at 15:45. And we will resume at 16, and we'll have the last 2 invited talks from Dinesh Manocha from the University of Maryland and Jeanette Bogg from Stanford University. And we'll close the workshop with the final open discussion round at 17, and we'll have just some closing remarks at 17:45. So now it's time to define how you can interact with the speakers and also the presenters of the Spotlight Talks. So we set up mainly 3 channels. So you have the Zoom question and answers, the Slido channel, and in particular, the number is 267619. And then we have also the YouTube chat where there is the live streaming of the workshop. So please ask as many questions as possible. So let's try to have an interactive workshop, even if it's online. And if you want to watch again a talk, or if you want to read the accepted extended abstracts, which I suggest because they're really interesting, you can find all this information on the workshop website. So all the talks and contributions are there, and the talks will also be available on the YouTube channel. So that's it for the organization of the workshop. So if there are any questions, that's the perfect time for the questions. Just regarding the organizations, then we'll have plenty of questions for the speakers. Okay, so I guess if there are no questions, I can leave the floor to Mikael Welle, who is a PhD student at KTH in Stockholm, and he will moderate the workshop with me for the entire day. So please, Michael.
Thank you very much, Martina. It's my great pleasure to introduce right away our first speaker, David Navarro Alarcon. And he's a professor at the Department of Mechanical Engineering at the Hong Kong University Polytechnica and the principal investigator of the Robotics and Machine Intelligence Laboratory. He received his PhD in Mechanical and Automation Engineering from the Chinese University of Hong Kong in 2014. And his current research interests include perceptual robotics and control theory. And I'm very happy to welcome him here. And yeah, take it away, David.
Thanks, Michael. Thanks, Martina. And thanks to the other 11 workshop organizers. Is that a record? Possibly.
Yeah. Probably it is.
Yeah. Anyway, so let's start sharing my slides. So I trust you guys didn't change any special Zoom settings so that I can use it.
You can trust us.
Yeah, but if it doesn't work, I will easily blame you. So
that's good that it works.
Okay, so yeah, I guess I begin. So thanks a lot to the 13 organizers of this workshop. You know, kudos to you guys. It's a very fashionable topic nowadays. So, well, here the presentation I'm giving is mostly of the work that I've been actually mostly it's all about the work I've been doing with my group for the past 5 to 6 years. So I mostly work on manipulation, sensor-based manipulation. So for some reason, I'm only asked to talk about manipulation of sub-objects. Probably in a few years, I hope I can be asked to share my work in these other areas. But in this talk, I will share the great majority of the work that we have related to sub-object manipulation. So yeah, as I and all the others that will present today, we know and we all claim and make strong emphasis on the necessity to study this problem. More than the necessity, my intention with this slide is what is the difficulty? I mean, for someone, we have like 50 something speakers. So, someone who probably hadn't worked on this problem before, they may wonder, is there any significant difference in manipulating something that is rigid or something that is soft? Say rigid, we have basically many objects. Soft, I was thinking this morning actually about, is it fair to say that the great majority of the objects we have in common environments are non-rigid? I don't know. Probably for discussion, if someone may elaborate on this issue, but what they represent the great majority is a capability that we want robots to be able to autonomously perform the manipulation of these materials. So the difference between manipulating these two, whether being with a robotic hand or several manipulators, is that for a rigid object, its configuration, so now let's go technical, its configuration, its feedback representation is fixed. So we have at most 6 degrees of freedom. We have 3 of position, 3 of orientation. Now, how does this situation changes with deformable objects when manipulated by an object? How many degrees of freedom, how many coordinates in a feedback vector do we need? Well, in principle, theoretically, we know that deformable objects, they have infinite degrees of freedom. And this is precisely the central theme in the talk that I will give today. How many coordinates do we need to perform what I call in the work that I do a shape surveying task? So this is the underlying question of the work that I have today. So yeah, soft object manipulation is the fashionable topic nowadays, isn't it? We have reviews every 6 months, a new one. We have special issues. We have workshops. We have probably in a few months a podcast about this topic. There's a lot of people working on this, and don't see this as a criticism. I'm posing this, trying to highlight the importance of this area, because manipulation of deformable objects, providing these capabilities to a machine, it really has many applications in so many. I really don't want to spend too much in motivating saying that this is important, because being here and giving a talk in a workshop should already be implicit such a necessity. So the work that I'm showing today is about a problem that I call, I don't know, can I even say that this has entered the state of the art? Can we use the term shape surveying? I don't know, well, at least I am using this term. So by shape surveying, if I put it in terms of areas, we know there's an area called visual surveying, where say you have a camera, you have a manipulator, and you generally regulate some features. You want to minimize an error. So shape surveying is the natural extension to that problem. It is a control problem, but to control the extension to controlling, instead of like a feature of I don't know, let's say a square that you're observing with a camera. What we are here trying to, on one hand, characterize, and on the other one, deform is the shape or the configuration of a manipulated material. So I have a pen actually. Let's make use of our didactic tools that we have acquired in these months of online teaching. So does it work? Yeah, it does. All right. So we can, in a graphical way, describe this shape surveying. We have let's assume we can measure somehow the feedback shape of an object. And this is a target shape. Let's say we want to bend it. So in a very simple way to define these problems, we want to design a trajectory of the robot that minimizes this very standard quadratic error. So nothing special here. Well, I don't know, there's a question here. All right. So let me move this one. Yeah, so yeah, this is the main topic that I'm presenting today. How should we represent such feedback configuration of the object? So as I mentioned, in soft bodies, from a materials point of view, they have infinite dimensional, infinite number of degrees of freedom. So when we model this manipulation problem as a control problem, we have the necessity to compute this feedback shape of an object. So one of the questions we can start asking is, so how accurate or how detailed such representation needs to be? And this is a very crucial factor, because depending on the level of detail that you want will be the size or the dimension of such representation. So, I mean, there are many ways. I don't think there's a unique way to do it. And this is an actively studied problem in this field. So we can see in this figure, these are all screenshots from papers and experiments we have done through the years. So we can represent perhaps shape with angles, as we will show later on some experiments. We can represent them with simple points, such as this one. We can represent them with some contours. We can represent them with points in 3D. And anyway, there's really many ways you can do it. Now I start here drawing some attention to an important issue that I think, if we are to give you some hints and some clues from the experience that we have acquired here, is there's an approach that I call here the naive approach to shape surveying. So again, this is a control problem. I here very much emphasize that simulation, numerical simulation, virtual reality simulation, finite element model simulation is the objectives of such a field they're different, or generally different from those of control. So we cannot equate simulation to control. So for example, if we have various cases where we may be able to manipulate, say, something in 3D to observe. First of all, we can observe, let's say that we are observing this object, some foam sheet with a point cloud sensor. So these are some typical, shapes, surfaces that we might be able to compute. Let's assume for some moment that this is what we want. We want the robot to deform this one into this one. So the question here, and as the talk that I'm giving tries to pose and partly solve, how should we characterize the shape of this object so that we can use it in a control scheme? So if we just use this approach that I call the naive approach and just take entirely the raw dense feedback from a point cloud sensor, we may have like way too many coordinates. I mean, this is just an estimate. Let's say 600 numbers just to represent this surface. In this other case, how do I move this thing? In this other case where we can observe, for example, a cable, very active also, many people working on this, we might be able to add a very high contrast background and observe a binary image of that cable. So if you compute or extract the contour to all that binary image, how many numbers do you think you can get? I mean, also very rough estimate, I say, well, we can easily get 100. So are these two representations suitable to define this vector, suitable to one, represent, and two, control the shape of a deformable material? That I can, well, fairly say that probably not. I mean, it has way too much information than what we actually need to do this problem. So if we represent it as a series of steps, so I'm deliberatively using the word latent because it's although in the field one may associate latent with almost exclusively with a network. we can generalize this concept as, let's call it the non-evident way to represent the configuration of a sub-object. So I'm here calling that we have some shape encoding algorithm or method that will, from it, we will extract a series of numbers that can fairly characterize, maybe even almost locally, quite globally, the configuration of this object. So our interest in this talk is to find different ways to compute this one. And how do we use it in, well, this is a very also standard a feedback control problem. We have some plant, we can feed the shape back and we can define some target. So we will be giving you some examples of the work we've been doing specifically on this one. Okay, so what is the, well, I would call this the trivial solution to do is if we can use some specific geometric features to compute, let's call it centroids, angles, distances, curvatures, and its combinations. So any non-geometric function based on some point features that you may be able to detect in the surface of your object. So we can use such functions, say, for example, let's say a centroid or an angle, to characterize the configuration, the observable configuration of this object. So we did this in probably too many papers. I mean, it's a very, I would call it the very trivial, because it's the direct extension of what one from the visual surveying community would do. So, I mean, this is like really the natural way you end up doing it, because it's the easiest way to do it and closely resembles the visual surveying problem. So, but it has some issues. The type of shapes or configurations that you can encode by using hard-coded geometric features are very basic, very, very limited. And once you define it as such, you cannot morph them into something else. So once you, let's say, coded curvatures and you want to do something else, then that's it. I mean, your function cannot change. And that brings several limitations to the problem. So we can, of course, define more general approaches, and these are not specific for some geometry. Let's say, for example, bending. That's very clear, like practically. Once you coded bending, you can't really do it stretching somehow. So we start studying like more general approaches to represent, in this case, contours. So we use, very also, I mean, it's a very standard way to do it. So we use Fourier series, like finite number Fourier series to approximate the observable contour of an object. So the reason why we did this is, well, from a controlled background, we can then use very well-known tricks that we use everywhere. So we can split such approximation based on like a known regression matrix that you can measure based on sensor feedback. And then you have here a vector, which are here the so-called Fourier coefficients. So it turns out that these coefficients, we can, that's our proposition here. We use the coefficients as, I don't know, let's call it as a proxy to shape. It's not shape per se, but they can encode a shape that you're observing with your camera with a locally unique set of vectors. So here again, I highlight this has to be with using finite Fourier series, because we know that from the theory, the infinite Fourier series, well, it will exactly approximate everything, but it will give you a gigantic vector of coefficients. So if we put it as a pipeline, what is quite simple. So we binarize the image, we compute the arc length, we use observations of data along the arc of your shape, and then we can just use least squares estimation to compute such vector. Compared to the approach that I call the naive, how much could we reduce the computation? Say we had from a 2D image, like a 200 so vector, we end up having, say, for example, if we use 4 harmonics, we have 18 numbers, from 200 to 18. So, that's quite something. So how do we use this representation for control? That's also a central theme in what I do. So it's well, we also I don't know if somebody's expecting very advanced theory, probably is not the right talk. I use very standard method. So I use a very conventional Jacobian-based method to project. First of all, you have a contour, desired contour. You project it into Fourier coefficients, desired Fourier coefficients, and then you project this differential. This is actually a differential in shape space. You project it now into robot motions. You know, that's what we generally do with sensor-based control. Key here, as someone may wonder, is how do you compute the Jacobian metrics? There's so many recipes, and I literally call it like that, recipe, because you just use it to estimate the Jacobian metrics. So let's see some results. So, well, here we're using 2D motions, and the sensor also gives us 2D shapes. Well, things to highlight here is, well, what we are doing is we are encoding a high dimensional observable shape from an object just with a few parameters. In this case, depending on the number of harmonics. I don't remember, I think this experiment I used three to four. I use less than 20 parameters, so it's not so detailed. So as you can see, what we do is we remove all the high frequency information, you know, all the little details, which even if you have them, that's a question. Does it help from a control point of view? What would you do? I mean, if you hadn't really reached that specific detail, can you still control it with limited number of grasping points? Not really. So that's one of the reasoning that I put as for not using the dense measurement of the object shape. Well, we naturally extended this idea to, well, there are many analytical formulations of say curves. So we have, I mean, from the graphics field, we have what we call nerves and Bezier curves. So we use these other representations, and we literally follow the same set of steps that I presented before, observing a contour, characterizing it in terms of its arc length, and then we can use least squares estimation to obtain not Fourier coefficients, but we will obtain different coefficients. Let's call it like nerves coefficients and also Bezier coefficients. So these are numbers that locally they help to characterize the shape of an object, in which we can use as a quasi-feedback signal for control, for deforming this, well, it's a cable in this case to a desired shape. So, oh, actually, here it is. You see the green little dots? Way too many, multiplied by 2 for a camera. So it's a very long vector. In this case, we don't need that many information. You know, let me try to remember how many. Same case, I don't think we use more than 20 numbers to characterize these curves. We also work, this is some work we work with Montpellier. Well, also a natural extension of all this is to use, well, this one really brings the concept of optimality in the sense of really orthogonalizing different notions of and properties of shapes. So we use PCA tools to do the eigen decomposition of a series of observations. So let's here briefly review what we do. So let's say that we collect several, well, in the paper we actually did local observations, but let's say that we collect a whole global set of contours of the object, and then we construct, let's call this the data matrix, observation matrix, and we just, I think this one is like median, probably. To these we can eigen decompose it and then obtain the matrix, this matrix U, which contains the eigenvectors. If we select, the power of this is that it will tell you how many coordinates you actually need to represent to a desired degree of accuracy. So it's going to completely orthogonalize the, let's say, the specific properties of the shape in the object. And by selecting a given number of eigenvectors, we can then project. So everything here means feedback. This is your contour, your feedback. You simply project it with a selected number of eigenvectors to reduce space, in this case, obtained from such PCA-based decomposition of shapes. We will use this with exactly the same in the previous servoing approach for doing control. We are going to use this as a quasi-feedback signal, and we will design desired features that relate to this same PCA-based representation. So with Andrea Carvini and Yisheng Lee, we conducted several experiments. These are 2D cables, similar to the ones we did before, but using different theory. The standard now, spongy being deformed into a desired contour. One important aspect here is that with exactly the same method, for the method's point of view, the representation, it doesn't really matter if it's a rigid object, a soft object, a mixed properties object. We're just characterizing its configuration. So we use it to do both deformable, shape, to do translations, translation plus deformations, and so on. So, we have more details in this just recently published paper. Well, and also if someone says, well, these guys use PCA, why don't we use, the autoencoder? It's also very similar, related. So how would we use autoencoder for doing a representation of this? So, well, exactly as the autoencoder works. So we will have a set of contours that we will use to train this autoencoding network. And we will use, in this case, the bottleneck layer as the shape coordinates, as the latent variables the quasi-feedback variables that we will use for control. So in contrast with autoencoder and all the previous one, well, it also doesn't necessarily provide you orthogonal latent coordinates. So it will just give you some numbers. And you may also have in its standard form, the question of how many coordinates do you actually need to represent that, to represent it well. We don't really, at least in here, address that problem. We use also PCA, as a guide to select the number of codes. What should we looking here? Well, yeah, also interesting. Well, we have, we can obtain some semantic information here. So if we visualize this in the reduced space of the, this is for 3D, by the way, of the 3D contour, we can find some information as to what kind of shape the object has, and we are sensing. For example, we can have a helix, we can have a positive arch, negative arch, and so on. So this might give, this information might be given by PCA if we run it in parallel. Which also leads us to the issue of we have actually for this work been just simply designing controllers where we want to drive the feedback to a desired location. With a student of mine, Jeffrey, we recently started developing a method that we model that, or this is the formulation we have, that these latent variables that we use, for example, from an autoencoder or literally any of the other ones, that is not necessarily restricted to that specific neural network architecture. Fourier and the others might produce the same, that locally small changes in the robot pose will produce small changes in the shape. So locally, this will resemble as a Euclidean space, but if you see it as a globally, some trajectory might not be a connected one in the shape space, as for example, here we are describing. So what we did is we constructed such manifold and then start designing trajectories, which are like geodesic trajectories over such manifold, in order to avoid, say, what it could potentially be unfeasible shapes. And in this paper, we also found that by simply doing the linear interpolation, we may find some linear interpolation in this space. So it might be some shapes that are not, there's no a sequence of shapes that are not really connected or physically achievable from one state into the other. Whereas if we work on developing, on computing the geodesic path, we can find a smoother set of shapes. So this is a nice, interesting planning shape problem that we have been recently working and just recently released in RAL. What else do we have? Okay, yeah, this is also all very recent work. So I told you all about this talk is about different ways to represent it and use it in control. The task remains the same. Yet another way to represent it is by using contour moments. So this is another work that we have been working with my student from HIT. So what do we do here? We have three main parts of this descriptor. We use standard contour moments, which we know they're invariant to translations and rotations. So with this first part, we have 7 numbers that describe in an invariant way the shape of any object. It doesn't matter whether it's deformable or not. We use central moments like centroid to describe the position, the translation of this object. And we use the orientation of the principal axis to describe the rotation on the plane. So in here, we can see how, say for many collected, this is in simulation, many shapes, we can see how these descriptors are varying in this respective space. So we normalize all these because they all have different units. And here's just some experiments showing the same with different types of objects, cables, well, some spongy, and I believe even a rigid object. In this paper, what we are working on, this is a control paper, very control paper. We are comparing different types of controllers. So the one we're proposing is this one. We're proposing finite time sliding mode control. The other ones still work also quite well. But, I mean, it's a control. You need to highlight some issues. In this case, it's exact minimization of the error. But the interesting thing here that we are addressing in this paper is the notion that the same shape descriptor and control method can be used not only to soft objects, but also to do, to consider more like a spectrum, entirely going from purely elastic to rigid and what we here addressing and call as composite. So we are proposing a method for deform or position composite rigid deformable objects with the same method. And these objects might have different types of properties. And yeah, well, more from a practical aspect, this is the latest work of my student here in PolyU. We are working towards doing packing, optimal packing of precisely what we mentioned before, which might be some soft objects, rigid objects, composite, rigid deformable objects. So our idea is to design an algorithm, an optimal algorithm that can decide in an optimal way the type of box that you need to use for optimally packing a series of objects. So we are working on action planner for, at the present stage, we're mostly working with soft and deformable materials. But the idea is that we want to, for example, in this case, completely transfer all these objects into smaller box and decide its specific location. So in this case, what we have been working is on the action planning point of view. So we are designing a series of grasping, re-grasping, and jointly deforming an object such that it fits the expected shape within a confined workspace, in this case, the box. I'm not taking time, but well, this is the last one. Okay, so conclusions for me talk. I have today modeled, as I do with this line of work, the soft object manipulation as a control problem, specifically as a servoing problem, where we can have some form of output representing shape, and then we just feed it back and have an explicit shape error. Key to do that, which is the main topic in this talk is we can represent in many ways such shape with standard geometric features, Fourier coefficients, NURBS, Bezier, principal components analysis, contour moments, and so on. There's probably many other. And by doing that, we're able to do automatic control of manipulating objects and deforming them in various shapes and configurations. So this is the end of my talk, and I thank you all for inviting me. And I'm not sure if I still have time to answer any question.
Thank you, David. Yeah, I think we have some minutes, and we also got some questions. We have the first question from Martin Sundermeyer in the Q&A system of Zoom. In case you want to read it yourself, but it says, wouldn't dense non-rigid registration be required in order to distinguish between object pose changes and object deformations? I.e., are sparse 2D representation like contours not too ambiguous in that regard?
Is it valid to say? I don't know. No, well, I refer back to the too ambiguous. No, actually, yeah, I think I get, say, what if, say, I don't know if I'm reading the question correct, but let's say, oh, I can draw. Yes. Let me draw. These things do help. So let's say that we have this shape and it has a small, I don't know, high frequency analysis. That looks like an angry bird. Okay, let's say we have an angry bird, all right? And if I use, very few harmonics, let's say we're using Fourier, we might be able just to remove, the nose. How do we really deform it or rotate it into the way that we want? Is that probably what the question was about? No, yeah, actually, this is a valid point. I do take it. It's true. I might revise my slides based on that later on to say that we don't need it. I say we might need it for these cases.
Okay, thanks. We have another question from the Slido from Rachel Holiday. Could you discuss the pros cons of your virus representations in comparison to each other? Why choose one representation over the other?
Yeah, well, at least in papers, I deliberatively avoid doing that. But no, yes, it's from a reviewer point of view also very good question. Well, if we, can I go to the previous one? I personally like, for what it provides and what it offers, I like principal components analysis. It's so clean and elegant in a way that you can really talk about optimizing. If you go to, say, Fourier, Bezier, contour moments, very frequency and repetitive, but not in an optimal way. PCA does give you a minimalistic way to represent everything. So I mean, my take would be that in that sense, if we consider all these properties, PCA is superior to those.
Okay, thanks. I think we have time for one more. Anonymous wants to know how you found the desired contours in the first place for the shape serving.
Oh, well, the truth in the experiments. Well, I mean, how do we find it? You can actually draw it yourself. I mean, it can be literally any contour. You can, I don't know, it can be the angry bird that I just draw. I mean, you can have anything, and from here you just extract that vector of parameters. In the experiments, in order to know whether it's a nearby feasible contour, what we did is we deform, say, the object towards some region. We collected, save that observation of shape features and just move elsewhere and then try to go back there. That was the experimental approach, but that doesn't mean that the method is limited to that. That was just simplicity for the person doing the experiments. You can draw anything, and an algorithm should be able to extract the numbers that represent that.
Thanks. And I think we have just one more question, so I'm going to also ask it. Faye asks that it's kind of a sensible approach for 2D contour representations, but what's in a 3D case? It happens that different 3D shapes can project into the same contour or in image frame. What will happen in this case, and how to handle this?
Yeah, no, yes, it's a valid question actually. But well, I mean, well, look at this. I mean, this slide. So you can have, say, let's say if I go with my favorite PCA, you may compute your PCA for, say, for I always have it with me in case somebody asks. Of a 3D object like this, no problem. Given that you have the necessary observations to know the shape and the configuration that you have. Say, for example, where was it? In this one, actually, we don't see here very clear, but my student, she's actually computing the backbone of this object. It mostly moves in the plane, but that's by design. I mean, we can also move it in 3D, and we should be able to observe it. So no, it's actually not restricted to 2D. Experiments and many things we've done it in 2D, but analytically, there's no way why it shouldn't be feasible. And actually, well, some of the results we saw, I didn't emphasize this, some of those are actually 3D. We did show something with geometric features. We do have something with Bezier. Also, these contour moments we have done in 3D. So it's feasible, yeah, and has been done.
Thank you so much. This was really a great talk.
Right.
And yeah, thanks you again. And we're handing it off to Martina to introduce the next speaker. And have a good day, David. And we see you in the first discussion round, if I'm not mistaken.
All right. Cheers.
All right.
Thanks, David.
Thank you. Bye.
Okay, so next speaker is Yisheng Lee from Tsinghua University, and he's an associate professor with the Department of Automation. And he received the highly commended paper award in 2013 IF TOM, the best paper in robotic control in 2017 ICRA, and the best application paper finalist in 2017 IROS, and the TJ Turn best paper in robotics in 2018 Robio. And his current research interests include robotic manipulation, vision-based control, micro-nano robots, and human-robot interaction. So thanks, Jiang, for being here, and the floor is yours.
Okay, thanks for the great introduction.
I think, David, you need to stop sharing the screen so Jiang can start sharing it.
Yeah.
But still, David is sharing the slide, so.
Sorry. I was about to go to the toilet, imagine. Good. Okay. Share new. Stop sharing. Yes, my bad. Okay. Jiang, my man, the floor is yours.
Okay, perfect.
Okay. Okay, thanks for the great workshop. So I'm very happy to be here to present some of my recent works. So okay, so my name is Yisheng from Tsinghua. So the title of my presentation today is the adaptive control for robotic manipulation of a deformable linear object. Yeah, the title is seems a bit long, but actually mainly covers three topics. The first topic is offline learning together with the online learning. So the second topic I'm going to say is the robotic manipulation of multiple features. And the last topic, we will discuss some application to the 3D robot. So here is some robotic manipulation of a deformable object in the literature. So actually this result, the result on the bottom, the left one is the result from my previous group, both for Hui Liu's group. So we can see that in the presence of the change of the significant mass of the deformable object, we still can manipulate this green feature point to the desired position. So in our work, we consider this formulation. So this is a deformable linear object. So both ends of the deformable linear object are grasped by manipulator. There are two manipulators. So this is the feature point. The feature point marked with the red color. So then based on this formulation, we can have this equation. So y dot means the feature velocity. The r dot is the end effector velocity, which is also the control input. So these velocity are related by the Jacobi matrix. And we assume this Jacobi matrix will depend on the shape of this deformable linear object. Actually, this shape in the representation, we will use multiple features to represent the shape. But the problem is that in most cases, when we manipulate the deformable linear object, we have no idea about the deformation model. So in the presence of the deformation model, so this Jacobi matrix is also unknown. So the problem becomes, how can we manipulate the wires, the ropes in the presence of unknown Jacobi matrix? So according to our survey, so there are many two ways. So first is a model-based method. But this method is relatively computationally involved, and also it requires the structure information of the deformation model. The second method is the data-driven method. Now the data-driven method become more and more popular in these publications. So we further can divide the data-driven method into two ways. For the offline method, the quality of this estimation of Jacobi will be limited by the quality of the data set. For the online adaptation for the Jacobi matrix, actually it is locally effective, which means that the desired shape cannot be far away from the current shape. And also, if let's say if the deformable linear object is now at the same configuration in the task space, but still we have to redo the estimation for the Jacobi matrix. So this is our formulation. Actually, in this work, we want to combine the advantages of the offline learning and the online learning. So in the offline learning, we do the offline learning first. So the offline learning, we just move the robot and effector in a random manner. So this offline learning is to provide a good initial value for the online adaptation. And the online learning will further compensate the offline learning. So this is to combine advantages of this two estimation method. So our novelty here in this work is that we can claim we can directly transfer the result obtained in the offline phase to the online phase. So there's no need to do any additional work for the formatting. We can directly transfer the result. So we believe such way can fully explore the advantages of these two methods. So this is a bit straightforward for the offline learning. So basically we use the fully connected neural network. So the input is the feature position. We have multiple features, m features. So this x1 to xm represent the feature position. So the middle layer, we use a series of nonlinear functions. We can choose RBF for the radial basis function. It's a very standard. And the output will be the column of the Jacobi matrix. So we would like to point out that actually this structure can be used for the estimation of all the features the Jacobi matrix, because for multiple features, for all these multiple features, they all receive, for the Jacobi matrix, they all receive the feature position. So we can use same structure, just one structure to estimate all the Jacobian metric for the multiple feature along the deformable linear object. And this is our loss function for the supervised learning. So basically, we use the EW, which is the difference between the sensory feedback. We can use the, let's say, sensor or vision to measure the white dot. Then this is the difference between the measurement and also the estimation in the last round. So this is some result for the offline approximation. So the first three figures represent the estimation for the Jacobian matrix, and the red one represent the ground truth because it's a simulation. We use the simulation to validate the offline estimation first. So this is the ground truth. So we have the blue line for the training for 5 minutes. Then we have the green one for the training for 61 hours. Actually, definitely we have a green line performs better than blue line. But in the actual implementation, we may use the blue line. We may just do the offline training for 5 minutes because we have the online phase. So further in the online phase, we will further compensate the modeling errors. So the first three figures represent the estimation for the Jacobian. This is a Jacobian. And also we can use the similar structure for the estimation of the pseudo inverse of the Jacobian matrix as well. Also, we have 5 minutes and 60 minutes. We can simply use 5 minutes, then we move to the online phase. So this is our online phase controller. So this is the estimated Jacobian matrix. So this Jacobian matrix will start from the result obtained in the offline phase, and then we keep updating it with the feedback error in the online phase. So this is a control input. So this delta y represent the position error, which is the feature's position minus the design position. So this is our online adaptation law. So we can see that y dot is the rate of the change of the weight of the neural network. So this update will start from the initial value of the result in the offline phase. So this is why we point that we can directly transfer the result obtained in the offline phase because the weight of the neural network in the online phase will start from the initial value which has been estimated by the end of the offline phase. So then this way we'll start from this good initialization value and then driven by the delta y and the approximation error, modeling error at the same time. So let's say if the point is not at the desired position, this delta y is non-zero. So this w hat dot is non-zero. So the online adaptation continues. So only when the delta y and the EW goes to zero, this w hat dot equals to zero because the feature has been manipulated to the desired position. So there's no need to do the online adaptation because we have realized our control works. So we have some comparative studies for the online adaptation. So this is the feature, and the red one represents the target point, which is the pick one point from the multiple features and manipulate the feature to the desired position. So this is the desired position represented by the green point. So we design the online controller to move the status of the y to the final status. So the below figure shows the result. We can see that firstly, if we deactivate the online adaptation, so we can still have the position error converge to zero in steady state. But if we can add the online adaptation, we can see that the error can reduce to zero in a faster speed. So this also shows the effectiveness of this online adaptation. So this is some simulation and experimental result For the simulation, if we can specify different, trajectory or combination of some set point for the features, we can actually specify different tasks for the shape control of the deformable linear object, but it's basically the planning works. So the below two video actually shows the comparison between the online adaptation. So the first result, we don't use the online adaptation. We simply use the Jacobi matrix obtained in the offline phase. So we can see that in a steady state, we cannot have a very exact information about the Jacobi matrix. So in a steady state, we cannot move the feature to the desired position. But then if we can add the online adaptation, so first the convergence of the position error is faster compared to the case that there's no online adaptation. And also in a steady state, we can successfully manipulate all the features to the desired position. So the next topic is about the multiple features manipulation. Actually, the previous slide has shown some result for the robotic manipulation of multiple features. We find actually there are several challenges for the manipulation of multiple features. The first challenge is that we cannot always ensure the controllability of the system, because let's say if we manipulate multiple features, the control input may be less than the control output. So maybe the system is not controllable. The second challenge is that in some cases, during the transient stage, if we manipulate multiple features at the same time, maybe there's some conflict between multiple features. And the last challenge is the same as the previous one. We have to deal with the Arnold deformation model, which is also the Arnold Jacobi matrix. So we have this dynamic region control to deal with these aforementioned three problems. So the first, we can see that these are three features. So for each feature, we formulate a very big region. So at the beginning, all the features are inside the region at the beginning. So the center of this region is the reference position. You can consider as the desired position of the feature. Then we shrink the region. We scale down the size of the region one by one. So when the region shrink or reduce to a point, this feature also manipulate to the desired position. And if all the features are around the desired position, we can realize the desired shape. The advantage, the novelty by doing this is that firstly, we just manipulate one feature at one time, so we can ensure that the control input may not be less than output, so the controllability problem may be addressed. The other advantage is that actually when the features is inside the region, there is no control input. So when one feature is being manipulated, other features just moving accordingly. So we can address the conflict between multiple features. Later we can show the result. So these are more detail for the region control. So this T bar represent the transformation matrix. So we can specify the transformation matrix to move the size of the region reduced to a very small bound to determine the desired shape. This is realized by specifying the potential energy function. So this desired region corresponds to the bottom part. So when the region shrink, the potential energy, the gradient of the potential area will just push the feature to the center of this bottom part of the potential energy. So this is a simple comparison. We can see that if we manipulate multiple features at the beginning, so this the second point will move downward and the third point will move. Sorry, the second point is moving upward, the third point is moving downward. So there's a conflict between these 2 points. So later we use the region control for the three multiple points. So this is the first region. So when the first point is being manipulated, so these two regions remain static. So actually in a steady state, you can see that the second and third point are away are away from their desired positions, but it's okay. It's just the transient stage. So when the second region shrink, reduce to a very small bond, this will just push the feature back to the desired position, and also for the last feature. So these are two technical we mentioned before. First, we have to set the gradient of the potential energy is very steep. So once the feature is around the boundary of the region, this is a very steep gradient which has to push the feature back to the desired region. And also, if let's say if the feature really escape the desired region, so actually we can make the region bigger again. It's dynamic region to recapture the feature and then rescale down the size of the region. These are more illustration. So this result, the first video shows that we can manually pull the feature outside the desired region to mimic the scenario where the feature escapes from the desired region. So the region becomes bigger to re-enclose the feature. So by using some planning technique, we can specify we can match the specific task for the shape control of the deformable linear object. And also we can choose some maybe more critical features and additional features to make relatively complex the shape. This is circular shape. We can make the circular shape match with the pole under the circular shape. The last topic is about the applications. We actually have a project working on the 3C robot. 3C robot is to deal with some deformable object in the 3C manufacturing, such as the flexible PCB or the USB wires. Due to the deformation, most of these deformable objects in the 3C manufacturing are done by humans now. But actually, the market for the manufacturing is very big. So we get this data just for the iPhone charger cable, the USB data cable. Just for the 3 months, the sale of this charging cable is 76 million. It's a 76 million. So it's really a very big global market. So these are solutions. So this machine cannot deal with the deformable object, can just solder the standard, the rigid PCB. So this is the latest, the state of the art for the USB soldering. Still, we can see that it's not fully autonomous. So we summarize some limitation why we cannot apply the existing result to the 3C manufacturing. First, we have to assume that the robot manufacturer is always controlled to contact the deformable object. The second limitation or assumption is that we actually mainly consider the kinematic level. But in the 3C manufacturing, the speed is very high. So we have to design our controller with the consideration of the robot dynamics. So so in this project, we propose some prototype for the 3C robot. Sorry, how long do I have? How many minutes?
Okay, you have some other few minutes. Okay. Please, maximum 5 minutes.
Okay. I will speed up.
Thanks.
Yeah. Okay, so first the deformable object we are going to consider is the flexible PCB. So this is the system. So we have the vision is 2D vision to capture the feature, and then we use the vision feedback to control the robot to contact the flexible PCBs and do the active deformation. The main challenge here is that actually this contact point is away from the feature, is the solder pad. So let's say if the PCB is not calibrated, the deformation model is unknown. So we have no idea what is the exact information of the Jacobi. So similarly, we use the adaptive neural network online to deal with the unknown Jacobi. And the other contribution for this work, we can combine different feedback information based on the regional feedback into a single controller. There's no hard switching between different phases. So first is the region control for the contact contact test. This controller is to drive the robot infector to automatically contact the flexor PCB. The reason we use the region is that the region can provide more flexibility for the contact task, because what we need to do is just move the robot to contact the deformable object. So there's no need to specify a very fixed, very specific contact point. So another controller is this vision-based controller. So the key point for the vision-based controller is that we have to ensure that the robot has already contacted the flexor PCB. So definitely, if there's no physical contact, there's no way to do the active deformation. So this composite vector is to synchronize the contact task and the active deformation. So sorry, due to the time constraint, I cannot say too many details. Later, if you want to discuss, we can discuss later. So this is a prototype for the flexor PCB, and this is some illustration for the contact and active deformation. And this one shows that if we can make the solder pad, two solder pad match, then we can activate the soldering machine to solder them together. People may ask, how do you set the design position for the feature? So in this experiment, we just show the idea of the contact and active deformation. So we manually specify, but in actual implementation in a factory, we can use some visual tracking algorithm to check the solder pad of the other PCBs in real scenarios. So this formulation can also be used for the shape control of other robotic systems. So this to show that if we start from different initial position, we can still move the feature to the design position. So the last object we are going to discuss is the USB-Y. So as we mentioned before, people need to get involved at the beginning. So what the people need to do is to separate the 4 USB-Ys and then make sure that the color of this 4 USB-Y is correct. It's a design sequence. This is very important. If the color sequence is not correct, even we can manipulate the 4 USB-Y. This soldered or assembled USB cable cannot function properly at all. So we propose this another objective for the robot. So combine 2 levels to try to push the robot to automatically transit between different phases of the manipulation to automatically grasp Y and manipulate Y to the design position. So this is another solution for the USB sorting. So we have a more hardware design. So the robot can automatically separate the 4 Ys and then just sort the Y. Make sure that the color sequence is correct and finally press the Y. And through the result, we can see that there's no human involvement at all. It's fully autonomous. So this is principle for the separation and the sorting module I just skipped. And in the actual implementation, we also use some deep learning, deep vision network. This is to ensure that the detection of the grasping point is correct, even in the change of the illumination or in a change of the factual environment. So finally, is the conclusion for my talk. So first, we propose the offline learning and the online learning. So we want to combine the advantages between these 2 phases, but the problem is that how to transfer the result directly to the online phase. So we propose some technical based on the neural network to realize this objective. The second topic is the dynamic dynamic region. So for the multiple features, so we believe by using dynamic regions, we can address the conflict between multiple features, and also we can ensure that the system may be controllable for multiple features. So last topic, we did some application to the 3C manufacturing, and we built a prototype, and with the regional feedback, we can improve the autonomous capability for the robot. So this will be the end of my presentation. Thank you so much for it. Sorry for the delay. No.
Okay, thanks. Thanks for the talk. It was really nice, and I think you showed a really nice combination of the formalism from control theory and the learning. There is a question. The Adrian Kessler is asking on slide 11 how to ensure that the sequential approach of servoing one feature after another is successful. And is there a case where trying to servo the third feature will put the first feature out of its target? For instance, some cable with a higher bending stiffness.
Yes, very good question. Actually, we are working on it. We are working on it. My answer to this question is that actually we don't need strictly assume that just the one feature is being manipulated at one time. The reason we introduce the dynamic region is try to make the controller maybe as sparse as possible. So definitely, if one feature escape from the region during the manipulation, this will generate a control input. But we can use the region control to make sure that not all the features will escape from the dynamic region. So if let's say the feature is outside the dynamic region, still the region controller will try to push the feature back to the region. But definitely by using the region control, we can control less dimension of the state compared with you just activate the control for multiple features, all the features at the same time.
Okay, thanks. We have another question from Zhu Peng, and the question is if there is any way to predict whether the target points or shapes configuration is achievable or not, since every time if we need to execute to check that the process will be very time consuming.
Yes, actually it's also very, very good question. And in fact we are also working on it. I do not have an exact answer to this question, but maybe I have some suggestions. What we need to do is that, let's say if you manipulate the deformable linear object, and definitely when you specify the design position, we have to ensure that it's achievable. First the guideline for specifying the design position is that you have to match the task, right? You have to match the task. You have to match the main features of that task. This is the first guideline. The second one is that we have to consider, let's say, the constraint of multiple features. So when we specify a series of design set points for the multiple features, we have to ensure that this distance between two neighboring features is just can match the feature you specify along the deformable linear object. This is the second guideline. The third guideline we are working on is that we also taking part into the dynamic model, the deformation model or dynamic model of this deformable linear object. So for some cases, maybe it's a bit elastic. So some distance between the initial distance of two features can be enlarged or can be maybe, I have no idea, maybe condensed a bit at a steady state. Yes, so this, yeah, I hope this can provide some suggestion for your future work. Still, yeah, sorry for that. We're still working on this topic.
Okay, nice, thanks. And I have just a curiosity. So regarding the multi-features application, so one question is, are these features pre-selected, right? And in this case, is there a kind of procedure on how to select these features and if they then affect the performance of the approach?
Yeah, it's a good question. But I think for selection of the feature, Debbie have give a very great workshop. I think we can refer to the feature selection based on his talks. For my experience, if we're talking about application, so for the 3C manufacturing, we just choose the feature, let's say case by case. If we are going to solder the USB wire, definitely the feature will be soldered back on the flex or PCB. If we are going to deal with the sorting task of the USB cable. There are 4 USB wires, so the feature will be 4 different colors. I mean USB wires. So it's I think in practical it's a totally case by case. Yes.
Okay. Okay. Thanks a lot.
Yeah. Thanks.
Thanks for joining. I think we can move on to the
thanks.
spotlight
So I
session.
stop sharing my slide.
Yeah. Thanks.
Yeah, thanks.
Okay.
Right. This brings us to the first spotlight talk session. As we said, it's going to be the 5-minute pre-recorded video and then a 1-minute Q&A. So type your questions again in the Zoom Q&A or in the Slido. I should now have added most spotlight talkers. I think we are missing Satoshi Funabashi. If you are in the attendance, you can raise your hand and I can add you, so you can also answer questions. Not, it's just going to be the video, so that's also fine. Then, yeah, Martina, you can start the video.
Okay, it's here. I will make it him panelist.
Ah, perfect.
Okay, nice.
And we have everyone.
Okay.
Hello everyone, I'm Satoshi Funabashi from Waseda University, Japan. I'd like to talk about our research in hand manipulation of multi-fingered hand with daily objects based on graph convolutional network and 3-axis tactile sensing. In the background, the multi-fingered robot hand is capable of dexterous manipulation. On the other hand, the acquisition of tactile information for the contact states can improve the manipulation stability. So when we see the previous research on multi-fingered hand control, some studies achieved the dexterous manipulation by using deep learning, but there is little tactile info like this one. This research doesn't use tactile information, or this one use only for fingertips. So the achieved manipulation is limited, or the object was specific for the manipulation. On the other hand, when we see the other research which focus on using tactile information for the multi-fingered hand, which is actually our research, achieved the high object recognition rates by using CNN and also considering the position and the sizes of all the sensors. So in this research, we could use all the tactile information from the entire hand, but still it has a problem that the results are unstable because the size of the tactile feature is not uniquely determined by experimenter. Also, we also need to think like to recognize the softness and the slipperiness, I mean the object properties, so that the robot hand can manipulate a variety of objects. But when it comes to multi-fingered hand, occlusion usually happens, so we still need to focus on the tactile information. So here we propose the motion generating method based on graph convolution network, GCN, and also property labels. So firstly, we prepare the graph convolution network so that we don't need to do the engineering of the tactile information in advance. And also we prepare the property labels to input the GCN so that the hand can change the manipulation motion according to the property of the graphed object. So firstly, we did a comparison of GCN structure. So as you can see, most of the models could generate a successful motion. But actually, when it comes to the final posture of the manipulation, only this one, which had the most number of the convolution layers or the size of the convolution layers, could achieve the most number of successful manipulations. So we confirmed that the larger the number of the GCN convolution layers and the larger the sizes, we could get the greater number of successful manipulations. Also, when we confirmed the features from the convolution layer of model 1, which is the most successful one, we could confirm that the network acquired the feature of the position and the robotic configuration and the tactile features like thumb, middle finger, little index, and the palm. So we confirmed that it acquired a feature, and then it could generate a successful manipulation. Also, we did an experiment on the deformable object, and as you can see, it did a successful manipulation. But when we add the correct labels, like this object is a deformable object, and then the final posture is like this, it doesn't deform. But on the other hand, when we add the wrong labels to the GCN, it does the manipulation, but when we see the final posture, it squeezes the object. Also, when we see the trajectory during the in-hand manipulation, when we add the wrong labels to the GCN, it generates always generate the higher forces. On the other hand, the correct labels provided low forces, but still it could achieve the successful manipulation. So we confirmed that using appropriate property level is effective, and in it, I mean, the hand didn't squeeze the deformable objects. So here's the conclusion. Thank you for listening.
Thank you. Then we have now time for questions. Let me just check the system. So I have the question. So you added a bunch of sensors. Did you also investigate like which of these sensors give you kind of the most information?
Yeah, that's a good question, and we didn't try it yet, but yeah, I want to try that. And also, I think the fingertip is the most important thing because the hand grabs the object from the desk, especially using fingertips.
Okay. So that's future work then.
Yeah, currently working on it.
All right. If there are no more questions, we will go to the next spotlight talk. It's going to be Sarah Navarro from the University of Siena with the Mac gripper, soft rigid gripper augmented with an electromagnet to precisely handle the gloves.
Hello everyone, I'm Sara Marullo, and in this video we'll present Mac gripper, a work on autonomous manipulation of garments. We propose to approach the autonomous garment manipulation by considering gripper and garment as cooperating parts of a dyad aimed to successfully achieve the desired manipulation. Mac gripper allows to improve grasp repeatability and precision by design, compensating uncertainties in the target grasping locations. And the idea underlying Mac gripper is currently patent pending. Garment manipulation is extremely challenging due to the fact that the configuration assumed by the garment is highly dependent on the grasping points, and the relatively small variations can lead to a task failure. On the contrary, grasping in proper locations lead to rapid and efficient task accomplishment. Our core idea is to exploit an attractive force between gripper and desired grasping points located on the garment. We consider to establish an attractive magnetic force between the gripper and the garment. Hence, we designed Mac gripper, an augmented jaw gripper embedding an electromagnet and capable of interacting with garments equipped with small ferromagnetic parts that can play the role of ornamental or brand elements such as buttons, studs, or small plates. Mac gripper is an augmented jaw gripper. In its central part there is an electromagnet mounted on the top of a linear actuator. By activating the electromagnet, a magnetic field is generated, which causes a magnetic force attracting the ferromagnetic part attached to the garment. Due to the attractive motion of the ferromagnetic part, a collision between the end effector and the garment occurs, and is detected by a small resistive force sensor located near the electromagnet. And the collision detection triggers the closing motion of the jaws. So the electromagnet allows to grasp the garment in the desired point, while the jaws allows a secure grasp maintenance during the manipulation. Concerning experiments, the electromagnet allows to grasp the garment without unnecessary wrinkles that usually lead to unpredictable change in the garment configuration. The electromagnet instead allows to achieve a conic-like shape, similar to a pinch grasp. Clearly, the larger is the plate located on the garment, the greater is the probability of successfully grasping the garment. At the same time, however, the probability of performing the grasp always in the same location decreases. Concerning weight and thickness of the garment, thickness is more relevant than the overall garment weight. As a matter of fact, changing the thickness results in varying the local mass the electromagnet has to attract. So, if the local mass increases, the electromagnet needs to be closer to the plate to cause the attractive motion of the ferromagnetic part. Having an attractive motion of the garment towards the gripper has interesting advantages. For instance, an intrinsically safer robot environment interaction, the possibility of performing aerial grasps, as well as the possibility of quickly re-establishing the contact in case of contact loss during manipulation, besides the possibility of coping with grasping point location uncertainties. Concerning the last point, we investigated the possibility of performing a sort of partially blind grasp. A blind grasp is meant to be a strategy according to which the robot is first commanded to reach the estimated grasping point, and if the contact between the object and the gripper is not detected, the robot starts spanning a small area around the estimated grasping point to exploit the magnetic attraction. To conclude, my gripper proved to be a suitable tool for autonomous grasping of garments, exploiting the magnetic force to perform a repeatable grasp execution and to compensate the planar uncertainties on the estimated pose of the target grasping point. Moreover, the extended point-like contact produced by the electromagnet allows to perform grasps without unnecessary wrinkles, achieving closing configurations more suitable to vision-based machine learning techniques for autonomous manipulation. And now we would like to establish a synergy with researchers in machine learning and producers of garments to develop new lines of robot-friendly garments. Thanks for listening.
Thank you very much. Just a reminder, you can use Slido or the chat to ask any questions to the spotlight talker. I'm having a question regarding the need for the metallic plates in the clothing. You just presented that you might get it like in ornaments like buttons or so, but doesn't this restrict the grasping points too much? What do you think?
Well, we can have some small metal plates, but if needed, we can think about something more complex. We can also have some wires, ferromagnetic wires in the garments. So depending on what we need, we can think about suitable solutions. So the grasp, if you need to grasp the object in a specific point, well, you can simply put a small plate in that point. The idea is that you are interested in grasping in specific locations. So if you know what are your locations, then you can exploit this information. Clearly, the specific location, in our vision, the specific locations are the output of some machine learning based algorithms. So then we need a synergy between researchers and garment producers.
Okay, thank you. Very interesting.
Thank you.
And we continue the spotlight talk with Yisheng Lee from Seoul National University with the work interactive real-time simulation of robotics snap connection process.
Hello, this is Yisheng Lee from Seoul National University. I will present about interactive real-time simulation of robotic snap connection process. Snap connection is a process connecting two objects into tight complementary geometry by exploiting deformation of deformable objects and is utilized in various industrial sites. For automation of these processes, simulation of the snap connection is necessary. However, the simulation is challenging for 3 reasons. Firstly, the snap connector has high stiffness and lightweight, which leads to large dynamics discretization error when any nonlinearity is included in the dynamics. In addition, to simulate fast snapping motion, a noticeably small damping is required, and for these reasons, the simulation becomes unstable. And finally, the deformable object has high dimension, which makes the simulation slow. Recent studies related to FEM simulations typically rely on iteration-based implicit Euler integration, which induces undesirable numerical damping and cannot simulate fast motions, whereas semi-implicit Euler integration is only conditionally stable. Also, in case of inversion-based simulations, model reduction is essential, and for this, a prior simulation or experiment is required. Therefore, existing simulators are inappropriate for snap connection simulation. In this paper, we developed real-time simulation framework of snap connection, which satisfies discrete time passivity. It does not require a priori simulation, and physical accuracy is validated with experiment. To achieve this, we approximated time-consuming complex collision detection process into simple MLP traversal and utilized GPU to enhance the simulation speed. As the position on the FEM surface is given as input, penetration depth is computed after traversing the network, and normal vector is calculated from the differentiated network. Also, we reduce the dimension of the dynamics of socket connector to speed up the simulation. Firstly, we segment the original linear FEM into one segment with contact and others without contact, and connect them via strong spring. Then balance model reduction is applied to each segment to further reduce the dimension. Balance model reduction is an analytical technique which does not require any simulation or experimental data. However, since coupling terms are still remaining, each equation cannot be solved separately. To circumvent the problem, we analytically eliminate the coupling terms via short complement. With contact force calculated from original FEM, we can solve dynamics of each segment in parallel. Also, every matrix used for calculation can be pre-calculated. This figure shows 3 different snap connectors, which are segmented into 2 segments. After segmenting and applying BMR, the dimension has reduced drastically. If nonlinearity is included in dynamics, discretization error is inevitable. Especially for high Young's modulus, it induces severe instability as shown in the figure. On the other hand, our framework satisfies discrete time passivity without any artificial damping while applying techniques to enhance speed. As a result, we can overcome the challenges mentioned above and stably simulate even with stiff material. Also, it can generate fast snapping motion as it can be simulated with small artificial damping. Additionally, it makes it able to use high spring coefficients to guarantee strong connectivity between segments and reduces discrepancy from the original problem. We validated the accuracy of our framework by comparing the reaction force with that of the experiment. As a result, RMS error of the force was 4.9 Newton, and the frequency has improved about 8.5 to 9.5 times from the baseline simulator. Also, we tested the framework with various geometries and material parameters, and it could robustly simulate different snap connectors. Thank you for watching.
Thank you very much. So I have a question regarding the simulator you use. Like, can you give an intuition how hard it is to set up this FEM simulator to get useful data? You can hear me? Okay. Yeah, maybe you can just type. I'm going to read it out. The answer, like basically intuition about how difficult it is to set up a simulator, like the FM simulator, like how many parameters are there.
I think we may also move on and when the answer is available. So unfortunately, she has problem with the microphone. So I think we can move on and when the answer is there, we just read it.
That's true. All right, then let's move on with Bruno Marek from the University of Zagreb. Will present soft robotic approach to autonomous plastering.
Dear ladies and gentlemen, my name is Bruno Maric from the Laboratory for Robotics and Intelligent Control System, LARIX. LARIX is a part of the Faculty of Electrical Engineering and Computing, FER, from the University of Zagreb. Together with my colleague Marcela Polic, we will do our best to present you our recent work called Soft Robotics Approach to Autonomous Plastering. This paper was submitted for ICRA 2021 workshop representing and manipulating deformable objects. In the beginning, please let me briefly introduce ourselves. Both of our research interests include soft robotics manipulation, with Marcela being more interested in tactile sensing, compliant control, and machine learning. On the other hand, my research focuses on compliant control of industrial manipulators and collaborative human-robot interaction in industrial environments. We are both involved as researchers in the Specularia project. If you are interested in our recent works, please visit our website and also please join Field Robotics 7th session of the conference, where Marcela will be presenting her paper called Compliant Plant Exploration for Agricultural Procedures with a Collaborative Robot. The presentation is organized as follows. In the beginning, I will introduce motivation and related work. Then we will talk about the shape modeling and control of the plastering knife. Since the estimation of the plastering knife deformation is essential for the autonomous plastering, I will introduce estimation techniques used in this work. At the end, experimental results and conclusion will follow. A motivation of this work was to develop an industrial soft robotic systems for the autonomous plastering of complex shaped surfaces. The main idea of such approach is a project Endorse, where we have successfully developed autonomous robotic system for grinding of complex shaped surfaces used in aircraft manufacturing industry. Our approach relies on deep learning-based soft body estimation, where the goal is to estimate shape and deformation of the flexible plastering knife. Controlling both the knife inclination angle and the contact force, the robotic system can apply different plastering strategies. For a proper execution of the plastering task, the robot needs to control both the knife inclination angle to the treated object and the contact force. Since the shape of the tool is a result of the contact between the plastering knife tool and the treated object, we have designed the control system that decouples the system into two parallel control systems by estimating the shape of the knife. The shape of the knife is estimated using RealSense RGBD camera, capturing the complete plastering knife. Inspired by the results from vision-based tactile sensing development, the plastering tool was enriched with visual clues for easy deformation modeling through image analysis. The knife shape was modeled using 3 deformation features. 3 features were later estimated using a deep learning model. During the training phase, a pre-trained architecture was used for deformation estimation on a custom dataset. The dataset was created through the experiment and data analysis. The approach presented here can easily be extended into a more complex 3D deformation modeling, where both the inclination angle and the torsion angle of the knife tool could be estimated. The evaluation of the proposed estimation method and control system is conducted through experiments using industrial manipulator KUKA KR10, equipped with sensors and specially designed plastering tool. The first experiment includes plastering task on a flat surface. On the other hand, second experiment is conducted on a piecewise flat surface with a single discontinuity between two flat surfaces. This is used to evaluate the dynamic response of the knife inclination control, resulting in knife inclination adjustment with low position change. In this work, deep learning is deployed in industrial tasks involving deformable object manipulation. A pre-trained convolutional neural network architecture is trained by a transfer learning paradigm. From the raw camera images, a neural network estimates the values of the deformation features of the flexible robot tool. The experimental results show that the provided control architecture ensures that the tip of the knife tracks the desired attack angle. The remaining deformation features, as well as the estimated contact force, will be used in the future work where the approach will be extended with a coupled force position controller. For more information about our work, please take a look at our manuscript or contact us directly on our email addresses. Thank you for your attention.
Thank you very much.
Thanks a lot. I have a question. It's actually more a curiosity. So thanks for the talk, and the application is actually very interesting. I was wondering how the pre-trained architecture affected the performance of the approach. So have you also compared the results with learning from scratch?
Well, thank you for your question. I must admit that my colleague Marcela was completely involved in all part about neural network. But as I know, the training using the pre-trained architecture was much faster.
Okay.
With the training from scratch, we will have much more cycles of learning, and the results will not be as good as we got with the one from pre-trained network.
Okay, thanks. I was wondering this because the ImageNet is composed of different samples from the ones that you need in your architecture. So that's why I had this question, but thanks a lot.
Thank you for the question.
All right, then we move on, if there are no further questions, to Yifan Wang's presentation from Carnegie Mellon University, Learning Visible Connectivity Dynamics for Cloths Moving.
Hi everyone, my name is Xinyu, and today I will present our work in learning visible connectivity dynamics for cloth smoothing. This is joint work with Yifan Wang and David Held from CMU. Manipulating deformable objects have wide applications, from folding laundry to preparing food. However, these tasks are challenging for the following reasons. First, unlike a rigid object that can be represented by its 60 poles, deformable objects can have high dimensions state representation. Second, deformable objects can have infinite degrees of freedom, presenting complex dynamics. And third, due to heavy occlusion, it's hard to reason about the state of a cloth underneath its surface. So, given an image of the cloth here, how should we represent its state for manipulation? Previous method first maps an image to a latent vector, and then, combined with the action, learns a latent dynamics model that predicts the next latent state. However, such method does not apply any inductive bias and can overfit easily. Another approach directly learns the pixel dynamics model, but this approach also does not capture the physical structure of the cloth. In this work, we propose to learn a graph dynamics model. Given the observed point cloud, we first estimate the mesh of the cloth, and then learns a graph neural network dynamics that predicts the state of the cloth in the next time step. Why do we use a graph? The reason is that the cloth can be modeled by a set of points connected by springs. This gives a natural graph representation of the dynamics and the forces applied to each particle can be modeled by different types of edges. For example, the forces applied to a particular particle include the gravity, spring force, and collision force, and these can be modeled separately. Here's an overview of our method, and I will describe each component in detail. In the first brain, given the RGBD observation, we first voxelize the point cloud and then compute the collision edges by connecting all points that are within the radius R to each other. For each collision edge, we learn an edge prediction GN to predict whether it is also a mesh edge. The input feature on the edge is the distance between the two endpoints. We then learn a dynamics GN. The input to the node feature include the particle position, its historic velocity, and an indicator of whether the particle is picked. The edge feature is the distance between the two endpoints. And the dynamics model then predicts acceleration for each node. Once we have the dynamics model, we play in a high-level pick-and-place action space to smooth the cloth. Given a pick point and a place point, we will first decompose them into a sequence of low-level actions, each denoting a small movement of the picked particle, and then roll out our dynamics model using these low-level actions. To plan with our dynamics model, we use a reward that computes a covered area in the top-down view of a set of spheres centered at each particle. And we greedily select the sample trajectories with the highest reward. Our dynamics model is trained in the Flex simulator wrapped in SoftG. The training data are generated from random pick and places, and the dynamics model is trained with a one-step dynamics loss. For smoothing the cloth, we use a normalized increase in covered area as an evaluation metric. And we compare other baselines and learn a pixel dynamics model, or a latent vector dynamics model, or directly learns an RGB-based policy. We first show that the estimated mesh edges are close to the ground truth at mesh edges. In simulation, our method, denoted by the blue line here, greatly outperforms all baselines on a different number of actions. Here, we show smoothing results in the real world with a Franca on. The left is a smoothing video from the robot view. On the top right, we show scores of sample actions predicted by VCD, and on the bottom right is a rollout prediction of the best action. We show results on two types of cloth. The first one here is a cotton cloth. The second cloth here is made of silk. We can see that in both cases, the robot is able to smooth the cloth in a few pick-and-place actions. In conclusion, we propose learning a visible connectivity dynamics, which poses strong inductive bias that fits the physics of deformable objects like cloth. We show zero-shot sim-to-real transfer for cloth smoothing of different materials. For ablation studies and more videos, please check out our website and the paper. Thank you.
Thank you very much. Very nice presentation. There is some question from Slido. If you did you consider adding the action magnitude as a node attribute, or did you try different graph attributes that were not successful?
Sorry, there's a problem with my computer. Can you repeat the question?
Okay. Did you consider adding the action magnitude as a node attribute, or did you try different graph attributes in general that were not successful, and then you went for this method?
Yeah, we didn't try actually our action representation is we didn't embed the action as a node feature, but for the pick point, we directly modify the graph structure that the pick point is rigidly attached to the gripper and its position and velocity is modified. So, and through that, it will through the mesh, the edge connections, it will affect the motion of the other particles. We didn't try with we didn't really try with many different combinations of the node features, and so yeah, I'm not sure how well they work.
Okay, there's a second question from David about how important was the edge prediction graph neural network to get accurate dynamics. Did you perform any evaluation study?
Yeah, sure. We have like different applications where like we remove the edge prediction GNN at test time, but we only use the collision edges and we fix it through the rollout, and the performance is much worse. And one reason we guess is that the collision edges they are much denser than the mesh edges, and they are dynamically reconstructed at each time step, so they cannot represent the fixed underlying code structure, which like affects the dynamics throughout a lot, and that leads to worse performance.
Thank you. Very interesting work. We move on with Peng Zhao from Hong Kong Polytechnic University with a latent and semantic framework for deformable object representation.
Hi everyone, I am Peng Zhao. I'm a PhD student at Robotics and Machine Intelligence Lab at Hong Kong Polytechnic University in Hong Kong, China. In this video, we introduce a new data-driven latent and semantic framework for soft object manipulation. Soft objects are widely existing in our daily life. In the past few years, this domain has witnessed many encouraging results. For example, some works already can automatically control the curvature of the creature and contour of the soft objects, or bend or fold a tower, or even freely manipulate cables in real time. In spite of encouraging results from different software manipulation tasks, it is still very hard to extend the system for new soft objects, because they usually use different level of feature specific for different soft objects. So the objective of this work is to design a general representation framework to support different soft objects manipulation tasks. As shown in this figure, we built a 3-level representation framework, which can be partitioned into 4 layers. Layer 0 is to complete low-level geometric feature extraction, such as contour descriptor, surface normal, vector, and so on. Layer 1 and Layer 2 form the mid-level representation layers. The first phase is focused on dimensionality reduction to generate a latent space, and in order to have a concise and compact representation. In the second learning phase, we design several semantic techniques to better understand the latent variables. With the output from the mid-level, we design shape deformation analysis, which allow us to explore the high-level semantic shape knowledge. More importantly, shape planning from the current shape to the target shape can be achieved by geodesic path interpolation in the learned latent space. The left image shows the experimental setup of the shape data collection to build this framework, where a sponge bar labeled with 8 markers is manipulated by human hands, and then their positions are computed by motion capture system. The right figure shows 7 predefined shape classes. As for semantic deformation process, the left video shows the soft object manipulation by motion gestures, and the shape was represented as a point in the built latent space in a real-time manner. The entire deformation process will form a trajectory between different shape classes in this latent space, thus revealing some rules of shape deformation in real-world applications. With this framework, we can solve a shape planning problem in latent space. Given current shape and target shape, we can form a shortest path in this latent space, and a geodesic path updated with a linear interpolated path. By reconstructing the geodesic path-based latent space shows a more smoothing and natural deformation process compared with the shortest path techniques. For more information about this work, you can visit our project website. That's all for my presentation, and thank you for listening.
Hello everyone, my name is Jiang.
It's too early. Thank you very much for the presentation. I have a question regarding the type of deformable objects you use. You use this pool noodle. How would this approach kind of scale to more complicated or even more deformable objects like cloth or like t-shirts?
Thank you for this question. For more complex issue, I think if we can collect some data with the better strategy, we can still use this framework to solve some problem, especially for some visual planning. For example, when we try to close some t-shirts or some other garments, it's very important to have visual planning, since this task is kind of a long-term horizon task, right? And we also need some intermediate states that we can achieve the final goal one by one step by one step. Yeah, which is very necessary and also helpful for this kind of task. Yeah, thank you.
Thank you. Very impressive, Rick. We move on with Yifan Wang from KTH, Royal Institute of Technology, and his presentation about graph-based task-specific prediction models for interactions between deformable and rigid objects.
My name is Yisheng. Today, I will present our paper, Graph-based task-specific prediction models for interactions between deformable and rigid objects. This paper has two contributions. First, we built a novel dataset for task-specific action effect prediction. Different from some previous work, we consider a bag with complex shape and multiple types of interactions. Second, we propose a method for predicting the interaction dynamics based on graph networks. Regarding the dataset, we generate 20 different scenarios by varying different task parameters. For each scenario, we split into 80, 10, and 10% for training, validation, and testing. These are examples of 4 different types of actions. To model the interaction dynamics, we start from what we have in the scene. In the scene, we have a deformable bag and multiple rigid balls. Each ball is represented as a key point, and the bag also has some associated connected key points on the surface. Each key point has a position, a radius, a fixed label flag, and a connection flag with other key points. For the radius here, when it is a ball key point, it is a ball radius. When it is a back key point, it is a small constant value. The fixed label flag here is either 1 or 0. As shown in the opening case, the key points on the left handle is fixed in place, so the fixed label flag is 1, otherwise it is 0. The C flag here is either 1 or 0. It is 1 only when we assign connections between 2 key points. We also have some external input. We control one point and move it from one place to another place, which are P start and P end. We also have a radius variable here. When we control and move the ball, it is a ball radius, and when we control and move the back key point, the radius is set as a small constant value. We then convert the observations and the external input to get into a fully connected graph. We encode each key point as one graph node, including the position, the radius, and the fixed label flag. The spatial differences and the connection types are encoded as age attributes. The external input are encoded as a global feature vector. Given a graph at time step t, we want to predict the key point position at time step t plus h. Based on the graph representations, we propose a model with 2 different modules for capturing the dynamics, which are called APM and TPM. TPM is used to predict the movement of every key point, and APM is used to predict a binary mask, which indicates if the node is moved or not. In the inference stage, we have different inference models depending on how to use the modules. First, we build a one-stage model by using PPM alone. Then we build a 2-stage model by considering the APM module. APM produces a mask, and we only update the moved particles in the inference. Finally, we propose a mixed horizon strategy for long-term prediction based on 2-stage model. We train 2 different models for short and long horizon. In the inference stage, we combine 2 models to predict the final results. Here's the comparisons of 3 different inference models from vision inspection. The mixed horizon model fixes the sphere's point movement and has more accurate results compared to the original 2-stage model. Here we show one example of comparing the ground truth and our mixed horizon prediction model for pushing action. For quantitative evaluation, we first evaluate the single time step prediction error for the 1-stage and the 2-stage model. From left figure, we see that the 2-stage model decreases the mean position error and also reduces the inter-task variance. From the right figure, the model has similar performance on two different materials. We then calculate the long-term accumulation errors for different actions. The two-stage model always outperforms the one-stage model. The mixed horizon model reduces the long-term accumulation error, but sometimes produces worse result in short-term prediction. In conclusion, we built a novel dataset and show it is feasible to use graph networks to model interaction dynamics between rigid and deformable objects. The dataset and the code are publicly available. Finally, we would like to thank KAW, PR, ERC, and DFG for the support. Thanks for watching.
Thank you very much.
I think we have a question. So the question is, right, how to define the best number of graph nodes to represent different deformable objects?
So this is a good question. So the number of the nodes in the graph actually depends on the number of the objects, the rigid object, and also the number of the key point selection on the back surface. And in my paper, based on the dense mesh, we pre-select a sparse mesh on the surface to get a sparse key point set, and it is manually selected to preserve the overall appearance and the topology. And actually here we fix it, and we didn't test other set of selection for the key point, but it would be interesting to investigate in the future. Yeah.
Okay, thanks. And I have just a curiosity. So have you tried the models with even longer horizons? So it's really nice that you combine these models, but I was wondering how you selected the horizon for the long horizon model.
You mean to longer the prediction, the length of prediction, or use other horizons for the other horizons of the model? Okay, so in the because here in the dataset collections we fix the length of the data generation is 6 seconds. So in the inference stage we only evaluate for the 6 seconds. And also regarding the mixed models, in the current settings, we choose a simple way to combine only two horizons, but of course we can use other more horizon models, as you said, and use other strategies to do the combinations or fuse them in a proper way. But here we do not examine this, but it will be very interesting to investigate, use more horizons and other strategies to do the fusion.
Okay, thanks. I think it's really, really a nice work.
Thank you.
There's one more question just coming in. If you are using model predictive control.
Yeah, so currently we do not use the predictive model for the control, but we are now going to incorporate the prediction model also with the MPC for the simulation environment, and it is ongoing, yeah, but not presented here.
Very nice, thanks. This concludes the first spotlight session. We're now going to have a short coffee break until 11:15 GMT +0. So that's in 5 minutes. So yeah, take a quick leg stretcher and see you back in 5 minutes.
I think we can wait other few minutes as we were a bit late. So maybe we can start at 1:20. Hi, Zachary.
Hello, Martina. How are you?
It's going fine. How is it going to you?
Oh, it's going well. It's a bright and sunny morning here.
What time is your workshop?
So my workshop, it's going to start in like a little over 2 hours from now.
Okay. Yeah, that was crazy with the time zones.
Yes.
It was kind of difficult to organize all the speakers, but
Oh,
thanks
yes.
for being here, even if you have the workshop.
Oh, absolutely. Well, my pleasure. Yeah, we also have speakers from, well, all across the world, from the US, Europe, and from Asia. So yeah, it is very challenging getting
Yeah.
in a single day.
Yeah. But it seems it's working. So let's see.
Looks like it's working for you as well, in your guys' workshop.
Yeah. Okay, I think I can start introducing you so that it will take just a few minutes. Okay, so Zachary is a PhD. So Zachary Erickson is a PhD candidate at the Georgia Institute of Technology, and he is advised by Professor Charlie Kemp. And he received his master's degree from Georgia Tech and his bachelor's degree at the University of Wisconsin-La Crosse. And starting from this fall, he will join Carnegie Mellon University as an assistant professor. So congrats. And his work has won the Best Student Paper Award at ICRA 2019 and Best Paper in Service Robotics finalist at ICRA 2019. And his work spans the fields of physically assistive robotics, haptic perception learning, physics simulation, and human-robot interaction. So the floor is yours, Zachary.
Thank you. Let's try to share the screen here. Oh, second. Let's see. If I share this.
Yeah, perfect.
Then, oh, I can't. Play. There we go. All right. So do you see this?
Yes, perfect.
Awesome. So, hello everyone. I'm Zachary Erickson. Thank you, Martina, for the introduction. You covered pretty much my entire beginning slide here. So I'm going to share with you some of my past and ongoing research on leveraging soft body physics simulation for developing intelligent robotic caregivers. But first, before I begin, just a little bit about myself. This is kind of things Martina's already talked about at this point. I'm a fifth-year PhD candidate in the Healthcare Robotics Lab at Georgia Tech, where I'm advised by Charlie Kemp. And in the fall, I'll be joining CMU as an assistant professor in the Robotics Institute, and I'll be building a lab focused on robotic caregiving. So my research focuses on intelligent physical assistance. Robots are in close physical contact with people. These robots aren't just standing next to a person, they're touching the person, applying force, sensing, and manipulating the human body. An example from my research on what this close physical interaction can look like is bathing assistance, where a robot is using a wet washcloth in order to clean off a person's body, or dressing assistance, where a robot is helping someone with disabilities put on a fresh set of clothes for the day. Robots present an opportunity to have a profound impact and improve the quality of life for millions of older adults and people with disabilities. And what I'd like to focus on in this talk is robot-assisted dressing, the task of manipulating cloth around the human body in order to help someone with physical disabilities get dressed. Now, since safety and comfort are important during this process, one natural question for us to ask is, can a robot estimate the forces it applies onto a person? Yet for the task of robot-assisted dressing, this question can be a bit difficult to answer. First, deformable cloth is making contact with a person, which results in these complex force distributions. Visually estimating the coupled cloth and body state remain exceptionally hard today. And it's difficult for robots to take on a person's perspective. Our somator sensory system, our skin, it's wonderful for us, but it's not particularly useful for robots. It doesn't provide robots with much data. So to overcome these challenges, we've designed a physics-based simulation environment, which allows us to simulate how fabric applies force onto the human body. This environment consists of a few different elements. First, a robotic end effector pulling on the sleeve of a hospital gown onto a simulated arm. And the colors that we see on this arm are what we call a force map, where each color indicates different levels of force being applied. Blue is low force, red is high force, being applied at specific regions along the arm. And what I'd like to show you is how robots can use low-dimensional haptic measurements from their end effector in order to estimate a high-dimensional force map across a person's body in real time during assistance. This will allow a robot to take on a person's perspective and view this task from a person's point of view in terms of how the person is having forces applied onto their body. So again, I'd like to share with you a novel technique in which robots can use low-dimensional local measurements from their end effector, think sense of touch here, combined with learning using temporal features in order to estimate high-dimensional forces applied onto a person's body by deformable fabric. Now, these force maps look continuous and smooth over the arm, but they have a discrete representation underneath. So let's briefly look at that, since it's going to impact how we learn these force maps. So the human arm is discretized into 300 force sensing points. You can think of these as little force sensors all over the arm. A vertex on the deformable cloth mesh will make contact with the simulated body at some arbitrary position X, and it'll apply some force F. And what we're going to do is distribute the magnitude of that force to the nearby force sensing points on the limb. And if we were to just color each of these force sensing points according to how much force is being applied to each one, we'd end up getting a figure that looks something like this. And then what we do is we perform an interpolation over all these points in order to generate a nice smooth force map along the arm. And so now what we'd like is for robots to be able to estimate these force maps. And the way we do this is by building an estimator, a function f, that takes as input prior measurements from a robot's end effector, as well as a current measurement from the robot, and then uses this to estimate a force map across a person's body. And it's important to note here that this estimator does not have an explicit model or observation of the fabric. Right? It's estimating these force maps just from end effector measurements alone. So now we're going to be getting these measurements in simulation from the end effector. This includes haptic and kinematic measurements, force, torque, and velocity. And in terms of the real world, these measurements are also going to be quite easy for us to collect. We're going to be doing so using a force torque sensor, and this sensor will be connected to the fabric garment, which the robot is also holding. Now, in terms of implementing this estimator, we're going to do so using a recurrent neural network. And at every time step, this network is going to take as input these 9-dimensional end effector measurements, and then output an estimated 300-dimensional force map across a person's limb. And here we're using a long short-term memory or LSTM network for this estimator, but there are certainly other types of architectures or temporal networks that would work here. What is important is to have some form of model that leverages temporal features in order to make this mapping tractable from a 9-dimensional input to a 300-dimensional output. So we can now train this recurrent network using simulation. We perform 5,000 randomized dressing sequences in physics simulation, where the robot is just moving around randomly in a self-supervised fashion with the goal of collecting lots of data of how fabric interacts with the human body and applies force onto a person. And so now we can collect lots of data from simulation and train our estimator on that. But what happens is that if we just try to naively use this estimator, we end up getting some really weird scenarios like this, where the trained model is estimating these tiny forces all over a person's body. And this is just regression error. This is error in our recurrent neural network, where the model is constantly estimating these small forces all the time, even though the cloth isn't in contact here. So to overcome this, we build a contact map, which a robot will also be estimating. And just like the force map, this contact map will have 300 points, one for each corresponding force sensing point on the limb. And this contact map is set up just like a binary classification problem, where for each point along the arm, it's going to be assigned a value of 1 if the cloth is applying some non-zero force at that point. Otherwise, the contact map will receive a value of -1. And then if we bring this back into our recurrent neural network, we're now going to be estimating both the force map across a person's body, but now also this contact map, so a 600-dimensional vector that we'll be estimating. And what we can do after performing an estimate is loop through all of the forces in the force map and zero out any of them in which the contact map indicates that there's no force being applied. And so this is going to allow a robot to estimate both how much force is being applied onto a person, but also if force is being applied at specific regions along a person's body. And again, this is just to overcome these small errors in our regression model. And in practice, we find that it works quite well. So let's look at that. How well are we able to estimate these force maps in simulation? On the right-hand side, we're showing the ground truth force maps from simulation. This is the forces the fabric is actually applying onto the simulated arm. And on the left, we'll be visualizing the estimated force maps, which is the output of our recurrent model. And so here we're looking at two different scenarios of this hostile gown being pulled onto the arm. In the first case, the sleeve of the hostile gown is getting pulled onto the forearm. It's going to kind of tug and pull at the elbow there. And in the second case, the sleeve is going to miss the forearm entirely and just get dragged over the upper arm. But what we're seeing is that in both instances, the estimated force maps from our model are closely aligning with what we'd expect to observe from simulation. And this learning-based technique also generalizes to other tasks with deformable fabric, such as pulling a pair of shorts onto a leg, where here the shorts get caught on the heel of the foot and start to tug and apply force there. But the big question is, can this generalize to real robots interacting with real people? It seems possible, since our recurrent network only needs measurements from a robot's end effector. It doesn't need to know anything about the state of this high-dimensional cloth. But instead of just estimating force maps, let's take this one step further and look at how real robots can predict these force maps into the future. Doing so will allow us to explore the question, how will a robot's future actions apply force onto a person? Can we select actions that minimize future force? So in order to predict force maps into the future, we're now going to set up two different models. The first, both a predictor and an estimator. In this first model, the predictor is a function g, which is going to take as input prior measurements from a robot's end effector, along with now a set of proposed future actions for the robot to execute. And then given this information, we want our predictor to output a set of predicted future measurements that a robot could expect to observe if it were to execute those candidate actions. And here H sub P is the prediction horizon. That's how far into the future the robot is looking. And if you're familiar with what a dynamics model is, this predictor is essentially a dynamics model. And in order to map measurements to force maps, we're going to use the exact same estimator that we've already trained, that we saw just a few slides ago, but I want to change the notation of it a bit here. So this estimator is again going to take as input prior measurements, but now also take in these predicted future measurements. So we're going to pass the output of our predictor into our estimator. And then we're going to use this information in order to output a predicted force map and contact map across a person's body. And again, we're using the exact same estimator that we've already trained, that we saw just a few slides ago. But what's really cool about this approach is we can now start to do function composition, where we have f of g, and that's going to allow us to go directly from robot measurements and future actions straight to a predicted force map across a person's body. And so now if we piece together our predictor with the estimator, we can predict force maps across a person's body that a robot could expect to observe if it were to execute those candidate actions from the left-hand side. And in terms of implementing this predictor and estimator, well, the estimator is really easy. We've already implemented it and trained it, so we're just going to use it here. But now for the predictor, we're going to use the exact same recurrent neural network architecture that we used for the estimator, but we're going to train a separate model. This model will have different inputs and outputs. And a nice thing about this is that we can use the same self-supervised training approach from the estimator that we used to train the estimator to also train the predictor. So we'll collect thousands of randomized dress-in sequences in simulation and use all of that observed data to train the predictor. So we now have a model to predict these future force maps applied onto a person's body. How do we use these force maps to control a robot? Well, we do so using a technique called model predictive control, in which we select actions that minimize the cost function shown above here. Now, I apologize for throwing just a bunch of arbitrary variables on the slides. Let's walk through what each of these terms are going to be doing one by one. This first term in our cost function is going to be minimizing the predicted forces across a person's arm. This is that term that's minimizing those predicted force maps that we've been looking at so far. The second term is going to be encouraging the robot end effector to move forward along the arm, essentially making and encouraging the robot to make task progress. And then the last term is discouraging the robot from rotating its end effector whenever possible. And so that's it to this controller. We then set up a human-robot study wherein a peer to robot assists 10 able-bodied participants with the task of dressing on the sleeve of a hospital gown. And we're going to be looking at two different scenarios here. First, can the robot fully pull the sleeve of a hospital gown onto a person's arm? And then second, can the robot mitigate the cloth from getting caught on a person's body? And what we're going to be doing is varying the prediction horizon anywhere from 0.01 seconds all the way up to 0.2 seconds. And this is that H sub P, that prediction horizon that we're changing here. And so if we prevent the robot from looking very far into the future, what we observe is that the robot doesn't recognize that it's applying large forces onto a person's body until it's already too late and it's starting to tug and pull at the person's elbow here. Yet by allowing a robot to predict further into the future, the robot is able to recognize that it can continue to minimize forces by rotating around the elbow and pulling the garment all the way up to a person's shoulder. And the robot successfully pulled the garment up to a person's shoulder in almost all the trials that we had tested with participants. And similarly, by preventing the robot from looking very far into the future, the robot doesn't recognize that a garment is about to get caught on a person's hand and apply large forces until, well, it's already too late and the garment has gotten caught and starting to tug and pull. Yet by allowing a robot to again predict further into the future, the robot is able to recognize that a garment would soon get caught on a person's hand. It then lowers its end effector closer to a person's body, shown here by this red line. And this allows the robot to mitigate the garment from entirely getting caught on the person's body. So overall, we've seen a novel human perspective taking technique that combines low-dimensional end effector measurements with model-based learning for predicting high-dimensional force maps across a person's limb. And when we combine these predictions with model-based or model predictive control, a robot is able to provide physical dressing assistance while considering how the actions would apply force onto a person's body. So far we've seen how a real robot can leverage simulation in order to predict the forces applied onto a person's body and dress these deformable garments. And now at this point, I'd like to briefly share how we've been recently extending this concept of physics-based simulation for robotic caregiving, simulating many different robots and many different people with a variety of tasks, some of which include manipulation of deformables. And historically, there's been well over a decade of active work on designing robotic systems to physically assist people with tasks ranging from feeding and drinking to dressing to hygiene assistance, all of which require manipulation of deformable materials, whether that be food or clothing, washcloths, or just the soft human body. Yet in almost every case, it's a single robot helping a small group of people with only a single task. Robots aren't able to learn common sense about deformables or the human body that transcend multiple tasks or scenarios. And this is because there are some huge hurdles in the field of physical human-robot interaction. First, capable real-world robots are not cheap. Conducting human studies is also not that cheap, and this has arguably been one of the largest barriers of entry for researchers into the field. There are also risks associated with robots coming into close physical contact with people, and we would never want robots to accidentally hurt someone or put someone at risk. And lastly, collecting data and performing evaluations on a real robot interacting with real people is really slow. And this is especially true when working with people with disabilities. These challenges limit not only the kinds of research we can do, but who can do this kind of research. But what if we could use physics simulation to overcome these challenges? Recently, there's been a growing push for multitask simulation environments where we can train or evaluate robots across a large number of diverse tasks. Yet most of these are within a robot manipulation or navigation context. In fact, there's a complete lack of simulated robots physically interacting with people in any framework. So our research has recently introduced Assistive Gym, the first open source physics-based simulation framework for modeling physical human-robot interaction and robotic assistance. Assistive Gym is a framework for simulating both rigid and soft body dynamics towards developing robots that can physically interact with people across a large number of tasks, including those that rely on manipulation of deformable materials such as clothing or cloth. And what I'd like to share with you is how physics simulation can open up entirely new research directions and opportunities within physical human-robot interaction and deformable manipulation. We've introduced several physics-based environments for physical assistance, developed baselines and benchmarks for robotic caregiving, and we've investigated generalization of physical human-robot interaction from a number of angles, including human motion, preferences, and variation in human body shape and impairments. So one of the first research opportunities that we gain with simulation is the ability to train versatile assistive robots and develop control algorithms towards common sense reasoning. For example, we've developed physics-based environments where robots have learned to assist people with different tasks associated with activities of daily living, such as bathing, feeding, or dressing assistance. And these tasks are selected from literature such that if we have versatile robots that could help with them, it would have real-world impact and be meaningful to many people with disabilities. Physics simulation also enables us to establish benchmarks and baselines for physical human-robot interaction. And this is something that the field of computer vision has done remarkably well at, and I believe physical HRI can benefit from that same mindset. So towards this goal, we've introduced a set of baseline control policies with assistive GYM, each trained with proximal policy optimization and actor-critic deep reinforcement learning technique. And we trained 24 policies, one for each task and robot combination in assistive GYM, where each policy is trained for 50,000 rollouts, and we select the best policy out of 3 random seeds. And the first question we should be thinking about is, well, how well do these baselines perform in simulation? So when assisting a person who holds a static pose, these baseline controllers were able to achieve reasonable performance for several of the assistive tasks, including itch scratching, bed bathing, feeding, and drinking assistance. But it's also worth noting here that there's still significant room for improvement and future research. These are just baseline controllers. They're not solving the field of robotic care for us. And a very clear example of this is that all robots struggled to provide dressing and arm manipulation assistance to an inactive human. Yet by simulating physical interaction, we can now create reproducible benchmarks for assistive robotics. We can now quantify how various robots and controllers are performing when interacting with people across different tasks. And this table here shows the average reward the baseline controllers achieved for each task and robot combination, where bolding here represents the best robot for a given task. And creating physical interaction benchmarks like this is something that's exceptionally difficult and costly to do in the real world, especially when robots are having to deal with deformable materials. Another research direction that we gain with physics simulation is the ability to design techniques for generalizing assistive robots across varying human body shapes, weights, and impairments. So if you would like to train or evaluate an assistive robotic system on 50,000 people with different body sizes, disabilities, and simulations would take maybe 6 to 12 hours, fully automated. And on the left is a visualization from ongoing research where we're investigating assistive robots that can generalize across a large distribution of human body proportions, weights, and sizes. Yet in the real world, 50,000 participants is immediately disqualified. That is far too large of a number. And we instead think, let's just test on 10 able-bodied college students, and that'll still take a week to do a study like that. If we want 10 real participants with disabilities, it's a much slower process, and it could easily take over a month. Another really interesting research topic that becomes available is modeling human preferences and developing control algorithms that learn and adapt to a person's preferences. So assistive GYM provides a reward-based structure for modeling human preferences, and what that allows us to do is train robots that adapt their assistance to different human preferences. For example, robots are penalized more for spilling water on a person rather than on the floor, and robots also learn not to apply large forces onto a person's body. But you also might be wondering if modeling human preferences actually matters. So what I'd like to introduce you to is one of the early development versions of assistive GYM where we were not modeling human preferences. And here the robot has learned to help someone drink water using reinforcement learning. And as it turns out, the fastest way to get water into someone's mouth to help someone drink water is to really just catapult water at their face. So essentially just precision water throwing. And this is one of the reasons why I believe it's important to give robots common sense about deformable materials around people. Throwing water does solve the task at hand, but it's clearly not the right way to interact with people. So again, physics simulation opens up a number of exciting and new research directions for physical HRI and robotic caregiving, which our research has begun to investigate. There are also several other extensions or research directions that sadly, I don't have the time to talk about in depth today, but I would like to just briefly mention them. So we've investigated modeling and benchmarking human motion in assistive gym, where we used a co-optimization technique to learn collaborative human motion. And we found that pretty much across the board, robots are able to provide more successful assistance to an active collaborative human. Assistive gym is also an evolving framework that's been adopted at other universities, and as a part of a collaboration with researchers at Stanford, assistive gym has been integrated with Gibson, which now allows us to simulate robots physically interacting with people in these visually realistic and interactive homes. And then additionally, there's a gap between simulation and real-world assistive robots. Yet there's also risks with just blindly evaluating simulation-trained robots with real people. So to overcome this, we've introduced assistive VR gym as a way to bring real people into physics simulation through a virtual reality interface to interact with and evaluate virtual assistive robots. So in closing, this is an ongoing and developing research direction. And what I've shared with you today is really just the beginning. We have ongoing projects and collaborations that are pushing cloth manipulation in assisted gym to be more robust when interacting with other objects, the environment, and the human body. Beyond that, I'm happy to talk about research offline and discuss potential collaborations related to ideas that I've shared here in this talk. And with that, I'd like to thank you for your attention. It's been a joy sharing this research with you, and I'd be happy to take any questions now. I also left a few minutes just so that we can have a discussion of physics simulation for deformables. So thank you.
Thanks a lot, Zachary. The talk was great, and we have a lot of questions. So first, at the very beginning of your talk, Yifan Wang asked how to evaluate your force estimation model.
Yeah, this is a great question. So how do we evaluate the force estimation or force prediction model? Well, I would say right now, actually, we're currently doing this. So I can provide a little bit of insight into how we're planning on doing this. So at least my initial response is that we don't currently have a way of evaluating whether the forces in simulation are matching ground truth force estimation, or the ground truth forces cloth is applying. Right? Simulation has been optimized to align these forces, but there hasn't been a closed loop process of evaluating, is this correct? So we're currently doing this. And the way we're doing this is we have a deformable cloth simulator. It's a force sensor with about 200 or so deformable force sensors in it. And so we're putting this around the human body, around the human arm, and then pulling different garments onto it, and then validating whether the forces in simulation are matching what we're actually observing from the sensor on real people. It's a great question.
Okay, great, nice. Then we have another question from Yifan Wang, and the question is, I'm curious how the estimator and the predictor will perform when training and test distribution is different. For example, training cloth and training arm can be different from test cloth and test arm. In addition, it seems that a human is assumed to be static here. What if a human actually moves during dressing?
Yeah, these are all very good points. So there's definitely a big question with what happens if the cloth in the real world doesn't match the cloth in simulation. That would absolutely, it's out of distribution in that case, and whether the models generalized to that is unclear, I would say at this point. The simulation that we saw there has actually been optimized based off of real world force data from pulling a hospital gown onto different objects and the human body. So the simulation itself has been optimized based off of real world data, but that's again specific to a certain type of cloth, right? So if you change the cloth, we would expect there to be different dynamics. And this is just a challenge with soft body simulation in general, is that there's lots of different types of soft bodies, including lots of different types of cloth. And at least currently, the ongoing approach to this is you need to collect some real world data and use that data to optimize the simulation. Right? So for each type of cloth that you'd like to use, there is kind of an optimization process to get the simulator to align with that. Now, in terms of, so that was a good point. In terms of the staticness of the human body, I also agree with you. The human body, at least in that work that I showed at the very beginning, was static. Some more recent work, again, doing the evaluations of that in the real world, there is some human motion in play there, but again, it's pretty minor. We're not seeing any significant human motion. And that's where, so that is actually definitely a limitation of that, that approach. And that's where hopefully we're looking at kind of breaking that in this future work with assistive gym, where we're actually modeling human motion. We've got controllers for humans at this point, and looking at how robots can, again, learn to do different types of deformable manipulation once the human is actually in motion, collaborating with a robot. These are good points. Thank you as well.
Okay, thanks. That was also the point that Julia from our panelists was asking. And then we have a question from Alberto Longini. So in the assisted dressing scenario, have you thought about how different properties of clothes, such as different degrees of elasticity of the fabrics, can influence the forces perceived by the human?
Absolutely. So we haven't actually done a full investigation of how much cloth parameters impact the forces. There is clearly, it will impact forces, right? If you have like spandex, something that stretches a lot, versus like leather, which has very little stretch, you would expect there to be a noticeable difference in the amount of force applied, particularly once the cloth becomes taut, which at the point at which it no longer stretches easily, right? So certain types of cloth will stretch much more easily than other types, and hence the forces applied will be significantly different. So we haven't, though, this is a good point for, I would say, future research, is actually investigating how those types of cloth materials actually impact forces. It's not something that has been done yet.
Okay, nice, thanks. And then we have Christian Kaufman. I'm sorry for the pronunciation. And so thank you very much, Zachary, for your talk. And he's asking, I was wondering if you also consider to implement and integrate sensor simulation models in your framework, such as proximity sensors, to further close the sim-to-real gap.
Oh, yes, I very much like this. So this actually has, I have some other research which is kind of touching on this. I didn't present it all in this talk. One approach to look at specifically a proximity sensor is capacitive sensing, in which it emits an electric field. So if you have capacitive sensors on the robot, those sensors will emit an electric field, and anything that conducts electricity will be able to be sensed by that. The human body is an aspect, is definitely an object or material that conducts electricity well. So by using capacitive sensors, you can use them as a type of proximity sensor around the human body. And so I have work on that direction. And I myself have not been simulating that, but one of my colleagues has been looking. Alex Clegg has been looking at simulating capacitive sensors in simulation as generic proximity sensors. However, that loop has also not been closed yet. So although we have begun investigating these types of proximity sensors in simulation, the loop hasn't been closed in terms of evaluating whether those proximity sensors do work with real robots, right? In terms of the difference, the gap between the simulated sensor and the real capacitive sensors. There is still a gap there, and we haven't fully closed that yet. So that's a really good point. So beyond that, there are a number of different types of sensors that can be simulated. Some are usually readily available in physics simulators, things like cameras, RGB, and depth cameras. Other types of cameras, though, are a little bit more unique, and I haven't seen many implementations of them, things like thermal cameras. And so I would say this is actually very much still an active research area in terms of how to simulate different types of sensors in simulation, especially physics simulation. A few of them, force and torque sensors, have been implemented, cameras have been implemented, but beyond that, there's, and other things, torque, kind of actuator sensors, encoders and such, those have obviously been implemented in simulation, but there's a lot of other sensors that, especially haptic sensors, that are still very much open research field to look at in physics simulation.
Okay, nice, thanks. We have the last question, and it's Joanna Mizzoni. She says, thank you for the talk. It was a very well-rounded approach to physical human-robot interaction. And in the case of real-world executions of the assisting tasks, how do you think the active or passive compliance of the robot will affect the underlying estimation and optimization?
Oh, this is a good one. So I haven't actually put much thought into this. There is, and it might be slightly biased because of the robot that I'm working with. So I am working, at least historically, I've been working with a PR2 robot. Which I have done some other work with a few other robots, including the Sawyer and Jaco, but predominantly the PR2. And there is a good amount of compliance to that. So I suspect some approaches that some of this research has kind of that built-in notion that there is some compliance, right? The PR2 is a very, it does have compliance in its motors, its actuators are back drivable and such. So I would suspect that comes into play a little bit, especially and I think realistically, when robots are interacting with people in a close physical nature or physical interaction, it is probably important to have robots that have this level of compliance, right? So they're a little bit kind of inherently safe from a mechanical perspective. So I suspect actually that kind of compliance is actually a very good thing. How it impacts the control, though, is definitely a big question, which I haven't fully investigated yet. And it would probably require looking at both robots that have less compliance compared to robots that have more compliance in the real world, right? So sadly, I would say this is an interesting research idea, but I haven't investigated this yet. But this is very interesting.
Okay, nice, Zachary. Thanks a lot for being here. And good luck with your workshop.
Awesome, thank you. I'll be sticking around here a little bit more just to see some other talks.
Okay, perfect. Okay, nice.
We're gonna move then on with the next talk. Let me introduce the speaker. It's our own Julia Boras. She's a tenured researcher at the Spanish Scientific Research Council. She obtained a European PhD degree in 2011 at the Institute Robotica y Informatica Industrial. After she worked abroad for 6 years as a postdoc, 2 years at Yale University and 4 years at KIT in Karlsruhe. In 2018, she was awarded Ramon Llewellyn Scholarship, on my pronunciation today, one of the most prestigious senior postdoctoral scholarships in Spain. Her research interests include parallel robots, whole body motion, analysis, humanoid robot locomotion, grasping, dexterous manipulation, and robotic glove manipulation. I myself was fortunate enough to have a collaboration with her 2019 and can only say positive things. So Julia, take it away.
Thank you for this awesome introduction. Let me put the timer so that I can control the time. So I'm going to talk about analyzing and representing. Can you hear me and see everything?
Yes, it's fine.
Okay. And analyzing and representing cloth manipulation tasks. So the first thing that we can realize when it comes to cloth-like objects is that when we manipulate them, the first thing we do is grasping them. All the grasps are intrinsically non-prehensile, not only because we do platform grasps as normally, but also because not all the object is grasped. So we don't put all the object inside the hand. Also, most of the tasks are by manual. And we also have different friction requirements because a lot of times when we humans manipulate cloth, we sometimes slide over edges, for instance. So that means that sometimes we need to firmly grasp and sometimes we need to be able to actually slide on the cloth. From a robotic point of view, that means that we need to change probably the friction of the fingertips. And of course, then the elephant in the room is like the high deformability, which implies a very high dimensional configuration space, which means that it's difficult to estimate the configuration of the cloth, but also that both the hand and the environment, they will conform shape to this object, which is very relevant in the moment of when we are manipulating it. So that the environmental constraints are essential, and we actually use it when we fold, as we see in this picture. We use the table to support our manipulation and to be able to accomplish the task. So in a manipulation task, normally there is like this different process in parallel where we have a decision-making tool that is going to decide what is the action that we execute. Then we have these planners that decide the trajectory and controllers so that we are able to execute this action. And then at some point to monitor it and to recognize where we landed, we need to identify the state so that the decision making can keep deciding on things. This is normally the execution loop, and what we see is that with cloth manipulation, one of the main open challenging is this state recognition and how we define it, which is basically the focus of this workshop. So state of the art has focused mainly on representing and grasp cloth state. It's difficult enough, of course. So for these are, for example, 3 examples of the main different configurations, which is completely crumpled, flat on the table, or folded. So what we propose and what we are working on is adding to this state definition on information about grasping and what is the grasping state of the cloth, and also information about the environmental contact. So basically for us, this is all part of the grasping. So we are going to assume that the environment is also grasping the cloth. So that means that if we can represent a finite number of states and we arrange them as a graph, that's what we are trying to do, that we think that this can simplify both the state recognition, because we are going to simplify the number of states that we need to identify, but also it can be as itself easily interpretable as a decision-making tool, but also we can store parameters for execution. For instance, the location of the vertices or the grasping or the interesting grasping points or the edges, etc. And in addition, what we want is to be able to learn that from human demonstrations, which right now this is an open question because it's difficult to get data from real cloth manipulations in general. So in this context, our initial proposal is this novel representation of a task as a graph of transitions between scene states, and each one of these scene states are different moments of interaction between the cloth and the grasp and the grippers. So different moments, where is it grasp the cloth, how is it grasped, and we have basically just semantic labels describing the cloth, if it's crumpled versus if it's flat or if it's folded. And then we are able actually to learn that from human demonstrations. And we have called this the cohesion graph because it gives like a coherent overall view of the task. This is an ongoing work that we are actually still developing. So if we pay closer attention to one of these stage definitions, here we see that there are 3 levels of information. The first one is on grasp type, then the grasp location and the cloth configuration stage, which I'm going to enter later. So the first thing that we did when we started this work is focusing on grasp type, which normally nobody has really done in the past, as we will see now. And this is a work that we published in Transactions on Robotics on a grasping-centered analysis for cloth manipulation. So the first thing that we realized when we started working on cloth type for cloth is that while normally now there is all these novel soft grippers that they adapt to the shape of the object, what happened in our case is that is the cloth that is completely shapeless and adapts to the shape of the hand. So that means that we cannot really use the classic grasping type definition that mainly depends on the object shape. We don't have shape. So for cloth, we thought is that this grasp type must depend on the shape of the hand, because this is the shape that is going to be given to the cloth. So then we look actually in the bibliography. Here we see several executions of robotics cloth manipulations, and we can quickly realize that they all use the pinch grasp, which of course things are complicated enough, and already with the pinch grasp, these are not the focuses of these works. But then if we review also the grippers that have been used to manipulate cloth, we quickly realize also that most of them, they rely on pinch grasp, at the most in pinch combinations. But we see some interesting already manipulations with grippers against surfaces, for instance, for flattening. So that's already something interesting there. And also there are very few objects where they consider other geometries of fingertips. So for instance, here we see like some linear fingertips that they conform more shape to the object. So what we proposed in this transactions on robotics paper is to define grass type for cloth for textiles using prehension geometries. That's very basic. So we focus first on points and lines and planes, which we notate that as a P, L, or pi. And also we consider this extrinsic dexterity following this in this paper from Ann Mason, where we consider that external contacts are also grasping elements. That means that this point, line, and plane can also be geometries from the environment. Then we put this subtitle, the E, which means the extrinsic, and then we just combine geometry. What did I do now? Oh, okay. We just combine the geometry. So for the pinch grass, that would be a double point grass. For pinch grass is a double PP, a PP grass. But then if we cannot combine a lot of them, actually we have a lot of combinations. So only with that, we can see that we can abstract from the human hand. So we can actually analyze human grass by defining what is the geometry that they are conforming to the cloth, but also we can define generic, for generic grippers, what are the grass that use. For instance, we are able to describe what are the grass types that all these robots are using. So for instance, in this last one, that maybe is the most complex one, where on one side is using a point against the table, and then a line, they have like a brush that to flatten the cloth. So from this definition of a state that we talked before, we already have defined what is this notation that I had before here, that they had this PP plus a pi E, which is the planar contact of the table. What we did is we analyzed the literature and about robotic demonstrations with clothes, and we saw quite already a variety of the grass types that have been used. But when we check the numbers, you realize that it's basically all these red ones. It's basically mostly focused on the pinch grass, or the PP grass. In addition, this definition allows us to also classify types of manipulations, depending if they are sliding or if they are with the fixed grass, but then you move the cloth. As I said before, the cloth is not fully inside the hand, so you can move the hands and manipulate the cloth, which is basically what we do when we fold, for instance, but also adding and removing restricting contacts, etc. So first of all, it's really important, this grass type, because if everybody is using the pinch grass, maybe it's because it doesn't really matter. So what the first thing we did is try to see how grass type can influence on the manipulation of cloth. And what we did is we used 3 different grippers with different geometries. This first one is a double line, then this other is between a line and a plane, and this last one is the double point. And what we did is we manipulated with a pre-grass cloth. It was the human, the subject that was using the grippers. And we performed, for instance, the task of folding a t-shirt in the air. And we also were wearing this Xsense suit that was able to collect the motion data of the hands. And you can already see that, for instance, doing this task with only a pinch is quite complicated. So what we can do now is compare the trajectories, which depending on how is the alignment and the rotation point, you see larger or smaller trajectories. But what is more interesting is the acceleration and the velocities. When we compare the velocities, we can clearly see that when using only the pinch, you need to really do a very fast motion to give enough impulse to the cloth so that you can actually fold it in the air. So that basically means that, yes, it's true that the type of grasp can influence the dynamics of the task. And if you choose the correct geometry, basically you can get a much simplified task dynamics. And this is, of course, this is a highly dynamic task, the folding in the air, but we got similar results, as I will show soon, with other tasks that are much simpler. So if we look at these 3 tasks, we selected these 3 tasks: pick and place, folded clothes, folding a t-shirt in the air, and trace cloth. We observe humans performing this task. This has done in the literature, has been done with only pinch grasps. But we can clearly see that we as humans, when we manipulate, we use a lot more of support under the cloth so that it doesn't get unfolded. And this is highly also dependent on the type of cloth. Also, for folding a t-shirt in the air, this has also been done in the literature mostly with a pinch grasp. this work that is also from Adrià Colomé and Carme Torres from our institute also started with a pinch grass, but they quickly realized that this was a reinforcement learning work where the robot was learning to perform this motion of folding in the air, and they quickly also realized that if we're putting more geometry on the gripper, the task could be learned better and faster. So giving, for instance, linear geometries in this aspect would help also the dynamic of the task. And finally, the last one is tracing the cloth edge, which is of course is done with a pinch grasp, but is a pinch that has different requirements because the one that is holding the cloth needs to have a very high friction, while the one that is light needs to have very low friction in it in order to be able to actually slide along the cloth. So based on these observations, we designed a gripper able to perform a variety of grasp. For instance, these pinch ones, but also like providing a support with a plane. That's why it can open the bottom fingers. And also it can provide like a planar surface against the table to perform the double plane one. And so we are still working on developing a novel version of this gripper. And one of the things that we did in the same idea that we saw before is comparing grasp type and the influence on manipulation. So we did a subject study where the subject was instructed to do the task as well as they could. We humans can do anything with anything. So we give just like chopsticks and we can do also folding of clothes. But the idea is that it's more difficult. So with the fingers open, we could do this unpiling and piling of folded clothes. And we did the same with the fingers closed. And especially in the moment of placing, we could observe again, this similar than before, that the acceleration that you need to provide in order to actually place the cloth well is much higher when you don't have this support under. So far what we did is, what I explained so far is about grasping. So we can now describe the manipulations that appeared in the literature as a succession of grasp types. So for instance, this is the usual one where we regrasp the cloth and then we use vision to localize these grasping corners. In this other one, they use actually the extrinsic contact with the table. So they grasp the cloth and then they add the table contact and they slide it on top of it so that they can identify novel grasping points. And then they grasp it again, they remove the tablecloth and they iterate on that. And this other type is the sliding on the edge where you have a pinch grasp and then you just slide to find the pin. This is clearly not enough. So what we are working now is to adding also location of this grasping. So what we did, we defined a set of coordinates on the table that are subject dependent because these labels of left corner and left corner depends on the perspective of the human, of course. And for instance, this one is represented in this corner here, meaning that the grasp is basically, the cloth is grasping one corner. And then we also have a very basic definition, a semantic definition of the state of the cloth. If it's folded, if it's flat, crumpled, or partially folded, that means that the folded is not finished, or semi-flat, that it needs flattening. And we also have a semantic label to identify the transition between the origin state and the destination state. And here we see an example of how we do this labeling, which right now is actually still manual. We have done this labeling manual, and we are working now on trying to do that in an autonomous way or partially autonomous way. And so what we do here is every change of interaction between grasping or cloth state, we annotate it as a single option, but then we observe that for several humans. And here we see 4 of our subjects performing exactly the same task, and they do it completely different number of steps, different number of it's like 4 completely different ways to achieve exactly the same task, which is folding in 3 folds, which is what it was instructed to the subject. We did it with different tasks. This is putting the tablecloth, and again, these are 4 subjects, and it's a completely 4 different types of performing the same task. So with the grasp, with this coherent grasp, we are able to capture all these different variability and of strategies that we can get to accomplish this task. So we are working on this graph for several applications. And one of the applications that we are considering in the context of the work program, which this is a Chistera EU project that we have, is benchmark for understanding grasping. One of the things that we can clearly see in this graph is the segmentation of a task. We can identify this is the beginning, we are grasping the first point, this is the grasping of the second point, then we put it flat, then this is the first fold, this lower one is the second fold, and then we can identify the third fold, which is basically the final fold. This is interesting because this is relevant in the moment of evaluating manipulations. And for instance, in our initial work that we did on benchmarking with KTH in collaboration, we could already find 3 tasks for cloth manipulations where we could clearly distinguish this grasping of the first point, then grasping of the second point, and then performing the actual task. And this is actually not easy ways of doing it. For the grasping the first point or grasping the second point, it might require additional manipulations that are not expected. So this is the first idea, but then we kept working on that. For instance, grasping for cloth, this is true also always, like also for rigid objects, but it's really linked to function. So for instance, in this case, we see that it's not the same if we have to grasp the same cloth, but if it's for unfolding, or if you need to pick up the cloth to place it somewhere else. And even if you need to place it, is this grasp good for placing? Because depending on what is the cloth, maybe it wrinkles too much that you are completely unable to then place it again flat on any surface. So we think that grasping cloth is actually easy if you don't care about the function, because you can just put any gripper there and the cloth is very soft and you're gonna grasp it. But then maybe you cannot do anything with it. Also, the graph allows us to this definition of the task in steps, and now we are working on studying how errors in evaluation and success rates can spread through the graph. So maybe just the first edge of a manipulation, you can do it with some error, but maybe then this error is not relevant for the rest of the task. If it's not relevant, or if it can get corrected, then it's relevant to know if it has any value to actually evaluate this independently. So that's a very neat example of that is the task of edge tracing, which normally the normal process of that would be like you have the cloth grasp in 2 points, then you slide over the edge. When you reach the corner, you put the cloth flat and then you place it flat on the table. When you actually learn the grasp from humans, there is more variations to that. There is a lot more of variations to that, and one of the things that we see, this is actually a symmetrical graph on the left and on the right, so you can also only look at one of the sides, for instance. So here, what we see that when we trace an edge, one of the evaluations that you would quickly think of is like how well you can reach the corner. So how close can you get to that corner? But then when we observe humans doing it, we realize that not always the corner was reached and the task was still able to be performed correctly. So what we did is to actually evaluate one of these single edge of placing the flat on the table, but assuming different errors from the previous edge of the graph. And then what we did is like this is the video of the task of placing flat on the table when the cloth is correctly grasped. And then we define a continuous measure of success. We think that it's important also to have these continuous measures, because only success or failure, it might not be enough to actually see enough insights. And we can compute like a percentage of error, and we also did some performance of error depending on the area of the cloth. Then the idea, like here, some results is that depending, of course, this depends a lot on the type of cloth. So for instance, we tried with 3 different types of clothes. This would be the big tower, which is the one you saw in the video. And well, it seems that yes, it's true. You don't need to reach, you can get up to 12% far away from the corner, and 12% being of the total edge length. And once you start getting farther, you can get to 25% here and you're still fine. But then after that, you start seeing a lot of errors. So it's true. This is important when we evaluate edge tracing to take in consideration that maybe it's not really that relevant to be able to reach exactly the corner. As opposite, when we try to evaluate a full task, here is the task of putting a tablecloth. In the benchmark paper, we propose the option for the authors to actually report only the partial task, so the first grasping, the second grasping, the placing of the table. But then if you actually want to evaluate the whole task, you need to provide a measure of task quality of the whole task. And of course, this is highly dependent on task. This will always be like that. So what we propose here is to check how well the tablecloth was located against the table. Like if it was rotated or if it was more longer in one side and on the other, that's basically what you do when you put a tablecloth. And of course, that means that if a system of robots can place the tablecloth very, very badly, so hanging a lot from one side, but then the system is able to relocate the cloth and put it correctly, it has to have the same success ratio, the same success measure than another that does it maybe in a single manipulation. So that's what we've been working so far. But of course, this is an ongoing project, which means that we are actually using this graph and working in parallel in a lot of different projects. For instance, in recognizing of these scene states, as I said, once you define the grasp and the contact with the environment, the configuration of the cloth is simplifying because there are not that many ways, especially when you are doing a specific task. So now we are working on a deep learning system to train, to recognize these different grasping states and interaction with environment states. We are also working on cloth state estimation because in addition of this very basic recognition of flat or crumpled cloth state, we need to also have some parameters able to so that we can go to grasp, for instance, to localize cloth corners. And also we are using some topological measures on the edge of the cloth. We are also using this graph as a framework to provide explainability to a system. In a robotic manipulation, we have several artificial intelligence processes that work in parallel. And then we are going to use this graph as a common framework to provide a coherent explanation. This is the Coherent project that just started. It's like a month ago. And so this project really, I cannot really show anything yet. We are also working in this benchmarking of cloth manipulations, including also benchmarking and measuring of these grippers that we have. Now we put them on the robots and we're going to measure the same that we measured, but with the robot. Because of course, when you have the human in the loop, maybe the human is actually solving a lot of the things that we see. And we are also working on development of skills like edge tracing based on force feedback. As we've seen, like the force feedback, we think is very important, not only rely on vision, but also to be able to feel the cloth and understand what is going on also from force feedback. So that's our group. In parentheses, we have the women. We need more women in robotics in general. And this is our lab and our robots. We are working with Jaguar robots. And that's all. We're doing perception of rigid and non-rigid objects, planning for perception and manipulation, and also learning from demonstration and reinforcement learning, in addition of what I've been talking today. So that's all. I don't hear anyone. Okay. Like, maybe I was alone all this time.
No, thank you for the really great talk. I actually have questions about these coherent graphs. Like, are they object specific, like one graph for the napkin, and then if you would do one for the shirt, is it a new graph, or can it be integrated into one bigger one?
It could be integrated, but of course there is particularities of every object that make it different. So basically what would happen is that you would have an even sparser graph, that you would have more options for grasping from the first graph to the first grasp to the second one. You will have a lot more possibilities how to do it, that maybe they are depending on the object. And you see, it depends on how you simplify. At the end, you need to decide what you want to simplify. And so we actually worked on bridging, like having all the tasks that we have in a single grasp. So then we don't care about what's the object. But then it's more difficult to understand maybe other things.
Thanks.
And I also have a question about the graph. And actually, I was wondering if this kind of graph is completely comprehensive, or if you consider that you may also fall in a state that is not in the graph. So when you're interacting with deformable objects, it's kind of tough to already know all the possible states of the graph.
No, definitely, that's true. The good thing about learning from humans is that there is already a lot more happening than what the robot can do. But definitely one of the things that we have as an open question for the future is the ability to learn new states when we are able to actually execute, because we are still not at the edge of executing with this graph, so that with this graph on the robot, because we are still learning to recognize these states. And once we can do that, then if we don't find any match with the states that we already know, we can actually think about learning new ones online.
Okay, thanks.
Hi, Julia. I have a quick question. So your taxonomy, have you considered how the human hand fits into the taxonomy, where you might have like 5 pp, right?
No, actually, well, it's one of the things I still want to do with a data glove, like try to see how we can transfer. But my idea is to actually simplify in the same way that the virtual fingers nomenclature. This actually was done with this overall idea of these papers from the 80s that define the virtual fingers and the opposition forces. And if the fingers are making force in the same direction, they are considered one single virtual finger. So my idea is that if you are doing this would be a planar or a line. They would not be considered 5 points. And if you are doing a pinch, this is also going to be considered like a pinch, like a 2 points, not 3 points, unless you are actually doing it. But again, because you don't have shape of the object, that will never happen. Like when you have a round object, it can happen that you are actually doing 3 forces in 3 different directions. But when there is no shape, like it's like the object collapses to nothing. And then like, but it's still like, it's one of the things that I still want to do, like to map these geometries to the human hand. You can do it like yourself, like thinking about, but yes, I still haven't really collected data. And I'm not sure it's just with a data glove, it's gonna be, without actually considering contact. Because then you need to estimate the contacts, like with it from the data glove.
I agree. Thank you.
Michael?
All right, I think we don't have any more questions for Julia, so we will move on to the next point in the schedule, which is the open discussion round. So I mean, I think Zachary, you need to run soon, but I mean, if you still have some minutes, you could stick around for the beginning of it, give some input.
Sure.
Yeah, I mean, I might have to leave like halfway through, so I'd feel bad if panelist has to leave halfway through.
That's all right. Yes, so let's start then with how the open discussion round will go. We will propose some questions to the panelists, and they will be discussed. And I encourage the audience to take over in the Slido to vote and ask more questions. For this discussion round, we have David, Jiang, Guillaume, and Julia. And I don't think Yanis is here. And Martina and me will be
it's here.
moderator.
Yanis is here. I just didn't recognize the name.
Aha. Yeah, it's
Hi, Yanis.
Hey, Yanis. Good to have you.
Yes, it's here. Yeah. Nice to see you. Yeah.
Okay, perfect. And we're gonna kick it off with the first question, and it's basically some recent works deal with simple deformable object and scalability of these approaches. are we ready to deal with real-world deformable objects like the ones we have seen now in Zachary's talk with real gowns or T-shirts, or are we still in the phase of where we mostly deal with cables, ropes, and other more simpler objects? What is the possible gap between these current approaches and stuff that we need to employ it into the real world?
Hello, if you let me start, as I have not talked yet, I'm fresh.
Thanks.
So I think that we are definitely ready for tackling these more complex objects, because one thing that we have discovered while trying to deal with the whole complexity of the thing is that we don't really need a precise modelization of everything, just the small parts that are useful for doing the task, actually, for example, recognizing corners or dealing with where some particular parts are, like, I don't know, the colors, for example, something like this. So we are not anymore trying to deal with the complete set of features, like when you try to grasp a Mac, for example, that you try to figure out exactly where the complete shape is and where the handle is and everything. I think that the current trend is to start to think that we don't need all this complexity. We don't need a mesh modeling everything. We just need to deal with the important things. Or what we need is like an approximator of everything, like Zachary has shown us when just trying to figure out from the point of view of the forces that are changing between the contact forces between the gown and the arm, for example. There was not really, so the simulation had this model, but then the real execution does not need that model, okay, anymore. So short answer is yes.
Okay, thanks, Guillem. And what do you other speakers think?
I was going to talk, but I'm from the same group than Guillem, so I'm in this trend of thought too, even though Guillem has been very fast at saying, yes, we can do everything. And that's not true even for rigid objects. At the end, there is a lot of variability and uncertainty.
He has been very optimistic. I mean, I also wish to say yes, of course, but there are many things that needs to be taken into account. But I understand the point of this answer. I mean that sometimes you focus a lot on the detail, like modeling stuff very precisely, but we don't really need these models because I mean the task itself is guiding you without paying that much attention to the detail. So there is always some latent space that things belong that helps you make something rather than model pretty much everything.
Now I'm going to contradict myself, but that's fine. That's science.
Yeah, of course. This is the time.
Because it's true that we are able to model particular parts, and with that, allegedly, we are able to do a lot of things. But we have seen, for example, trying to put flat on the table some clothing, and imagine there is some wrinkles there, and then there is a lot of current research trying to unwrinkle, to flatten this with kind of different motions, either using the models or either using some learned sensory motor actions with deep learning or something like this. And at this point, maybe we need to extend this idea of I need just small parts of the deformable to I need basically a clear idea on how the deformable is. Okay, so contradicting myself, at some point we need some more fine-grained models to do something, maybe. Or you have seen that we are trying to put on the table this, not put flat on the table, this strategy of moving using the external constraint. Here, what happens if there is a small error and they have a small wrinkle here and there? Then basically you need to recognize everything and be able to unfold this. And again, we have to look at the deformable as a whole, not this small detail.
Yeah, but again, we have to understand what it needs to be done. And at the end, for the manipulation, probably you just need to know where the corners are so that you can move them. So it's more, at the end, going back to the rigid objects literature, like affordances. We need to understand what is the affordance, giving a particular state that you don't need to understand exactly how the wrinkle is, just that there is a wrinkle there. And that needs to be flattened or not, depending on what is the task that you are doing. So maybe you don't need to.
So again, contradicting myself in the second time, so coming again to my first argument, you don't need an exact model of everything, just a rough idea on what's going on here and there to be able to do things, yeah?
I guess the question is the degree of the granularity of this rough idea.
It depends a bit on the task, I think. I think that not all the tasks require the same amount of like information and the same level of modeling, I suppose.
Exactly. So I think task is really a very important thing when we are dealing with this manipulation of the formables, because basically the task is shaping the kind of everything that we need.
So David, you have been a fan of PCA, right? As representation. So, but then when Guillaume said if you have a representation like you need the flattening, you would need this finer grained representation. Like then how would you approach this with your models if the task would be flattening a piece of cloth?
Well, sorry, there was. Are these questions posted somewhere? There was one about, I mean, the very first one about, are we ready to, I don't see it written. The question was, are we ready to move into more realistic type of manipulation task, right? I don't know if we're still discussing that one.
Yeah, somehow.
Yeah, somehow. or
yeah, it's a follow-up, I think, on this.
A follow-up.
Yeah.
Well, it's yes. Julia mentioned it's a difficult problem. I mean, in a grant application where we can mention many things that can be solved, but the reality is that really having consumable robotic systems doing these things for us, I think is still a bit not yet there. I mean, if in my defense, if I may, of the very simplistic objects, I mean, it's not that that's all the robot or the algorithm can do. I will say is that we select a type of test bed to evaluate something, you know, whether it's a very well structured cloth or a cable or I don't know something. By using those, we can prove, you know, specific issues. So I mean, I don't know, my comment will be that I do see still a bit difficult to really do, as I don't know, I guess the people who fund all this work, they would like to see in real applications. So that's why we are studying this from a very fundamental perspective. That would be my comments.
Thanks, David. And I was wondering also about Xiang's opinion, because actually the work that you presented is mostly about these linear deformable objects that are, of course, extremely important. But still here, what do you think about the scalability of these approaches? So of course, this must be a starting point. So we need to start working with more simple shapes, but then do you think is the gap to more complex shapes? And if these kind of approaches are actually ready for these, for real world objects?
Thanks for inviting me. Actually, I'm thinking if we are talking about something we want to make the system work, in my experience, actually maybe some specific design in hardware in some specific tasks will work better than maybe the general formulation. So in our project, we are doing something about the deformable linear object. Actually, in particular, we are doing something about the USB soldering system. So actually, by the end, we developed some hardware system. It's a mechanism. It's not just a programming or control theory. We find that if we use the maybe specific design or module to realize the USB soldering task, we can have a higher successful rate. And another example is actually, maybe we're talking about the cross manipulation. I guess, yes, we can push the robot to do some cross manipulation, maybe in publication in papers, a bit progress. But if we really push the robot to the factory to do the cross manipulation, I guess, just my guess, maybe some specific design which we can control the cost in some maybe some steps will work better than the general formulation. And also, I guess this is a big gap between the real world and the general formulation, because we have a lot to do. If we want to totally mimic the way how the human hand to manipulate something, we still have a long way to do with the data and how we improve maybe the sensor and the motors. That's my comment. Yeah. Thanks.
Yes, thanks. That's very true. And I see there is also a question from the audience. So Benjamin Holt is saying, currently there are a lot of very different methodologies developed for different sub-problems, object types, manipulation tasks, and etc. Do you think that there will be a convergence in the near future toward one particular family of algorithms, like we see in image processing, where we have CNNs, or natural language processing with transformer-based architectures? And if so, which family of methodologies currently is the strongest candidate for such a convergence?
Wow.
So that's...
I think that's a very big and difficult question, because people from image processing, they have a, let's call it, easier scenario, not an easy problem, but at least an easier scenario, because they don't need embodiment. So they can deal with image databases, for example, and that's fair enough. Whereas we have to deal not only with the real deformable, but also with the real embodiment of the robot, the capabilities of each hand, of each arm. And we have not agreed in the community which are the interesting tasks, in the sense if, I don't know, folding is what we want to make research on, or unfolding, or dressing, or helping in everyday deformable manipulations, like putting a tablecloth or making beds, or I don't know, there's an infinity of tasks. So I don't think that in a close time we are able to agree on which kind of tasks and embodiments and capabilities are the ones that we want to agree. So in this common technique. And of course, that deep learning techniques are going to get into these, and we have seen already that for a lot of grasping, they are there already. And a lot of grasping control is now driven by deep learning methods. But I'm not sure that this is going to win, because there is a long history and
they also have the problem of ground truth, no? Also for grasping. They need to simulate a grasp, and it's not easy to simulate even for rigid objects. So yeah, that is basically the problem we have in general for robotics, and for soft manipulation is even more true, is the ground truth. We don't have.
So Julia has presented already that we have a project that is devoted to benchmarking.
Yes.
So we are thinking on that, but I'm not really confident that at the end of the project we can come with the solution for the community. We can just enlighten a little bit, because the task is really, really, really difficult. And I don't know, for example, that we want to provide a robot with dexterity of a human when manipulating textiles. I don't think that this is maybe the objective. Julia has already shown in her presentation that basically the research in textile manipulation has been done with a parallel gripper. And this has been enough for a lot of things. So I don't know why we would like to complicate all the effectors to have a lot of more complicated graspings. If basically with a pinch grasp we can do almost everything, and then if we can extend this pinch grasp to a manual pinch grasp or a point line, for example, grasp or plane, and basically this is a small set of kind of grasps. So yeah, that's my opinion. My opinion is that no, in this case. Short answer is no.
Okay.
Yeah. I also find it quite difficult because I think that, let's say, first of all, is the variation in terms of tasks. I mean, in robotics, the type of tasks are the same number of tasks that the human can do. For example, you can have from folding, you can have cutting, you can have assembly with deformable objects, you can have grasping with deformable objects. I mean, the variability of tasks is so high. So it's quite difficult to have a consensus on methods. I mean, even if we start discussing, let's say, if we choose between data-driven and more physics-based approaches, then we may have different opinions about this. And even in this case, I think that we should think of the task and we should think of the models in order to choose what method suits us. So it's a bit difficult, I think, to find the consensus and, like some key that can open all the doors, particularly when it comes to deformable objects and the tasks that are related to deformable objects.
Yeah, but at least in the vision community, they agreed on some basic tasks like recognition, for example. No, let's find out dogs on images.
Yes, but this is just a task. I mean, that should we found a task? I mean, that there are so many, we cannot choose. This is just a specific problem and all the papers deal with this problem. But should we deal with, for example, with folding or there are different semantics as well behind this task. And also, as you said, that the embodiment is very, very different. So you may have just a pinch grasp or you may have more complicated type of grasp with human-like hands.
Different sensors.
Different sensors. I mean, you have people that working with haptics, you have people working with cameras, you have people that you work with simulation, for example.
Yeah, but
and then, of course, they need to generalize. Yeah.
Yeah, maybe it would be a first step towards this, just to try to agree on a one or two tasks that we can all work on these and then try to compare one against another, benchmarking basically.
Yes, I think that there are many works in benchmarking, right? I mean, that there was like also this RAL issue that has like several stuff of benchmarking.
We could say there are as many benchmark works as tasks.
Yes. Yeah, exactly.
Yeah, but so look, the vision community could agree on a simple task at the beginning that was recognizing dogs on images. And then they started to make things a bit more complicated once this was already there. And we are doing the inverse. We are saying, no, we are not dealing with these common problems. We are doing, and everyone is dealing with a different problem. So now the comparison.
Because they have ground truth, they have databases that they could work against. That's easier. If you provide some sort of, imagine we could collect, it's not doable, but like collect the experience from the robot, and then you can just use like a simulated robot. The problem is that the problem is the simulation, that you cannot simulate well.
Yeah.
Okay. Then we need Zachary.
Is here like
Zachary is just like
yeah.
We need him to provide us with a nice simulation of these deformable things. Yeah.
Yeah. I mean, that simulation is indeed a very difficult problem. We have recently published a quite simple simulator again, but it's for deformable objects. It's reformed. It will be presented in ICRA 2021. But I will return back to the task thing and the task selection, because I mean, when we started working with the mainly deformable objects application, we make like a categorization in terms of task. And then we have something that we call explicit safe control. That I mean that you have a configuration and you want to bring it in a specific desired position, which is like more a toy problem. But then you may have, or this is implicit, so, right? You may have explicit safe control. And this explicit safe control can describe pretty much everything. Can it goes to assembly? Can it goes to folding? So it's very high variability, and I think that it's very difficult to impose directions to people when start working. Yeah.
Yeah, that's true. But do you think that in the future should we be more oriented towards learning-based techniques, or should we go back to control-based techniques? Because nowadays what we can see is that basically we are moving towards applying the learning almost everywhere. But is it also true for the deformable objects, and where should we apply, or should we still apply some control theory methodologies, and when we should not? So also, for example, from David's talk, we saw some great application of control theory in an effective way also for deformable objects. So when should we use control theory, and when should we use learning in these kind of settings?
Can we use both?
Yeah.
Yes, and how could we combine them then?
I mean, you can learn a trajectory and then use a controller to actually execute it in a soft way so that it doesn't crash against things, or it does in a soft way. I can let talk the expert on control. So.
Yeah. So can I take it, or someone else will start? Yeah, no one is, so I can. Yeah, I can start with this. Yes, I think that the most important thing is first of all to I mean, there is no a yes or no answer. I mean, to those stuff, either with one or the other one. And I think, as you said, that we see these nice examples from David in the morning. But what's happening nowadays is that people, without trying the simple stuff, they go directly to the complicated, the more complex stuff. However, it should be done, I think, in a different way. So first you start with the simple stuff, you see if this is working, and then if this has some problems, then you go and then you can leverage something that it is something that is more efficient. And I would say, I mean, that if you have simple models, then maybe it's better if you start with a more physics-based and more analytic-based approaches. But if you start, the complexity start increasing, and then you have more complicated models. And when I say complicated models, I mean contact-rich models, models that are switching between different contact states, or, for example, different phenomena that you may have. Let's say if you have elastoplastic models instead of just elastic models, that you have like hidden states in the model, then maybe it's good also to start investigating the data-driven approaches, because they can somehow help in identifying the models. And also a last point has to do with the probabilistic nature of the problems. I mean that if you have problems that are deterministic, like analytic-based approaches are something like I mean, they are the same thing. But if probabilities are involved, then you need to, you know, start to learn the probability distribution, particularly when you have multimodalities, I would say. And I will stop speaking. So,
yes, so if I may say, well, something I may share is, I don't know, I find, I guess probably many of you also have a feeling that maybe recently there's how this question is posed as if it's a dichotomy between some presented as a very traditional, let's say, control theory and more modern looking data-driven learning approaches. So I mean, I'm probably a bit biased because my background is in control. And well, if I try to see it as a control problem, I don't think that one should either choose either of these two. Say, for example, in what is a learning-based algorithm doing? Is what in control one may call in a single unit, actually, like adapting a variable. So you have many adaptive variables doing the job that you will otherwise do with a single element. So whenever there's something that you can learn and incorporating in a control problem, I just see that as very, very welcome and needed. There are many tools now, libraries, just many students are very, very good at implementing these methods quite readily now. So I do hope seeing more merging of these two complementary areas. One cannot like entirely replace a problem that by definition, what you need to do is to control it. I mean, one may still need to able, even if you're using a completely data-driven approach, you're still controlling something, and you may still need to be able to draw some conclusions from it. So yeah, just my stance on this will be to combine whenever there is things that one can combine. Yeah.
Thanks, David. So do you think that some pure data-driven approach like reinforcement learning may be a solution, or may lead to some issues when dealing with deformable objects?
Depends for what you want this approach, I guess. So I think that let's say for this new trend of using data-driven approaches, the old trend, it was trying to do end-to-end. So you input an image, and then basically what you have is the complete set of robot skills that, I don't know, fold everything. This would be the classical new approach for this. And I think that now people discover that this is like overkilling, and the amount of data that you need to be able to react to unforeseen situations that are very common when manipulating deformable objects, it's very large. So I think that we are going to be using the data-driven approaches for solving, I don't know, control problems, for example, for solving small perception issues, for solving even robot execution, for doing, I don't know, small parts of the task. And we will rely on this classical engineering driven and artificial intelligence in order to be able to decide among different options, for taking into account all the complexity of the uncertainty of what we have, in order to be able to react to unforeseen situations, or to redo something that, because of the dynamics of the clothing, for example, has not been executed as expected, something like this. And I foresee that kind of this combination that I think that all we agree that it's needed between these two different worlds, it's going to happen in this at this level, more or less. I don't know if you agree, but I think that that's what's going to happen.
So actually, can I say something about this question? Because my presentation just cover this topic.
Yeah.
Yeah, I agree with the panel member that definitely we can combine the control theory with the data-driven method. But my opinion is that maybe the problem is that how we can combine effectively to combine advantage of these two ways. So actually, for my shape control of a deformable linear object, our specific solution to this question is that we have to design the transition between these two phases. So this is why we use the neural network to get the deformation model in the offline phase, But this is very maybe trivial, and the training does not take very long. And just good to aim to provide some good estimation for the online phase. But then the novelty for this shift control for the wise is that we have to build another adaptive neural network system. So the challenge is how we design the adaptive neural network system. We ensure that the way we train in maybe in the data-driven offline phase can be directly transferred to the online phase. So this is our solution for the specific task. So back to the question, my point is that definitely we can combine because the model-based can be provide a very good initial status or the training status for the data-driven method, and the data-driven method can definitely compensate the model uncertainties. But the problem is that how we combine it. Maybe it's case by case. Thanks.
Yes, nice. Thanks. We have another question. So it's from Adrian Kessler, and so the question is, many works are really focusing on certain types of objects like cables, cloth, or applications like surgery or service, thus missing other parts of the field. To propose scalable generic solutions to all deformable objects manipulation problem, it is important to list the problems first. So have such classifications like a taxonomy of deformable object manipulation already been proposed? So I think that a taxonomy, a comprehensive taxonomy does not exist yet, but of course it may be helpful to understand which basic methodologies we can apply for the different tasks. But of course, the speakers are much more expert than me, so please.
I think that there is a review that's summarizing at least the type of objects that are involved in such type of manipulations. For example, you may have the deformable linear objects, or you may have objects that have considerable mass, but I don't know if, and also specify different problems. But I think that the surveys, most of the times, they don't have in mind to define some new taxonomy, but they're just going to depict the current situation. So they are getting around, and they're getting papers, and then they're collecting and put them together. So I don't feel that there is some taxonomy in a way. As I said, that I have tried to make some small definition about explicit and implicit state control, but again, this is very, very generic. And I mean, if you want to categorize further the implicit or the explicit tasks when it comes to deformation control, then it's, I mean, there are many. Yeah, I don't know. Maybe there are some taxonomy in terms of tasks of deformable objects, but I'm not aware personally. I leave to the rest if anyone knows more about this.
Let's write a paper then.
Yeah.
Yes, why not? It's up to Michael and Martina. You coordinate that.
Okay.
So that at least we get something. It's late for us here in Asia.
Yeah. that would be a great outcome of the workshop.
Yes. We're not doing this for free, Martina. Come on.
Okay, good to know. No, but okay. Thanks a lot. And I think that if there are no other questions, we may close this discussion round. And thanks a lot for being here. Thanks a lot for your great talks and for this discussion round. And we will start again at 14, so in 1 hour. And that's it. Thanks a lot.
Bye. Thank you.
Bye.
Thank you for the great workshop. Thanks.
Thanks.
Bye.
Hello.
Hey.
How's it going? So should I get started or what should we do here?
I think we just wait another 3 to 4 minutes. It seems people are just coming now back from the lunch.
Okay.
But then we are ready to go.
Okay.
You can test your sharing function if you want.
Hey, hello.
Hello.
Yes, I can stop sharing so that you can try your slides. And then we may just wait a couple of minutes.
Okay.
Okay, perfect. Okay, let's just wait a couple of minutes. So we were a bit late for the morning session, so we had a quite short lunch break.
With all these time zones, it's difficult to
Yeah,
accommodate.
it's kind of early morning here, so. You know.
We are sorry.
No, it's only 10 a.m. so it's not super early.
Okay, okay.
Yeah.
In Sweden, it's just now 4 p.m. So we had the later lunch and.
If you want to test out any videos while you're waiting, that is also sometimes a good idea. If you have any videos in your presentation.
Yeah, I do have a bunch of videos. I did test them earlier, so I think that they're okay.
All right, good.
Okay, I think we may start. So people are coming. And I can start introducing Dimitri. So Dimitri Berenson is an associate professor in electrical engineering and computer science and robotics institute at the University of Michigan. And before coming to University of Michigan, he was an assistant professor at Worcester Polytechnic Institute. And he received his PhD degree from the Robotics Institute at Carnegie Mellon University in 2011, where he was supported by an Intel PhD fellowship. And afterwards, he was also a postdoc at the UC Berkeley, and he has received the IEEE RAS Early Career Award and the National Science Foundation Career Award. And his current research focuses on robotic manipulation, robot learning, and motion planning. So thanks, Dimitri, for being here. And the floor is yours. And I just want to remind people that if you want to ask questions, you can use the question and answers in the Zoom. You can use the Slido channel and also the YouTube chat, and we will be monitoring these channels. So thanks a lot.
Hey, thank you, Martina, and thank you to the organizers of the workshop for the invitation. I'm very excited to be here, and I love that these workshops are becoming more common because it means our field of deformable object manipulation is gaining some prominence. So I'm very excited about that. But that's not how it always was. You know, when I started working in this area, people would ask me, why are you working on this niche problem? You know, it's really hard. Why not just keep working with rigid objects like everybody else? And, you know, the easy answer to that question is to say, look at all these great applications, right? We have cloth manipulation for domestic tasks. We have food preparation, manufacturing, we have surgery. Clearly, this is an important problem. But to be totally honest, that's not why I work on this. It's great to put in a grant proposal that there's some great applications, but personally, that's not my motivation. My motivation is actually to start to challenge the assumptions that have guided robotics so far. Assumptions that have enabled so much great work in robotics have now become somewhat limiting. So what assumptions am I talking about? Well, things like everything is rigid, that we know all the dynamics of everything, that we have simple uncertainty distributions, that we're working with fully actuated systems, and so on. right? All of these have allowed us to make progress, but now we're seeing the limitations of them, and we have to start to relax these assumptions. And that's why I think that deformable object manipulation is what I call robotics complete, in the sense that people used to use the term AI complete. So if we are able to solve to a sufficient degree of performance, deformable object manipulation, we will also have solved some of the hardest perception, motion planning, control, and reasoning problems that there are in robotics, and our solution should be able to propagate out from our applications to many others. So, with that context in mind, what I'm going to be talking about today is focusing on modeling deformable objects, and specifically being aware of the limitations of models. So there are many models for deformable objects out there, many types of models. So mass spring, FEM, meshless models, and probably in the last year there's been 3 or 4 more models proposed that aren't on this slide. And these models are great. There are trade-offs between expressivity and computation and things like that. But the upshot that I want to convey here is that none of these models is perfect. There's no model that captures every possible behavior of a deformable object. They're specialized to certain regimes. Nevertheless, people have used these models in, for instance, motion planning work for many years now. And in this work, it's very interesting motion planning, but the way that the models are used is basically as totally trustworthy. Whatever the model predicts, we just believe it. We have a little call to a simulator inside of our planner loop, and whatever the simulator tells us is what we use, and we just trust that completely. I think that's really unrealistic for deformable object models. We also see some very interesting work in control, using all kinds of different models, some from our work, some from David Navarro Alarcon's work, or Dinesh Minocha and Jia Pan, many different kinds of control methods for deformable objects. But again, there's this trust that we can kind of assume this model that we're using is more or less correct, or has some kind of simple uncertainty distribution. Okay, so the question that I want to be asking, and we've been asking for several years in my lab, is what do we do when that's not true? What do we do when our dynamics models are unreliable? Now, please understand that unreliable doesn't mean bad. It doesn't mean useless, right? It means that there are some things the model is good at and some things it's not good at, right? And so what we want to do is use models. Of course, we need to use models, even if they're learned models. But we also need to learn to avoid a model's mistakes, okay? We're not going to be told a priori where is this model useful and where it's not. We need to be able to figure that out on our own and still perform useful tasks. So today I'm going to be talking about 2 very recent papers that are on this subject. One of these works, just published in Science Robotics in the May issue, is about using a learned model. So we're learning a model from data for deformable object manipulation, specifically rope here. And we want to understand when is it valid and when is it not. And the other work I'm going to talk about is using what we call a simple model, which has a different kind of application when we don't know the state space of the object that we're encountering. So let's start first with the learned model. So this is the work of my students, Peter Metrano and Dale McConaughey, who's now at TRI. And what Peter and Dale were looking at were the following questions. First, we wanted to say that we don't know the dynamics of a deformable object a priori, right? We want to learn these dynamics. But the traditional way to do that is to just gather a huge, huge data set for a given task and try to learn the dynamics from that. And actually, that's not going to work in the kinds of tasks that we're trying to do. So instead, what we're going to do is learn the dynamics in an unconstrained environment. And now we'll have a dynamics model. And then we'll learn a classifier that tries to predict when is this dynamics model reliable in actual constrained environments where we want to use it. Now, you might say, well, that's great. You can maybe use this classifier to avoid unreliable transitions or actions when you're doing planning, but you still have a big problem. in that your start state might be in a place where your model is unreliable. So we also developed a way, again, based on learning, to learn how to recover when our model is in a state, when our system is in a state where the model is not reliable, so that we can move towards a state where it is. So I'll go over this work in a little bit of detail, but I really encourage you to read this paper as there's much more detail there. So the first step to this process is learning dynamics. Then we're going to basically figure out when the dynamics are valid and how to recover when they're not. And then we're going to use these dynamics in a planning and control, planning and execution architecture. So let's start with learning dynamics. So let's say we want to do tasks in this kind of tabletop scene where we want to move the rope center to a given position, right? And as you can see, we don't just have a static scene. We do have a static scene, but there are many possible object arrangements in that scene. So what we're arguing in this paper, and our results actually bear this out, is that trying to learn all the dynamics of the rope as it interacts with obstacles and catches on things and slides on things and so on is very, very difficult. And this would require a huge, huge data set. I don't even know how huge it would be. We haven't found the right size for actually learning these kinds of dynamics reliably. So that's really, really hard. And what we're arguing is that it's much simpler to learn dynamics in this kind of unconstrained environment. And in fact, we show this in our results that we do learn good dynamics here. And then to use these dynamics in the constrained environment where they're valid. Now, again, if you are doing this, you're basically sacrificing things like catching the rope, right? We're never going to be able to model how we catch the rope on obstacles. But we're still saying, hey, this is worth it because we can still do a lot of useful tasks, even staying in regimes where the dynamics of the unconstrained dynamics are valid. Okay, so the first step to learning the dynamics is then to collect a bunch of data in this unconstrained environment. And here we're rolling out random trajectories, not purely random, there's some bias in the randomness, but anyway, they're randomly generated and we get a reasonable sized data set, nothing on the order of millions, but thousands and thousands of data points here. And then we can take that data and we can learn a dynamics function from it. This is this model where we're just adding the dynamics function to the current state. Turns out this structure is way easier to learn than if you just eliminate this ST here. So we actually don't need a very complex network. We just have two fully connected layers here, and we can learn these dynamics very well. Okay, so now we've learned some unconstrained dynamics. When are they going to be valid? Well, we could hard code a bunch of domain knowledge like, well, if it's in collision and if it's too stretched, then it's not valid. But then, we're basically just telling the system what to do, and we may be wrong, right? For instance, in the case of sliding, our dynamics might still be valid as long as the rope doesn't catch on something, right? Okay, so how are we going to figure out when our dynamics are valid? Well, what we do is we take another data set, this time in the kinds of environments that we're going to be doing tasks in. But this data set is relatively small compared to what you would need to actually learn all the dynamics well. So once we get this relatively small data set, we can then measure the discrepancy between the predicted states of our dynamics model and the actual states we observe. And if the predicted and observed are close together, then we say, okay, the dynamics model was pretty good. And we give it a label of 1, meaning accurate. And if they diverge, however, then we give it a label of 0 or inaccurate. So then, given this labeled data, we are able to train a classifier. This is a supervised learning problem. And what we do is we take in the state and action that we saw in this data, as well as the local environment. The local environment is represented as a voxel grid where both the rope and the obstacles are voxelized. And then we can learn a prediction of how reliable the dynamics are for that state and action. Okay, so that's really nice. So that tells us what kinds of state and actions we want to avoid when our model's not reliable. But we still might start in a state where the model is unreliable, or we may just be perturbed into that state during execution. So we need a way to be able to escape from these states where we are essentially stuck. Now, why are we stuck? We're stuck because in a state where the model is unreliable, any action you try will be rejected by the classifier. So we can actually sample over possible actions given where we're starting, and see if the classifier is going to reject all of them. If the classifier does reject them, we need to recover, otherwise we will never escape this state. And by recover, I mean we need to move to a state where we can actually do some actions. So this is an example of a start state. The unconstrained model has never seen this kind of state before, and as you can see, it rejects all the transitions we try from that state. So how do we actually learn to recover? Well, what we're trying to do is move to a state where the model can actually be trusted. So how do we find such states? Well, we're going to use that same data set that we collected from the environments with constraints to find states where the classifier predicts 0 for many different actions. This does not require getting any more data. It just means that we're going to evaluate actions at states given the classifier we've learned. And then we can see when does a state where essentially we're stuck according to the classifier then turn into a state where we can actually get some non-zero classifier outputs. So if we look for that in the data, then we have examples of when we were stuck and then how we moved to get to a state where we were essentially less stuck or unstuck, if you want to say it that way. And then once we train that recovery network, we can use it to escape from these stuck states. So as you can see here, it's performing recovery. In this case, it's actually lifting the grippers up until the rope is kind of close enough to what we've seen in the training data. And the classifier says, okay, this is good enough. And we run our planner. Okay. So the third part of this framework is the planning and execution. And here I'm just going to go over it at a very high level because it's fairly straightforward. But the idea here is that we're using kinodynamic RRT with the learned dynamics, the unconstrained dynamics. So that's pretty standard there. But we're also including this classifier to reject transitions where the dynamics are unreliable, because again, we don't want to get into those regions. And that produces plans that might look like this, right? So we start out, we lift the rope up, and then we move it over here to the goal. Again, the goal is to move the center of the rope somewhere. Now, during the execution or before we can even start to plan, we may be stuck. So we may need to engage that recovery and replan, and basically recover and replan iteratively until we hit a time limit. So we tried several experiments to show the effectiveness of this method. The first thing we did is test this on what we call rope dragging tasks, where a gripper is holding this red rope, and the goal is to move the end of the rope to some location. So we're holding this side, but the target is for this end here. In dual arm rope manipulation, it's what you saw before in those tabletop scenes. We're trying to move the middle of the rope somewhere. And we compared this method we developed to several baselines. The most important is learning the full dynamics. This is kind of what is traditionally done. You just get all the data and you just try to train a dynamics model that captures everything. We also compare to ablations of our method. And the metric we're using here is basically the distance to goal after 3 minutes of planning and execution. And we define being within 5 centimeters as a success. Okay, so here's what the results look like. This is for dragging the rope around. You'll see some videos of this in a minute. But this is what the results look like for using the classifier versus not versus full dynamics. As you can see, using the classifier here definitely improves over the no classifier case. And improves vastly over the full dynamics case. This is just reinforcing the idea that trying to learn the full dynamics of the deformable object in a complex environment is a really, really hard problem. And we don't have nearly enough data, at least in this work, to learn that. So we need our method to actually be able to accomplish tasks. And in the dual arm rope manipulation, we also see the benefit of the recovery. So these two lines up here, the purple and the blue, represent results for the classifier using recovery as well. And as we can see, using recovery does much better than the classifier, no classifier. And again, full dynamics is doing the worst here. It's true, however, that a randomized version of the recovery that doesn't use this learning method is actually performing quite well too. So that suggests that maybe we need more data to actually predict recovery actions better, though we do do a little better than the random version of recovery. So I think the main takeaway from the results is actually with respect to the full dynamics. So what we're basically seeing here is that learning the full dynamics is not tractable for this kind of data set. And what we need to be doing is something more like our method that's able to take advantage of the unconstrained dynamics and still do useful things in constrained environments. Here are a few videos showing this method in action. So I want to first say, I don't want to be misleading here. There's no online perception or replanning happening here on the physical robot. All of this is planned in simulation and then executed on the real world. So before we saw the rope dragging, now you see this hose. It starts out in a state where it's very different from the states we learned the unconstrained dynamics. So we can do recovery, we can lift it up, and then plan to move the center of this hose to the goal here. You can see this is kind of in an automotive setting. It's obviously not as difficult as a true engine bay that's very cluttered, very difficult to move around in. But still we see that our method is able to avoid a lot of this clutter, avoid getting the hose snagged on something and get to the goal. This would be to position for windshield wiper fluid cable installation, for instance. And we can also do things like moving these straps out of the way. Now the straps are tricky, right? You see how dynamic they are, how they're swaying back and forth. Our model does not account for that, and you see it caught a little bit on the corner there. So this is just showing you a kind of rough idea of what would happen in the real world with these. We still need to do a lot more work to make this robust. Okay, so that was the work on using a learned model of dynamics and then avoiding that model's mistakes. But we don't always want to use a learned model. I mean, I think a lot of people think now that that's the only way to go. It's really not. I think that engineers have been using hand-designed models for a long time and will continue to do so for a long time. So this other approach actually addresses something that the first one did not. So if you noticed in the work I just showed you, the state space of the object was known a priori, right? So we were able to say, oh, the rope state is defined by, you know, a set of points on the rope and so on. But if a robot encounters a new object that it hasn't seen before, the state space may be very hard for it to know. So what do we do when we don't actually know how to represent the state space? Well, that's what we're going to talk about with the simple model work right now. So before I get into that, I want to just give a little bit of motivation and just talk a little bit about how engineers and roboticists have been using simple models, right? So something as complex as a car with the transmission and the engine and the friction of the tires, we don't want to deal with all that, right? We don't want to deal with all that complexity. We represent it as kind of a bicycle, kinematic bicycle model often. When we think about humanoids, we definitely don't want to deal with all the complexity of a humanoid when it's doing something like walking or balancing. And so we use simplified models based on inverted pendulum. Same with robot arms. We idealize them as rigid links with perfect joints that can just move kinematically. Again, in idealization, it's a simplified model. And we've proposed our own simple models for deformable objects. So for instance, instead of trying to understand exactly how every wrinkle in a cloth moves when we're manipulating a cloth, we can reduce that cloth down to what we call the geodesic between the grippers. And that model is called a virtual elastic band. And so that's a model we developed for the purpose of doing useful things with cloth that ignores almost the entire cloth and just tries to capture what's important, right? So engineers do this all the time. And what Tom did, Tom is a PhD student in my lab here, is to try to make these simple models work for deformable object manipulation while also accounting for their limitations. And so again, I'm going to give a brief overview of this work. I really encourage you to go to Tom's talk on Tuesday in the session you see here and see the full details and ask him all of the difficult questions. All right, so what we're trying to do in this work is find an action sequence such that the system, which is our deformable object, gets to a goal region. Okay, so standard kind of perform a task, right? But here's the big problem. Well, there's two big problems. First, the dynamics of the underlying system are unknown. Okay, well, maybe we can learn them with some data, maybe not, I don't know. But here's the issue that's even harder. The state space of the underlying system is unknown, right? So we can't even say, here is what this thing is, now learn its dynamics. We don't actually even know exactly what it is. But we have, of course, some information. We can look at it, basically. So we can get some high dimensional observations, basically images called O here of this system. And we have some function that tells us when we're at the goal. Of course, we need to have some function like that, otherwise we can't perform any task. Okay, so you see here on the right an example of a system that with a deformable object. So this is what we call tethered mass. It's a mass, that's the ball, that's on the end of a rope. And the rope is being held by this end here, and it can move back and forth. Okay, so this is a tethered mass. Again, the robot has never seen this before. How are we going to manipulate this tethered mass to maybe bring this mass to some location that we want to bring it to? And our objective is to do this task with as little interaction time as possible on the true system. So it's well known that if I just play with the system long enough and get enough data, I can use some model-free RL method to figure out how to do this task. We all know that. That's been done many, many times. But what those methods are not is data efficient. And when we're talking about robots interacting with things in the real world, we need to be data efficient. So, of course, we have some prior knowledge, and this is where the engineer comes in and says, okay, this thing looks kind of like a model I know about, right? So we're going to say that we have some coarse approximation of the system state, which we're going to call Z, and we have some simple model dynamics. Now, these dynamics could be learned, they could be hard-coded, they could be in a simulator. That's not so important here. What's important is that we have some kind of baseline approximate or simple model dynamics. And here for this system, we might pick a card pole, right? A card pole can translate in X and it can swing this pendulum here. That's the theta dimension of the state. All right, so we know everything there is to know about card poles. We can generate as much data as we want from card pole dynamics. And in fact, we can actually see, just us, people looking at it, that there is a correspondence between this model and the state of this tethered mass sometimes, right? Sometimes, as up here, this looks nothing like a card pole, but sometimes it does look like a card pole. So let's exploit the fact that sometimes it looks like a card pole to actually control it like a card pole. Now, the problem is, though, that we don't know where it looks like a card pole. We're just given this object. We know, hey, something about this looks like a card pole, but we actually don't know what state and actions can be modeled well with card pole dynamics. Our future work is to pick which simple system model we use as we're actually performing a task, but we haven't got there yet. We're working on that. Instead, we're just going to say, use this simple model and perform the task. Okay, so this is our framework. There's a lot of boxes. Please don't be overwhelmed. I'm going to go through it in pieces in a second. But the idea here is that we're going to do some offline training and then some online execution and model fitting, or uncertainty prediction, I should say. So offline, we get a data set of observations from the simple model being rendered, and we learn an ensemble of CNNs to estimate the state of the simple system. Now, the reason it's an ensemble is that it gives us a notion of uncertainty about how out of distribution the things we're seeing are.
And that is going to be useful here. So when we are online, then we can get observations and use this ensemble of CNNs to predict the state, but also with an uncertainty distribution on it. We can propagate that uncertainty using a UKF, a variant of the Kalman filter here, and then we can consider that uncertainty as a cost in a trajectory optimizer, which is MPPI. But we also need to get the data online as we're executing to fit a GP, which tells us about where in the state space our model is valid and where it's actually going to be erroneous. And the upshot of this is that our model is going to end up being valid in states or that generate observations which look like the training data we've seen. If we see something that looks radically different, like if we train on a rigid link and we see a bent rope, then we're going to say, whoa, I really don't know what's going on. So again, the idea is to stick to what you know and do actions that are going to be valid for the simple model. So here's what this actually looks like. This is the offline training for the tethered mass. Again, it's modeling things as a cart pole. So you see these kind of rigid links, and it's seeing a bunch of different cart poles with different masses on the end, but it's never seeing any bend in the pendulum. Then online, it encounters an observation that looks like this. It fits the simple model to that observation, says, oh, this looks like a cart pole of this length with this mass here. And then it can plan a trajectory and then start to execute it and replan as it's executing. So we tested this work in several experiments, first on the tethered mass, also on this kind of narrow passage rope insertion, and then also that a version of that in the real world. And again, the metric that we really care about here is data efficiency. All of these tasks can be learned with enough data using black box RL. We already know that. But what we want to do is really get a big gain on data efficiency. So the baselines were both model-free and model-based. Model-based is Planet and model-free is curl here. RL methods, we tried with pre-training on the simple model observations. We tried not pre-training on them. Turns out it doesn't make a big difference. And we also tested against ablations. For the tethered mass, we use the cart pole, as I mentioned before. And as you can see, sometimes it looks like a cart pole. Sometimes it looks nothing like a cart pole, right? So our goal is to stick to parts of the state space that look like this. And here's what the learning looks like kind of in episodes, right? So as we try the task over and over again, we don't want to hit this target with the rope, I forgot to mention. Anyway, as we try the task over and over again, our method, LVSPC, learns much faster because it's leveraging the knowledge of that simple model than, for instance, these methods here. We see this borne out in the statistics too. LVSPC in blue does better after only 20 trials of the task, just 20 executions of the task. We're already getting above 80% success rate, whereas curl, the closest competitor, takes over 200 episodes to get to the same level. Now it does have highest asymptotic performance. So if you give it enough data, it will basically memorize everything and win. But what we're looking for is success in the low data regime. Another task is to bring the center of the rope into this narrow gap here while avoiding getting caught on these hooks that you see there. The simple model there is a rigid link. And as you can see, LVSPC, after only 20 trials, is able to complete this task. And you'll see the statistics, whereas the other methods are barely getting started on the learning. Again, LVSPC in blue gets about 80% success, close to that. Again, curl takes about an order of magnitude more time, more episodes, I should say. But again, as we know, we'll have highest asymptotic performance. And then we said, okay, well, this is all very nice in simulation, but what about the real world? And so we trained with images that were domain randomized. This is, again, just the simple model, but we are randomizing the background and the colors of everything. And it turns out that does allow us to do things in the real world. So again, we start out, we don't really know what we're doing, and we get caught on the rope. But again, after only 20 episodes, only 20 tries, we're able to perform this task successfully 82% of the time. I think that is a phenomenal success rate with this little training data. Okay, so to summarize, what we've talked about here is learning to avoid a model's mistakes. There's a whole lot of future work to do here, including picking simple models autonomously, generalizing and transferring our learned models between tasks, a whole lot of work to do. But before I end, I really quickly just want to do a quick bonus video and advertise the talk of Yifan Wang, an undergraduate just graduated from University of Michigan, and also Dale here again. And this talk, this work is being presented on Wednesday. I really encourage you guys to go to the presentation. It's about tracking deformable objects despite severe occlusions. And again, it's using a simple model and some geometric constraints to make sure that our predictions are kind of realistic and plausible. And it really outperforms some very competitive baselines here. And it even does things like consider self-intersection, it considers obstacles, it considers dynamics prediction, and making its prediction that can be simple or complex. And it's really great work. And I think a lot of you here who are working on deformable object manipulation will be able to use this in your work. The code is freely available on GitHub, so I really encourage you guys to go to that talk and try this code. Okay, so with that, I'd like to say thank you to my wonderful lab and all of the amazing students that have worked on the things you've seen here, as well as the rest of our work. And I'll open it up for questions.
Yeah, thanks, Dimitri, for the great talks. And we have a question from Rachel, and she's asking, for the first system discussed, what's the boundary of the type of errors that are recoverable versus the ones that cannot be recovered?
That's a really great question. Thank you. Yeah. So it is possible that you get into a state where the rope might be, let's say, under a hook, right? There may be no easy way out, right? You would need a very complex motion planner to, go out under the hook and go around the hook. And our recovery policy doesn't do that. It's just taking kind of a greedy one-step action to say, okay, what's the next best state I can move to from here? So there are definitely cases where it will fail, and you'll basically just keep running recovery over and over and over again, but you'll be stuck in the local minimum. So that's a really interesting problem. It is as hard as the entire problem we're trying to solve, unfortunately. So we don't have a good answer for that at this time.
Okay, thanks. And I actually have a small question. So I think it's great that you presented these two approaches, but I was wondering if you have some hints about when we should go for a learned model and when we should go for a kind of simpler model, as you presented these two possible solutions.
Right. Yeah, it's a very difficult question right now because the boundaries aren't really clear. In the work specifically that I presented, the learned case is most useful when you have a good state representation, right? Because the state representation allows you to understand when your prediction is accurate versus not, right? So if we didn't have that state representation for the rope there, we wouldn't be able to do that method. And the simple model method is really when you're encountering something new and you don't know what it is. So you don't know what the state space is, so you can't possibly do the learned model. So you need to use something else. So that's this specific work. But at a higher level, when should you use simple models or not? I think it really depends on the task that you're doing, right? If the simple model captures a range of behavior that allows you to perform the task efficiently, then that's what you should use. Because first you can understand what it's doing, you can parameterize it and so on. It has all these nice understandable properties. If you can't do that, you're just encountering something that is just too strange, you don't know how it works, but you can get data, then you should use a learned model.
Okay, thanks. But do you think that the second model, so the simple model, could also generalize to some more complex shapes? Because now you're dealing with the rope, but it seems that it can be also adapted to kind of more difficult shapes if we have some prior basically. And is it something that you think it's doable with the simple model? And have you tried it?
Yeah, so we haven't tried yet, though we want to move it to cloth. I think that is kind of the next step. And some more complex shapes of cloth or you know, non-homogeneous ropes. I think those are all possibilities. It again becomes a question of, do you have a simple model that's sufficiently useful for doing the task?
Yeah, of course.
And if you don't, then your only choice is to try to parameterize something and learn. And yeah, so I'm definitely interested in that, but we haven't gotten to that point yet.
Okay, great. So I think if there are no other questions, let me check. Yeah, I think we can move to the next speaker. And thanks really a lot for your talk. That was extremely interesting, and we will be watching these talks that you advertised.
Okay, great, wonderful. Thank you for the invitation.
Thanks.
All right, then we are going to introduce our next speaker. It's Yifan Wang. She is an assistant professor in the Robotics Institute, Carnegie Mellon University, and the principal investigator of the CMU RoboTouch Lab. She received a master and PhD degree in mechanical engineering from MIT and bachelor's degree in mechanical engineering from Tsinghua University. She also worked as a postdoc researcher at Stanford University. Her research interest is in robotic touch sensing and robotic perception in general. And I don't think we can hear you. We can see the slides.
Okay, finally it works, right?
Okay, perfect. Yeah, now it works.
Thanks very much for the introduction. It's really a big pleasure to have a chance to come here and introduce my work of using high-resolution tactile sensing for perceiving deformable objects. So today I'm going to talk about more on the perception side, especially what happens if a robot can use tactile sensing to perceive those deformable objects. And particularly, I will consider two cases of deformable objects. So one of the examples of the deformable objects are things like avocado. So this kind of objects are made of softer materials. So we can perceive like some of the avocado is softer than the other ones, or we may say that deformable. It's just because like the material made of those objects are deformable and have different level of hardness. And the other kind of deformable objects are things like fabrics, and of course ropes, as we just heard from Dimitri's talk. So those kind of objects, if we consider the material itself, it's not that much pressable. So like if you have a very thin layer of fabrics and you want to press on it, so it usually doesn't deform a lot. But if you consider the global structure of those objects, there's lots of they may have deforms a lot, but it mostly comes from the on the structure side. So as a humans, it's very natural for us to perceive those objects through touch. For example, as soon as we are touching a avocado, so we can quickly learn whether it's a soft avocado or it's a hard one. And when we touch a piece of fabrics, we can quickly learn like how soft it is, how deformable it is, how stretchable it is, etc. So we have a good use of our touch sensing. So, but the things I've been trying to figure out with my colleague is that whether a robot can do similar kind of perception with tactile sensing. So when we talk about tactile sensing for robots, this is a very typical scenarios we may think of. So here a robot is trying to grasp an egg. So we know that the robot wants to use a moderate force for the grasping, so that it's not really crushing the eggs. So here the robot has equipped it with two tactile sensors on the two fingertips. And those tactile sensors are able to detect the distribution of normal force during this operation. So that like the good thing is that like the robots can detect like where is the contact, what's the approximate shape of the contact, and what's the force of contact. So that is very helpful in this like specific egg grasping task, because the robot want to control the force of contact to prevent crushing the objects. So that like by mirroring this normal force on the fingertips, the robot can understand, oh, hey, this is a acceptable force, it's good, so we can grasp the egg. So, but we can also see that for this kind of tactile sensors, so although it's very helpful to get some good estimation about the contact areas, the geometries, the contact force, but it's still pretty limited. So the information it can get is very limited, especially if we consider like some more subtle properties of objects. It's not really enough to do the job. So here we propose another potential solutions to this challenge by introducing a type of high resolution tactile sensor called gel sight. So this is invented by my PhD advisor, Ted Edelson at MIT. So the basic idea is that we use a vision-based method to detect touch. So in other words, we embed the cameras into this structures, and on the top on the surface of sensors, we use a piece of deformable elastomer as a medium of touch, and we also design some optical structures to make sure the deformation of this soft surface can be inferred from some optical signal that can be observed by the camera. So in this way, we are able to get a very high resolution details of the objects being touched. So especially regarding to its geometry, but we can also get some information about the force and torque on the contact surface. So here shows an example of how the sensor works. So the first window here is a human holding the sensor, touching different objects on different locations. So the middle image here shows the raw output we get from the gel sight, the camera into the gel sight, or in other words, it's also the output we get from the sensor. So there are two things happening. So on one hand, we can see the background colors from this image. Like normally it's like almost a gray colors, but upon contacts, there could be some change of the colors. And that change of the color is highly relevant to the geometry of the objects being contacts. And since we have like all those fine details on the this soft surface, and we use a camera to detect all the details, they're able to see the very fine details of the geometries from this change of the color. So on the other hand, we can see all those black dots. So they are physically painted on the surface of this sensor. So that and we can also track the motion of the dots. And they are very informative of the contact force and torque, especially the shear force and in-plane torque. So I'm actually drawing the tracking the motion of those markers in the third window here as those yellow arrows, and the direction of the motion of those arrows and the magnitude of the arrows are very informative about like whether it's a normal force or shear force and what's the magnitude of the force. Okay, so there are some questions, some chat windows. Let me see whether I can. Okay.
I think it's unrelated to the talk. It's for the next session. Sorry.
Okay.
We will have the questions at the end of your talk.
Okay.
Thanks.
So here we have the sensors, and so we also attach that on a robot, so on a robot gripper, so that the sensors can work as one of the fingers of the robot, and the robot can carry the sensor to detect different objects and perceive those important tactile informations upon contact. So when I look at those videos like about the contact sequence, so we can see lots of interesting things happening. So of course we can see those change of the geometry and the force, but also like I said, it is a change because the sensor itself is soft. So the contact is not like at one moment, but it's a dynamic process. And the good thing is that we can use our sensors to detect all the information happens in this dynamic process, like how the contact geometry changes, how the contact force changes. So this is pretty similar to the process of human touch. So we know that as humans, the fingertip is most important things for us to perceiving the environment, the external objects. So because like at least on the first step is that on the skin of our fingertips, there are a bunch of mechanical receptors to help us to understand what's the first information on the skin side. But if we take a look at like the structure of the fingertips, it's actually a soft fingertip, and it's wrapped around the rigid bones. And upon the contact, there's lots of deformation on the soft fingertip itself. And that is a very important type of physical interaction between your fingers and those external objects. And when we see that we have those mechanical receptors on the fingertips, we can detect the contact, we can detect the informations. So we know where is the contact, we know the force. But also it detects this dynamic process of the contact. It helps to understand like how your finger, how this soft fingertip is deformed and how that reflects about like the important information about this external environment. So if we consider basic problems about like perception of deformable objects, so that could be estimate hardness of objects. So a typical way of asking a robot to do this is building a structure like this. So we can ask a robot to use an indenter to indent objects with well-controlled speed, so that we can measure the force during the process, and we pair that with the motion, the constant speed. Since the force is known, the trajectory is known, the speed is known. So we can just use the basic relationship between like the contact force and indenting depth to indicate the hardness of the objects. But this method is very constrained, since that it requires very precise control of the motion and very precise changing the sensing. And it only works with objects that has a flat surface or has a very well-constrained categories of the geometry. But on the other hand, there are also some studies about how humans do this kind of things. So as we talk about like in the previous slides, human has these soft finger structures, and we learn lots of information from this dynamic interaction between the soft surface and the external objects. So actually, there has been a human study showing that if a human perceiving objects in a passive ways, or in other words, is as shown in these videos, the human is now moving, but an external object is touching the fingertips of this human. So that in other words, like this human has no control of the displacement. They have no clues about how hard was the displacement of this pressing or indenting into the objects, but they could still have a very good perception of what's the hardness of these objects. So this indicates that, like, in many cases, humans has more reliance of this dynamic process that can be perceived from the skin about the deformation of these soft fingertips. So the question is that can we use the lessons from the humans to get some better perceptions of the objects as well? So we did a simple experiment with our gel side sensor, which has a soft surface and can perceive the geometry of the contact objects with very high resolution. So we handheld these gel side sensors and press on objects that has a hemispherical shape, and it's also actually deformable. So of course, like the most important thing we can get from the gel side sensor is the geometry of the objects. So that is because the sensor's soft surface deforms during the process. But also, the objects may also deform if the object is soft. And we found that the softer the objects are, the more the objects may deform during the pressing process. And of course, usually the normal force is smaller during this process. So the good thing is that we can perceive the geometries exactly. So here is the sequence of the output we can get from the gel side sensor in these pressings. So we can see that from the window here, so there is a round area, it's growing larger and larger, has a distinct color from the backgrounds. That indicates that indicates the geometry of the object surface. So since this is a hemispherical surface, so the contact area is a dome shape, it's round and expanding as the force grows larger and larger. So on the other hand, we can also ask the sensor to press on an object that is of exactly the same geometries, but with a much softer, but it's much softer. So we can perceive some information like this. So it's still a round contact areas. It still has a dome geometries, but we can see that the color here is much shallower. So that is because the surface is much flatter in this case. Why this happens? Because the object is much softer and has much more deformation. So that means like during the press, it's more likely you will flatten out the objects. So the good thing is that we can perceive those like very fine, very small change of the object geometry with the gel size sensor exactly. And we can use that as a clue to help us to estimate how hard is this object. So of course, another thing we can consider is the normal force. So as our intuition tells us, like when we press on a softer objects, the force is generally smaller. So on the other hand, in the other words, that means like if we consider the motion of the markers, which indicates the pressing, the contact force, so we will see that like when we pressing on harder objects, the marker will have a significantly larger movements. So that means that represents a much larger normal force. And but if we are using our sensor to contact a softer object, as shown in the second row here, the motion of the markers, as the yellow arrow shows here, is much smaller than the first case. So that means like the contact force is much smaller. So that there are two most important clues here. So one is the contact force, one is the geometry that can be indicated from the colors. So we can just we just train the simple regression models to measure this dynamic change of those the colors, as well as the motion of the markers through the process. And we use that to estimate the hardness of the objects through this from this contact sequence. And it works pretty well. So, but also the constraint is that it only works for the objects with a spherical geometry. So where we know exactly what's the what we can predict as the contact geometry changes, and then we can simply build our regression model based on the colors and based on the motion of the markers. And so that means like at least by theory, this clue works well for helping robots to estimate hardness, and also for understanding those spherical objects. But it may turn out to be very challenging if we consider the contact or the detection of an arbitrary objects, which may have very unpredictable or unknown geometry. So we know the physical foundation is still there. Like during the context, we can consider the change of the geometry, the change of the contact force. They're still highly relevant to the hardness level of the object itself. But the big challenge here is that how can we build a model to describe these changes, to describe these differences across material objects with different hardness? So then we turn to data-driven models to solve the problems with neural network methods. So that means like we build a big data set of using a tactile sensor to contact objects with different hardness, different geometries, and hope the neural network can learn something. So firstly, we build this object data set. So we use silicon to cast based on like using different kind of modes, including some of the simple shapes or more complicated shapes. So we use different type of silicons so that we can control the hardness of the samples. And we also consider some of the natural objects, such as the fruits, candies, or human bodies, or some toys. And we don't have a good understanding about like the ground truth hardness level of those natural objects, but they can be a good test objects to give us some intuition about like how our method works to generalize on the objects that we really don't have any background knowledge about how hard they are. So then we collect a data set with a gel size sensor, either ask a human to conduct the contacts, or make a robot to conduct the contacts. And so we use both ways to contact those objects, the objects in our data set at different locations, different force, different trajectories to make sure we have enough varieties in our data set. And then we train a neural network with a structure like this. So the input of the neural network is a sequence of the contact of the gel set images. So that means like we can see what happens on a single contact case, and we can also see how this contact information changes as time proceeds. So that there are actually, and then we build this network with a combination of CNN structure and RN structures. So the CNN structure is more important to tell about like spatial information. In other words, it tells about like in this single moment, what is the geometry of this contact surface and what's the contact force. And the RN structure is more important to tell about temporal information. It's about like how this geometry changes as time goes and how the force changes as the time goes. And finally, we make an output about the single numbers regarding to the hardness level of these objects being contacted. So to test out our data set with lots of silicon samples where we know we have good understanding of the ground truth, we figure out like with a case working on like objects that has a same shape on the hardness, or like totally new shapes, or if the contact mode is different, like if we train on human data and test on like robot data, our network can do a reasonable job of estimating the hardness levels of those objects. And of course, we also have lots of interest at the first question about whether we can estimate the hardness of avocado. So here we use 2 avocados and ask a human to rank them from soft to hard. And then we make a human to press gel set sensor on the surface to guess the sequence of the data and estimate the hardness of avocado from the data. And we found out that the estimation from the gel set from the neural network matches the estimation of humans. Okay, that's a part of hardness estimation for the objects that is made of soft materials. So the second part I would like to talk about like the perception of fabrics, which is a good representations of the objects that is structurally deformable. So of course, like as a humans, we can get a good understanding of the fabric properties through touch, but like what can we do with tactile sensing? So here we consider the case of natural clothing. So here we ask a robot with a gel set sensor to go to touch different type of clothes in their natural states and take a look at what kind of data we can get through the process. So here the third one shows the like the tactile data we can be obtained from the gel set sensor through the entire process when contacting different type of the clothing. So we can see that there are multiple things happening. So on one side, so it's like we are able to detect very fine details about the contact surface. So we can see the geometry of the textiles very clearly. Like for example, this leather has this very dull structure, dull texture, and this is this clothes with polyester shells will have another type of the texture. But on the other hand, if we can also get lots of information from the overall change of the contact area. Like, is it like a very, is the contact area very large, covering the entire surface, or is much more smaller and only covers a smaller surface? And also there are some foldings happening during the context, like what kind of information can we get from those foldings? So all those information is very informative about like what's the material type of the object of this material it is, like how deformable it is, and what does it mean for a robot or for a human to understand this type of a material. So then the question is that like, how can we understand them? So we actually collect a big data set of like 150 clothes with a wide variety regarding to the materials and type of the clothes. And we ask the robot to explore them and touch on different locations collect a very varied data set like this. So as we said, as we just go through the process, we can see lots of difference in the textures, but the overall shape and structure of the clothing in context. And we want to have a good understanding about what we can learn from those tactile data. So again, we train a convolutional neural network to learn those relevant properties from those tactile images. So regarding to the properties or the ways we describe the clothes, so that's actually a big challenge. It's like, how can a robot understand those clothings? How can the robots use the understanding to help it to better manipulate or interact with those clothing in the daily life? So we use a reference of human perception, like we ask human, what do you think is most important things when you consider the properties of the clothes? So we summarize 8 physical properties to describe the clothes, like thickness, smoothness, fuzziness, and we also consider some semantic properties, like what's the wearing season of those clothes and how you should wash those clothes. So hopefully the robots can use those semantic properties to get a better sorting or arranging of those clothes based on those understanding. And for the ground truth, we ask a human to do the labeling. Like we ask human to put put all those properties into several levels and label different clothes as different levels. And we use that as a ground truth label. And hopefully the robots could come up with a prediction that is similar to the perception of human. So that finally we turn this into a classification problems, but it's multi-classes classification. So we use a neural network and take the tactile information from gel set as the input and make a classifications based on different properties and according to different levels, discrete levels in these properties. So we figure out with these basic structures, we can do a pretty decent work job on the object clothing that especially can be seen included in the training set. So for example, if we take a look at thickness, the chance of getting it correct with a random guess is 0.2. That means we are actually making 5 degrees regarding to the thickness level of a piece of cloth. So if we ask a robot to explore a cloth that is included in already seen in the training set, but it's totally new touch, so we can get the prediction correct with a chance of 89%. But of course, if we are exploring some unseen cloth, the performance is compromised, but still much higher than the chance. So the next challenge we want to make is that we want to make the robots to explore the clothes on its own automatically. So we design a system like this. We want to have the robots with a gripper and tactile sensors on their fingers, but also use a camera, which is actually a Kinect here, high up here, which is really helpful to detect the global information. And the global information will guide the robots to understand where to touch, so that the robot will choose a point and go ahead and just use the finger to squeeze on the piece on this part of the cloth and get a sequence of tactile data. So, so other than of course, there are lots on the robotic side. We want to understand how can we figure out the place to touch from the visual information. So we figure out a hack into this problem is that there are lots of foldings on the clothing, which can be represented as the edges from the depth images. And those are mostly the places very easy for the robot to generate some good tactile signals. But of course, some of those edges are good, what we call good edge points, and some of them are bad. The bad edge points where we can hardly get a good tactile image from them. So we train another neural network to figure that out. So finally, we have two neural network structures. Firstly, we use a depth neural network to figure out whether a candidate grasping point is a good touch point or not a good touch point. Once we figure that out, we ask the robot to go ahead to collect some tactile data and feed that into the second neural network and use that to get a bunch of perceptions of the properties related to this clothing materials. But then there's a question what happens if something goes wrong in the middle? What happens if it's not really a good point to touch and the data the robot get is not good, and the robot can hardly predict the hardness, the properties of this piece of clothing. So the easy answer is that the robot can just go back and redo this exploration procedures. So we actually designed this retrial loops by estimating how confident the robot is when predicting the properties of those clothes. So if the confidence is not very high, or in other words, like the classifications vectors is not very concentrated on the only one class. So we may come to the conclusion that it's more likely this is not a good tactile data. And the robot will just go ahead and touch the cloth again, collect another piece of data, tactile data, and use that to estimate the hardness, the property level again. So here shows an example of how this process works. So here the robot firstly tries to touch somewhere. It's actually a good place, but unfortunately there is actually a button buried in the cloth. So that turns out to be very confusing. So the robot decides, okay, I'm not very confident here, so I will lay the cloth and do a touch again. So this time it's a back place. So we can see that there's nothing in contact. The robot will figure that out immediately because there's no clothing in the touch information. So then it generates a third touch. So this time is very nice data. The robot is very confident about its predictions. So here is the robot is actually trying to do something further to decide how to wash this cloth and put the cloth into corresponding washing bin. So with this mechanism of retouch, the closed loop explorations, we perceive a much better performance regarding to the property estimation. So these are the results working on the object clothing that is not included in the training set. So for example, on the thickness, if we are asked the robot to only touch the cloth once, we can get things correct with a chance of 0.59. But if we ask the robot to do a closed loop explorations, we can get things correct with a chance of 0.65. Okay, so that's the end of my talks. So as summaries, we try to use data-driven method to understand the properties of deformable objects with tactile sensors. Especially we consider two types of material objects. One is like objects has softer materials, and we try to estimate hardness from the deformations and contact force change. And we also consider objects that are structurally deformable, like fabrics and clothing. And we try to estimate a set of physical properties from the tactile data. So at the last, I would like to thank all my colleagues working on those projects, and thank you for listening.
Thank you very much for the very nice talk. We have one question from the audience. It's asking if these test objects, I think it was the silicon ones, are available for viewing or files for download. If someone could kind of recreate this.
We have all the data online, open source. We can, I think the easiest way is search my name online, so there you can have access to all those data sets from my personal website. But also it's a big challenge about the physical data set. Like we actually spend lots of time collecting this data set of silicon samples and the data set of clothing. So some of them are still available in the lab. So if you're in US or can come to my lab, so we can talk about exploring those physical data set or mail them to you. But generally, they're not that easy to access as a digital data set.
Okay, thanks. And then I have a question of my own. Like when you explore these softness measures, like there are these traditional hardness measurements, right? Like the Rockwell or the Moore hardness scale. Like, are you planning of kind of extending those towards more the softness? Because if I remember correctly, all this material would fall in the softest category of all of these hardness scales, because they are really for minerals or rigid objects, not really deformable.
So the ground truth we use actually is the shore hardness, and we use the softest. The softest measurement of shore hardness is shore hardness 00. So we can measure the hardness of objects ranging from like very, very soft elastomers to the objects with the hardness similar to the rubber. So we figure out like for humans, those are the range of the objects, like the hardness perception is most important. Of course, there are also like engineering level of hardness, like comparing the hardness of wood materials, steel materials, or some other metal materials. I don't think like it's very important for human as a part of perception. So we are mostly focused on the range like a human is perceivable.
Thank you very much. We have another question from Alberto Longini. Have you considered also sliding exploration actions, like not just pressing, but sliding?
Mm-hmm. So yeah, that's a great question. So of course, there are different ways we can ask a robot to explore the material, different objects. So sliding, pressing is one thing, like it's mostly informative to tell about hardness of the objects. Of course, like sliding is helpful, especially if we want to estimate the friction of the objects. So we do have lots of interest on that. It's not, we don't have any results in that direction yet, but it's definitely a good way of thinking about how can a robot explore the objects.
Thank you. And we have one more question from the Slido. Are the sensors going to be commercially available?
Mm-hmm. So my PhD advisor, Kat Erickson, co-founded a startup of gel sites on this gel site technologies. So based on my recent touch with them, they have plans to commercialize one version of the robot sensors and might be on market probably very soon. So I encourage you to keep an eye on their company. So hopefully they will make the life of researchers much easier to access this kind of signals.
All right. Thank you very much again for a very nice talk. And then we are going to move on to the next scheduled event, which is the Spotlight session number 2. And just a reminder, we're going to play the pre-recorded videos for 5 minutes, and then we're going to have 1 to 2 minutes Q&A live. So the authors are now in the chat, and will then be called on to answer any questions that the audience might have. And you can ask the audience again through the Zoom Q&A or the Slido or the YouTube chat with some time delay. So preferred way is the Slido or the Zoom Q&A. And the first talk we're going to hear is from Rita Lesa from Chalmers University of Technology, and she will presenting Reform, a robot learning sandbox for deformable linear object manipulation.
Hello, my name is Rita Lesa, and in this workshop, I'm going to be presenting our work on Reform, a robot learning sandbox for deformable linear object manipulation. The motivation for this work came from observing similar software libraries such as RLBench, Concept2Robot, and AssistedGym, which aim to enable reinforcement learning or robot learning tasks in simulation to avoid the costly gathering of data in experiments. However, we noted that in these environments, there was very limited inclusion of deformable object manipulation tasks. Here, we're actually putting all that we could find at the time, meaning the rope environment in RLBench, the folding concept in Concept2Robot, and then dressing someone in AssistedGym. More recently, there has been new work done on this, but for example, SoftGym has released a benchmark on soft objects like cloth, rope, and even liquids. And Plasticine Lab has provided even more recently a library on plasticine manipulation tasks. In our work, we focus on deformable linear objects, such as ropes and cables, because we observe that this has been consistently studied and is still an open research topic. You can see on this conference, we have still a lot of active work done on DLOs alone. So Reformed is structured as the interface to the actual backend simulator, which is AGX Dynamics, a set of environments that I'm going to be presenting soon, and a set of classes which we found are facilitators for changing the reinforcement learning problem and testing new tasks. If you want to see the full presentation, I encourage you to visit us tomorrow at 10:15 at ICRA. We identify the fact that sometimes the deformation is just something we want to avoid, like when you pick up a bottle, you want to avoid spilling over by pressing too much. Sometimes it also can be negligible, and we can just consider it as a source of noise in our manipulation task. However, there are many manipulation tasks where the deformation is the actual goal, and we could categorize them into two main classes. Explicit shape control, where the goal is to deform the object into a specific shape, such as bending a wire into a paper clip. And implicit shape control, where the goal is to manipulate the object into a configuration where we don't care exactly how it looks, but it has to satisfy some more abstract concept, like tying a rope into a knot. For this, we proposed 6 environments. One where we want to insert a soft peg into a hole, cable closing where we wrap a cable around the cylinder, a similar principle but with a rubber band, and these are implicit shape control tasks. We don't care exactly how it looks, we just want that task to be completed. And then we have the explicit shape control tasks like bending a wire, doing the same with an obstacle, and then manipulating a rope on a surface. Reform has these 3 classes. One of them is the end effector class, which just defines how we control the object. It can be with 1 or 2 grippers. The compliance of the grasp can also be controlled. And there's an automatic scaling so that the reinforcement learning agent can always learn between -1 and 1, but then there's scaling for velocity and accelerations that make sense for the simulation. There are several observation types. Notably, there is RGB and depth vision data. And then there's also the reward definition class, which we find useful, especially when there's no clear way to define the goal in a way that it works well with reinforcement learning. And to know a little bit more about this, there's also going to be a presentation tomorrow at 1:45, where we go into how elastoplasticity makes the problem of shape control harder. In summary, to use reform, you need to, of course, have a Python environment, and it depends on Jim. It depends on the simulation software, HX Dynamics, and you can modify very easily the current environments by modifying the state representation, the control strategy, and for the explicit shape control problems, even the reward function. That's all for me. Thank you.
Thank you very much.
So thanks a lot for the presentation. I have a question. And in particular, I was wondering about the dynamics simulator that you employ. So the AGX dynamics simulator should be not free. And if this is the case, are you also planning to include other simulators, or are you addressing this issue?
Yeah, well, it is true that AGX Dynamics, it's proprietary. It's like Mojoko. They do have some discounts for academic use. And also, if we enter in some sort of collaboration, they are welcome to somehow have maybe even free access if you want to do something more specific within our project. At this time, there's no plan to use other simulators. One of the reasons why we have used this simulator is because they have specialized models for deformable linear objects. They have something called a cable model, which allows for this, as I mentioned, this elastoplasticity concept, where we can model metal wires quite more descriptively. And also they have this rope object, which we still haven't made use of, but it's quite promising because it allows for very, very long simulations of ropes and a lot of complex knots and shapes because of how it's basically dynamically formulated. So unfortunately, the answer is no.
Okay, but thanks. That makes sense. So I think the work is actually very interesting, and it's something we are currently missing. So I think if we have no other questions, we can move to the next talk. And thanks a lot, Rita.
No problem.
So the next talk is going to be Petro Peruzzi from the University of Strasbourg. He will present learning robotic needle steering from inverse finite element simulations.
Welcome to the ICRA 2021 workshop presentation, Learning Robotic Needle Steering from Inverse Finite Element Simulations. Here's a short outline of the presentation. In this work, we addressed needle-based therapies, in which precise needle placement remains a challenge. Robotic assistance has been proposed to both enhance the surgical gesture and to compensate the complex couple between needle and tissue during the needle insertion. In this work, we'll target specifically how the robot can account for the motion of these deformable bodies. The use of naive, rigid strategies for needle steering can lead to huge positioning errors. In green, we can see where the rigid strategies assume the needle tip to be and the result of a finite element simulation of the insertion. The state-of-the-art discusses many approaches on how to model the needle steering and integrate it into robotic control. Both the kinematic models and mechanical energy models assume the needle insertion to happen into stationary tissues and only account for the needle deformation inside them. Finite element models, however, are able to simulate both of the deformable bodies and their interactions. We'll be taking a closer look at the Bezic et al. Approach. The so-called inverse finite element simulations, or IFEM, are a promising solution. As you can see in the video, it is able to perform the needle steering in a complex trajectory while accounting for the soft tissue's deformations. IFEM interprets the needle steering as an optimization problem. It computes an end effector position which minimizes three objectives in the simulation: the tip-to-target error along the trajectory, the entry point motion, and the tangential efforts felt at the entry point. The solution is currently limited by the simulation complexity and can run at 20 Hz to perform robotic control. In this work, we propose to use a machine learning model to solve the inverse problem and command the robotic end effector in a higher rate. The method will learn from iframe demonstrations along 105 straight trajectories. Here are the main variables involved in the training process. We also chose to add uniform noise to the needle target position so it can better generalize to non-straight trajectories. We also compute the tip-to-target error for each time step and the displacement command produced by IFEM. The chosen neural network is called an extreme learning machine, or ELM, with a single hidden layer which presents fast learning speed and low inference time. As inputs, it takes the robotic position and the tip-to-target error and outputs a displacement for the robot to steer the needle along the trajectory. The needle orientation is set to respect a remote center of motion at the level of the entry point. In order to validate our method, we'll test ELM on previously unseen trajectories of both straight geometry and curved geometry. We will also test ELM on tissues with different elasticity parameters than the ones used for the training phase. Results showed the ELM was able to successfully perform needle insertion in all the previously unseen trajectories. When varying tissue elasticity parameters, a small subset of the insertions resulted in unstable insertions and the robotic command drifts away from the target. This occurred for trajectories in the border of the phantom, where the training data is more scarce. A precision analysis shows the ELM was able to provide clinically acceptable precision along the successful trajectories. For curved trajectories, the tip-to-target precision of the ELM remained small, while the IFEM kept a higher distance in average. Further tests are needed to address if this is an actual advantage of the ELM or if it's related to the additional entry point RCM objectives of IFEM. Timing comparison shows a 60% reduction in computational time needed to infer robotic commands using the machine learning approach. As a conclusion, the ELM shows a promising ability to learn from IFEM demonstrations and show relative robustness to trajectory geometry and elasticity parameters variability. Further tests are needed to compare it to IFEM as mentioned before, and future works will address the entry point variability and more complex simulation scenarios where the computational time advantage might really excel. Here are the references, and thank you very much for your attention.
Thank you very much.
Thank you.
Nice presentation. I have a question regarding the training procedure of these ELM models. Like how exactly are those trained, and like then how are they compared? I didn't quite get that from the video. If you could elaborate, that would be great.
Okay, of course. We trained previously on a set of 100 straight trajectories along that phantom, that rectangular phantom. So with the data exported from these insertions, we train our neural network model to be able to predict the IFEM displacements generated during this training phase, during the database generation phase, actually. So then we use these weights to infer these positions in a validation phase where we got the results from.
Oh, okay, because I was a bit confused because it looked like the ELM outperforms the IFEM, but it's trained on the IFEM, right?
Exactly, it's trained on the IFEM, but for its straight trajectories only.
Ah, okay.
During the training phase and the database generation, we never use the curved geometries.
Okay, thanks. Thanks for clearing this up. Really nice, Rick.
Thank you so much.
Good job. Then we continue with the next presentation, which is Ma from the National University of Singapore, and will present learning latent graph dynamics for deformable object manipulation.
Hi, I'm Xiaomar from the National University of Singapore. I'd like to present our work, Learning Latent Graph Dynamics for Deformable Objects Manipulation. Yeah, the robot manipulation has been successfully applied to different tasks, for example, like autonomous driving, warehouse robot navigation, manipulating rigid body objects, and flying a drone. One special characteristic shared by these tasks is that they have a very well-defined state space. But this doesn't always exist in the world. Consider tasks like pouring water, feeding a kid, folding cloth, and also like making my favorite noodle. So these tasks, they remain very challenging for the robots. We think the major difficulty here is that the large degree of freedom, when coupled with the nonlinear dynamics, will make the modeling of the dynamic model and also playing with it very difficult. So in this work, we take a different view. For objects like cloth and ropes, their dynamics can be sufficiently captured by a set of the key points. So this is similar to how humans manipulate cloth. We only consider the key point, such as the shoulder, the collar, and etc. We don't consider the full dynamics of the object because it's not necessary, and our brain doesn't model it. So the key points can be further grouped into a graph, where the edges further capture the key point interactions and further improve the performance of the model. So in this work, we introduce JUDO, graph dynamics for deformable objects manipulation. JUDO performs unsupervised key point detection directly from a top-down depth image. It extracts key point features, groups them into graphs according to the spatial relationships, and reasons a learned latent graph dynamic model for decision-making. Specifically, we use graph neural networks to capture the interactions among key points. A graph-based model predictive control is introduced to improve the quality of and sample efficiency of the planning. To effectively learn the dynamic model, we aim to predict the next state and minimize the difference between the predicted state and the encoded state directly from the images. Contrastive learning is further used to improve the quality of the learning model by contrasting the positive sample, which is the predicted state, with a bunch of the negative samples that are irrelevant and sampled directly from the dataset. We train a model in simulation with randomly sampled reactions and show that the trained model can be generalized directly to a real robot without any fine-tuning. We show that our model can successfully straighten and reposition the rope to different orientations. For example, like here, we reposition it with a degree of 0, 45, 90, and 135. We also show that the model can be used to flatten a piece of crumpled cloth with different sizes, and also fold them. Qualitatively, we show the results in the previous slide, and quantitatively, Jiang significantly outperforms the state-of-the-art models on all rope positioning tasks and also cloth manipulation tasks by a large margin. In addition, we show that now the model can be transferred directly to a kinematic robot with only simulation data. We mount a top-down camera, that is the Kinect, to generate the depth images. So here is a short demo video of the results. In this video, the bottom right corner shows the detected key points. Our trained model successfully straightens a rope and repositions it with an orientation of 45 degrees. In addition, it is also able to flatten a piece of cloth with only 4 steps of actions. And here are some additional visualizations of the detected key points. So the key points are visually salient on both simulation images and the real-world images. However, there are also some failure cases. The number of the key points has to be carefully chosen. It might be noisy given extreme deformation of the object. The inaccurate detections introduce additional noise to the model, but with the contrastive learning, the model is still robust. Yeah, thank you for listening. More details are available in the QR code. Thank you.
Thank you very much for a nice presentation. We have a question from from Minguri.
Sure.
Minguri, and it's may the key point detection network extract different key points of the same object in different frames? If so, how to train the dynamic models based on the unfixed key points?
Yes, it's actually a very good question. So the thing is that we consider that the key points across different time steps as actually the partial observation of the object. So that is to say that the key points, although they might not be aligned, however, like across frames, we will actually try to merge the key points to extract some kind of the global representation of the object. Then we use the global representation of the object as the input to the network instead of the exact try to match the key points across the frames. Yeah. So that kind of eliminate the issue of doing the exact key point matching across frames, and they might be different. And yeah.
Okay. Yeah. Thanks.
Yeah. Thank you.
Do we have more questions? No, I think that was all. Thank you very much again for a nice presentation.
Okay, thank you.
Interesting work. And we continue the spotlight presentation with Meerdat Dorsten from the Northeastern University. I will present deformable object manipulation using model adaptive techniques.
Hello, my name is Meerdat Dorsten and I'm a PhD student at Northeastern University Rivero Lab. Today I'm going to talk about our work on deformable objects manipulation using model adaptation techniques. Manipulation of deformable objects is a challenging task both for humans and robots due to their complex, anisotropic, and nonlinear mechanical behavior. As shown in these figures, the shape of a deformable object can drastically change depending on the applied force and initial shape of the object and many other parameters. In this work, we suggest a new deformable object motion model obtained by adaptation from existing rigid object model. Considering pushing as a motion primitive in many robotics applications, in this work we study the problem of pushing a deformable planar object along a desired trajectory on a flat surface by a robotic manipulator. So what we need is a motion model for the object, and then based on this motion model we can calculate the proper action by the robot. The equation of motion for a rigid slider can be presented by a steady-state representation. X dot equals f of x and u, in which x is the x and y position of the center of mass of the object and the orientation of the object, and u is tangential and normal velocities applied to this object. The main difference between a deformable and rigid slider is deformation. So we try to take this difference into account by adding an extra term to the previous equation, which is g of x and u times sigma, in which g stands for deformation effect and sigma is uncertainty. So our trajectory tracking problem turns into an optimization problem in which we want to minimize the deviation between the object's state and the desired state at each time step with respect to some dynamical and contact point constraints. To enable our robot to perform this trajectory tracking problem, we use adaptive model predictive controller for providing fast adaptation to changes in the deformable objects during manipulation. We use the following uncertainty estimator to estimate the unknown bounded uncertainty in our system. However, this method still suffers from difficulties in parameter tuning. For a better performance, we use learning-based control, in which we generated a dataset by pushing deformable object by different velocities in different directions, and we measured the motion of the object. We compared this motion with what we expected from previous equations, and this difference represent the effect of deformation in the motion of a deformable object. So training our multi-layer perceptual regression unit, we used this unit in controlling our robot. We replicated each experiment for 20 times, and as you can see in this result, learning-based approach outperforms adaptive model predictive controller. To wrap up, in this work we developed a model adaptation technique to represent the motion of a deformable object to demonstrate robust pushing task. Thanks for your attention.
So thanks for the talk. I would like to ask if you may elaborate a bit more on the training phase and on which data you used to actually train the model and how you acquired them and so on.
Yeah, so basically what we have done was for each deformable object that we use, we try to push with a robotic manipulator this object. We actually estimated the initial and final pose of the object, and then the vector which is pushing the object, and also the force that applied by the robot to the object. So having this data and the formulation that we have for rigid objects, we have compared these two different motions and used this difference as our criteria in our learning process. So we train our data set, and then we used this trained neural network in our optimization problem.
And how many data did you need for the model?
So
do you have an estimate of the size of the data set?
It's basically very dependent to the how deformable the object is. But we roughly use like 300 iteration for each object.
Okay, thanks. So we have also other questions. So from Joanna Mitsoni. And first of all, which parameters were the ones that were difficult to tune manually in the first formulation? And secondly, how did you model the deformation?
Yeah, so that's a good question too. Adaptive controllers basically are hard to tune based on the deviation, the bound of uncertainty that is involved. And in our case also, it was a little bit tough switching between deformable objects. And what was the continuation? Okay, actually we didn't model the deformation object itself. We modeled the motion for deformable object. So we just focused on what was necessary to predict the motion of a deformable object in a sliding motion. And yeah, we approximate the deformation in the object in two directions. So our object was kind of a slider objects, so we didn't focus on 3D. Yeah.
Okay, thanks a lot.
Thank you.
And I think we can move to the next speaker.
Yes, so the next speaker is going to be Alberto Longini from KTH Royal Institute of Technology, and she will present Perceiving and Handling Textiles, a Robotics Perspective.
Welcome everyone, my name is Alberto Longini, and today I'm going to introduce you the work that I've done with my colleagues about perceiving and handling textiles from a robotic perspective. Manipulation of textiles is relevant in many different fields. An example is fashion industry, which right now is undergoing a huge transformation due to sustainability concerns. The problem is that fashion industry is largely not automated, and that's because it has to face limitations that robots have when dealing with this kind of deformable objects. We were wondering, therefore, if we can find a common framework that could help to bridge the gap that there is between these two communities that are in fashion industry and robotic community. To do so, we firstly propose a textile taxonomy, which represents the production process of textiles. As you can see, we have two main branches. The left one, which represents the materials of the fibers that compose textile, while the second one is correlated with the production methods, which basically means how yarns are interlooped or intertwined. Both of these branches play a fundamental role in defining textile properties, and thus also the interaction dynamics that textiles have. And this is very, very important, but this just still the perspective of the industry. What we wanted to do is try to find a common point of view between fashion industry and robotic community. And to do so, we need to go behind the textile classification. We need to understand which are the most relevant properties that are worth being investigated, such as, for example, elasticity, smoothness, or color, or either the condition that an object like a garment could have. And to do so, we need to properly use the latest sensing technology and to combine them with the proper action, the manipulation action that could help us to understand and perceive these properties. But why a robotic framework could be relevant? This kind of perception is interesting from a robotic point of view. Well, because what we could understand is, for example, the status of a clothing item. Or it can be also relevant to understand how to design a control algorithm based on the application that we want for our robot. Or another interesting point could be how different conditional properties of objects influence the design of the algorithms that we want to design. A first initial example that we have done is related to the taxonomy that we have proposed, and we wanted to validate the taxonomy by a classification task and by means of the elastic property of the textile samples that we used to create our dataset. Our dataset in particular was composed by first arc measurements gathered by 2 robotic arms while they were manipulating and pulling the textile samples that we had. Initial results proved that these first arc measurements were carrying information about, for example, the construction techniques and also the materials. The image that you are seeing right now represents the 2D projection of our first arc measurements. And it's clear how we have here 2 well-defined clusters based on, as I said before, the construction techniques that in this case are referring to the taxonomy that we proposed are woven and knitted. We are also able to prove that these first arc measurements were relevant to distinguish the materials, as well as both the joint combination of materials and construction techniques, meaning that the robotic framework is important when dealing with classification of textiles based on the industrial perspective. To briefly sum up, what we wanted to say is that there are many scientific questions related to perception and handling of textiles that could be also relevant, for example, to bring closer robotic community and fashion industry. There are many open problems and future direction that we would like to investigate and that we hope that other researchers will investigate.
Thanks, Alberto, for the presentation. And I would like to ask a question. So it's about the relationship between the taxonomy that you proposed at the beginning and then the set of properties and conditions that you have in the second taxonomy. So what's the relationship between these 2 taxonomies that you highlight?
Okay, thanks for the questions, first of all. The relation depends a lot on the tasks that you want to solve with the robot, because the textile taxonomy represents what the production method of textiles. So it could be a matter of elasticity based on how close the yarns are, or could be also the durability of clothes. The relation with the second table is more at terms of finding a common perspective between the industrial framework and the robotic community, because what we wanted to exploit with these 2 tables is that there are some stuff that are relevant from the robotic perspective that are properties of clothes, of course. For example, as I mentioned before, elasticity, or there are conditions that, for example, how old a cloth is could influence also the elastic behavior of this cloth. So this is something that could be relevant for recycling purposes. But how to understand from the industrial perspective the correlation between properties? Well, these properties are defined also by materials and construction methods. So this was the goal. So to explain to the robotic community which is the industrial perspective when they are producing these kind of fabrics, and understanding it could help to have a clearer view. For example, to understand elasticity, because the anisotropic behavior of textiles depends on the construction method. So if you don't understand well the construction method of textile, maybe it's not that clear how to manipulate a textile or a cloth. So it was the goal not to have a strict relation, because of course not all the properties of clothes are related to the taxonomy that we proposed, but it's relevant to know that.
Okay. Thanks a lot for the clarification.
Thank you.
So I think we can move to the last speaker.
Yes, so the last spotlight presentation, last but not least, will be held by Sven Dittos from Artimines Robotics. And it's about localization and tracking of user-defined points on deformable objects for robotic manipulation.
Hello everyone, my name is Sven Dittos and I'm a software engineer and expert for advanced robotics at Artimines. In the next minutes I'm going to present the results of our approach on how to localize and track user-defined points on deformable objects for robotic manipulation. Manipulating deformable objects requires localization and tracking of points, which can be very challenging. Many state-of-the-art solutions are addressing this issue, but still have drawbacks. Some approaches are limited to specific materials, geometries, or distinct features. Others focus on reconstruction rather than tracking, and doing this online means no points can be defined by the user prior to execution. And then there are also solutions that suffer from insufficient precision or require markers on the object, with either one making them not applicable for most automation processes. Our contribution is a very generic approach that is geometry independent and doesn't require material modeling or learning. We propose a representation in which the resolution of the surface and the deformation are independent of each other. This allows to use a highly detailed surface model, leading to high precision, and a coarse deformation model, allowing for efficient computation. The model and the points of interest can be defined offline, which makes it especially suitable for automation processes, because no manual action needs to be performed during the execution time. We implemented a processing pipeline that works in an iterative manner to estimate the object's deformation from each observation. Knowing the object's deformation state then allows for tracking user-defined points on the object. In an offline procedure, the user demonstrates the model and the points of interest, and existing approaches usually struggle with large initial deformations. And we address this issue by demonstrating the object in multiple deformation states, which are then combined in a so-called object library. This only has to be done once for a new type of object. During the online execution, the deformation estimation is initialized with the most similar model from the library. For every iteration of the tracking pipeline, we pre-process a point cloud from the 3D camera by removing outliers and segmenting the object from the environment. In a second step, we identify correspondences between the deformed virtual model and the current observation. For this, we use commonly known projective correspondences, point-to-plane correspondences, and feature matching with a shot descriptor. Knowing these correspondences is the input for defining a nonlinear optimization problem, which tries to minimize the distance between defined correspondences. And additionally, we use a regularization term for the occluded areas of the object, for which we can't find correspondences. The regularization term is a commonly used as rigid as possible approach. The first step of our solver is to do a position update, which is a classic rigid registration. And then we leverage a flip-flop solver structure to minimize the prior defined error terms in an iterative manner. Once the solver converges, the next depth image from the camera is processed, and we continue with the next estimation loop. To close the perception action loop, we integrated an interface through which a robot can request the pose of a certain point at any time. And by calibrating the camera system against the robot, the manipulation task can be executed. But enough of the theory now. Of course, we've tested our solution on an actual robot, which can be seen in the video here. The deformed object is placed into the scene at a random position, a scan is performed, and the best matching model from the library is chosen to initialize the tracking algorithm. Now that the algorithm is initialized, a robot equipped with a measuring tip can move to the user-defined point. The algorithm is executed on simple consumer hardware, and it takes about 1.5 seconds to estimate the deformation. The entire algorithm can be parallelized on a GPU to improve computation time and achieve higher frequencies. This is subject to our future research. Now that the object is moved to a different position, you can see that the user-defined point is again detected very precisely. The average precision we determined in our experiments was 2 millimeters with a relative deformation of 20% with respect to the reference model. In the next step, you can see another deformation being applied, and in the upper corner, a visualization of the converging algorithm. Once the deformation is estimated, the robot can begin with the manipulation. And of course, also a rigid and a non-rigid transformation can be detected at the same time within a single step. So now you see the camera taking another picture, the algorithm is converging and estimating the deformation, and the robot moves to the manipulation spot. For future research, we plan on optimizing our algorithm even further and also benchmark it against public data sets. For today, this is it. I thank you for your attention.
Thank you very much. Very impressive presentation. I have a question regarding the types of objects you can use. Like you said, you need to learn the object once. That seems reasonable, but are there limitations in regards, for example, could you also use objects that are self-occluding, which you then not see everything from your top view? What would then happen to the algorithm?
Well, first off, thanks for the invitation today. I'm joined by my colleague, Benjamin Alt. And that indeed is a great question about the occluded areas. Of course, we can not find correspondences between our deformed reference model and the current observation. And that's why we introduced the as rigid as possible term, which is a regularization term. So for the occluded areas, we assume that the parts that are occluded behave like or in close relation to the parts that we can actually see on the front side. And that allows for a regularization. Of course, if you, for example, have objects that have occluded areas within the objects that can never seen, or which have not a surface that can be seen from the outside during demonstration, then we cannot actually find out any positions within the object. But since we're focusing on surface manipulation tasks, those are areas which are not very relevant for the manipulation.
Okay, thank you very much. Just another curiosity question more, like I'm guessing you are more interested in the commercial viability of this system. So is your current task time of 1.5 seconds or what it was fast enough for that? Or like, can you give an intuition about how fast the robot would need to do this to be viable, to be set into the wild?
Mm-hmm. Well, yes, that's a great question as well. Well, you already realized that we're focused more on a practical approach. So we want to use the algorithm in an industrial environment and actually do real manipulation tasks. So we figured that existing approaches do have issues with a initial large deformation. And that's why we introduced the object model library to actually handle these large initial deformations. And that is part of our algorithm, which is new. And we, in terms of a proof of concept, we implemented this and tested this on a real application. And 0.5 seconds is fairly slow, maybe for a real application. However, we implemented everything on a commonly used CPU. And the algorithm itself, however, though, is capable of being parallelized on the GPU. And we have not implemented it yet, since we just first wanted to do a proof of concept if the algorithm itself is feasible. And since we found that out in our first experiments, we figured that we can now take the next step and put it onto a GPU. And we expect that speed ups of about 10 times to 20 times faster now, which gives us like a range of, let's say, 10 to maybe 15 frames per second. And that indeed is a feasible frame rate for a real world application.
Thank you very much. Looking forward to seeing the next version.
Thank you for the invitation.
Then we're gonna go to the next point, which is the coffee break. We're a bit behind schedule, so we're gonna shorten it a bit, and we're gonna resume at 18:15. So we have now a 10 minutes break, and then we will proceed with the next invited speaker talk. Thanks to all the spotlight speakers for their contribution, and yeah, I hope you still watch the rest of the workshop, and see you in 10 minutes. All right, welcome back, everyone. It's my great pleasure to now introduce our next speaker, Dinesh Manucha. He holds the Powell Chrisman Iper Chair in Computer Science and Electrical and Computer Engineering, and is a distinguished university professor at the University of Maryland, College Park. He's a fellow of AAAI, AAAS, ACM, and IEEE, and he's a member of ACM's ICRA Academy and the SEER Award from Solid Modeling Association. He received a Distinguished Alumni Award from IIT Delhi and the Distinguished Career in Computer Science Award from Washington Academy of Science. He was a co-founder of Impulsonic, which was later acquired by Valve in November 2016. His research interests include virtual environments, physically-based modeling, and robotics. And we are very happy to have this interesting talk here today. Thank you very much, and giving to you, Dinesh. I don't think we can hear you. We can see the slides though, but we can't hear anything.
Can you hear me now?
Yeah, perfect.
Great, thank you very much for the organizers. So good afternoon. It's really interesting to attend this workshop with different folks in different time zones. It's about 12:15 p.m. in the East Coast and US. So I will talk about some of the problem we're dealing with using machine learning for high-def grasping. You know, we've been hearing quite a bit of these ideas since this morning, especially I heard all this spotlight talks in the last 45 minutes or so, and it's really inspired by the prior work. So, you know, high-def grasping, ultimately the holy grail in robotics is, you know, someday we will have high-def hands, just like human hands, or even more dexterous as human hands. And these are problems, each of them is very well studied in robotics, you know, dexterous manipulation. We heard this term so many times today. Someday our home robots will come and do all the jobs we do in our kitchen, hand over this deformable objects like the soda bottle on the left, and pick and place, you know, the holy grail that Amazon Challenge has been picking up for the many years at ICRA and other conferences, Amazon Picking Challenge. So this is still the dream we all deal with. There'll be good hardware, but once there's good hardware, how do we go and pick and place any object we do? So the notion of grasping, you know, this is a classic pipeline. You know, I learned about this when I was a graduate student in the late 80s, and I'm sure that the pipeline has not changed. Use computer vision to localize any object. Pose estimation, you know, depending on the pose, how you do it. Then somehow the robot has to figure out how to grasp it. This is what I call grasp planning. And eventually they execute the motion command for the arm and fingers and everything to move to do it. We call motion planning. So this is the classic pipeline. And in this today's talk, I'm dealing with the grasp planning component. You know, of course, it depends on the left two modules, which are perception driven. I'll briefly talk about them, but especially recently in computer vision community, there's a lot of work on localization pose estimation, which has seen a huge improvements due to deep learning methods. But the focus is grasp planning. So as I mentioned, grasping is not new. You know, as I say, I myself got exposed to many challenges of grasping in the mid to late 80s. For the lack of a better term, you know, if you look at the classic work, all this dynamics, force, friction, for the lack of a better term, it's model-based grasp planner. You model the physics, model the geometry, model the friction cone, uncertainty. And one example of this is something that we use in our work called GraspFit package. There are other pattern packages available, but you know, this is the kind of method you're given a virtual object, GraspFit can generate the pose for different thing. And I don't know if you can see the slide on the left. On the top row is a 4-DOF gripper, but on the bottom row is like a human-like hand with about 20 degrees of freedom. So in this talk, I really want to focus on high-DOF grasping because some new challenges come from it. And especially in the last 5-6 years, clearly there's been a huge attention on using learning methods, deep learning method, reinforcement learning methods, very active area of research. And I'm sure every time we go to robotics conference, we see exciting papers on this thing. The only thing I would say is that at least in our work, which we started more than 2.5 years ago, we found that most of the active grass plotting methods are for low degrees of freedom. So the focus of my talk today is high degrees of freedom, and I'll tell you what challenges come up in that context. So before I go deeply into grasping, I'll just spend 2-3 minutes. This is what you will learn, a little bit of review, maybe in your undergraduate class on robotics, or even a graduate class on grasping. Because ultimately, you know, whenever we take these classic methods and when we design a network or a learning-based solution, we try to design a learning, you know, like some kind of a network or some more end-to-end unsupervised method, which is trying to model these issues of kinematics, wrench, friction cone, and grass matrix. So having this knowledge and using it to design learning is probably not a bad way to do things. So clearly we talk about degrees of freedom. You know, as I said, the focus of this talk is something like 20-25 degrees of freedom. So you got the basic kinematics, you know, this is something you learn in the introductory, take any introductory book on robotics, they talk about the second chapter, third chapter will be kinematics, you know, and all the way you deal with the degrees of freedom, especially on these arms. The notion of a wrench, you know, which is basically this we call WI for lack of a better term, the force and mass, and you can see how you place the grasp around, you hold the object at different contact points, and based on that, you figure if it's stable or not. Friction is a very big part. Now, there are a lot of friction models. I would say that some of the most widely used is friction cone, though some of my friends in physics will always argue that it's not the most accurate, but for the time being, I'll just stick with friction cone. If they're better models, we can definitely learn from them. And, you know, you compute the friction cones at all these contact points shown as C1, C2, C3. And ultimately, you take the wrench and friction cone, you know, and you compute what is called the multi-finger grasp matrix. So this multi-finger grasp matrix computation object is something, as I said, known since I learned in the 80s, and I'm sure the ideas are known even before that. So it's a very classic concept. And you're given the grasp matrices. So ultimately, in many ways, you know, this grasp problem corresponds to the computation grasp matrix. And finally, if you're given an object, you know, arbitrary shape, the grasp post computation comes out to be, you know, that is described by the grasp matrix and the friction cone. So the output is basically in a classic method is compute the grasp matrix and the friction cone, which are, you know, do it. Again, I will not bother you with the notation, especially it's evening in Europe or late in the day, but just keep these two terms in mind, you know, the notion of grasp matrix and the friction cone. And there could be multiple contact points depending on how many fingers you have. And of course, what we've always told, you know, is try to compute a force closure grasp because, you know, it's more stable and it can, you know, resist any applied length. And there are a lot of criteria known for force closure grasp. So this is just grasping 101. Now that we all understand the terminology, so the thing that grasping has come up with a lot of work on different metrics, the Q metrics. And I'm sure I've seen surveys on different metrics. So I don't want to get the debate of what's the best metric. All I would say is that for this work, we use a Q1 metric. There are other metrics, we can plug it in. we're not really married to that. This is a classic metric. It was actually done by, when I was a graduate student at Berkeley in the late 80s, early 90s, John Kennedy was my advisor. And I still remember Carlo Ferrari was visiting student from Italy. They wrote this paper. It's a very well-cited paper that defined the Q metric. So this is, you can see 29 years old, wonderful paper. I think it was ICRA 1992 in Nice, if I remember correctly. So that Q1 metric is you take basically this convex hull that proposes metric. So this is the basis we're using. All our formulation is based on Q1 metric. A lot of loss function and things we have done. And if you want these other metrics, we can try them out, you know, but there would be issues in using them right there. So that's clearly the point there. So what I want to talk about are two different works we have done. They're both on addressing the problem of height of grasping. First, we worked on a supervised method, design a neural network, especially taking into account some of the challenge of different loss functions. This was in IROS about a year and a half ago. And then last RSS, which was in 2020, which became online, we brought the notion of deep differentiable grasp planning. You know, these differentiable methods, learning methods, been a very hot area. It's been used in different fields. So we want to generalize those ideas to, you know, grasp planning and see what we can do. So most of the work is here. Both the papers are online, and, you know, you can refer details out there. So here's a holy grail. You're given a, you know, some object on the left. You see this, you know, these boxes. we'll see, we could be given depth images, or you could be given some occupancy grid, like a pose, a perception input. So this is what our robots see as an input. In this work, you look at like a voxelization representation. And on the right-hand side, we had this shadow hand, 25 degrees of freedom hand in our lab. Figure out the good grasp, as you show this, and I'll show you a video of showing of, picking up this, box of sugar cubes with a high degree of freedom arms. And you want to basically perform this computation very fast. So what really happens, as I said, grasping is not new, and machine learning and grasping is not new. But if you literally go to take the previous methods and go towards height-of grasping, let's look at what they really do. First of all, and if you look at most learning methods, they have this pipeline. You sample many grasps, and then you score them with the grasp quality metric. Of course, if I'm using Q1 metric, I'm claiming the Q1 metric is the best one. But previous method could not do height-of form, because especially with high degrees of freedom grasping, you get too many valid poses. And that, while it gives you redundancy and a lot of poses, it confuses your network. Having too many poses become what we call the graph ambiguity problem. So this ambiguity problem, at least we found the previous method did not handle it well. So this ambiguity actually makes it harder to train. Like just I show this example of a bottle with this human hand, and you can see I'm showing 8 valid poses here. So on one hand, say, hey, compute any one of them. Of course, we can label them based on Q1 metric and do it, but this is how things go. The second big problem is collision avoidance. We don't want, we want to compute a grasp which is like stable and at least in the virtual model doesn't penetrate and deal with all the inexact and all this value grasping. So this is another problem. One is the height of ambiguity. And secondly, some of the collision avoidance problems get more complicated in the context of height of grasping. So the first assumption we make, you're given some input. This is basically a computer vision pipeline, something that we just borrow from literature. You perform a segmentation on the object, which is getting pretty mature. There are very good solutions available in computer vision deep learning. We perform a simple Poisson reconstruction. And for this work, we just assume we're given like a nice voxelization. You compute a 3D grids of voxels, and you kind of occupancy. So given an object on the left, the sugar cube box, the representation fed to our network is this right-hand side, this shift here. So this is the pipeline on the network, which I will not details, why we did just so many layers and convolutions. You can see the papers there, but except the input is the voxelization on the left here, and the output is the friction cone we compute. And then we kind of do a post process, like a post refinement, to make sure, there are no penetration. So computing a absolutely collision penetration free grasp with network is very hard to guarantee. Some machine learning has some limitations. So we said, okay, let's do the refinement based on, after that, so that we guarantee it. So this is the way we overcame this problem was basically we used GraphSpit to compute the synthetic data set because there were not too many data sets. And just to deal with this ambiguity problem, we started chasing lots of best poses. Again, best based on metric, and our metric is Q1. If you have some of the metric, you're welcome to use it. But imagine for each object, we compute lots of objects and lots of poses. And this could be a synthetic CAD model, or it could be the database available real world objects, a bunch of them are available and you can use them. So, but the point is in our synthetic data generation, we generated lots and lots of poses for training. Now, this is example of, how we do it. We basically compute objects on the top left and voxelization, we rotate them. And, we try to basically do a lot of data augmentation. These are just numbers done by experimentation, but the goal is, whether 100 poses, 27 different angles, we really wanted to, sample the object from all possible positions and orientation and see what goes on there. So the real challenge was to design the network, and, a big part of the network are the loss functions. If you look at any deep learning papers, this loss function are somewhere the number of layers you do and the loss function are the two big challenges. So one was the consistency loss to handle it. And it has basically what we call it, like a function, the neural network output for the ith object, which we try to minimize here with this difference. And the grasp ground truth, you can kind of basically see the kind of function that the loss function we're trying to minimize, what the neural network output would be given by the function f, and what the ground truth would be. Now, this is what we attempt to do, consistency with this thing. And this is the number of objects. We kind of normalize it over there. The second thing was the two function collision loss. So again, you're given a pose on the left, you compute this metric voxelization. And again, you have all the grasp points on the top right hand. You see with each finger and each link on the finger, you get the links, and you basically go and deal with them and see what happens there. So this is a loss function here. Again, you can see what we're doing here is given the neural network output, the function f, the pose on the left, t, the function f, and you try to basically minimize it using a science distance function. Ideally, if this function is 0, life is wonderful, but of course, in the real world, it'll not be perfectly 0. This is how we try to perform with optimization. So this is just the details. Again, I will skip the detailed math, but the paper will give you the formulation of how we took the pose and perform this computation. So at the end of the day, you take this consistency loss for the ambiguity problem, collision loss, you combine them. And in this case, we do a simple linear, or even I would say convex combination of the two loss function, consistency loss and collision loss. Of course, how do you weigh them? And there is no perfect method. We did some trial and error, and I'll talk more about this towards the end, which affects the performance. But the holy grail was to take the two loss functions, formulate them, and combine them in a manner to get good results. So this is just showing post refinement. If you see on the left, you see all the friction cones at the contact points, but there are some penetrations on the left with the red thing. But with the refinement, the amount of I would not guarantee you still is penetration free, because high degree of freedom posed with the penetration free by itself is a hard geometric problem, optimization problem. We did a lot of work on that. So giving absolute guarantees of penetration free are still not there, but we can significantly reduce the amount of penetration. So this is just the examples of this L2 loss function for the consistency. So we tried two different grippers, the shadow hand with 25 degrees of freedom, and the popular Barrett hand with 11 degrees of freedom. And you can see the residual on the training set on the right and the test set. So we saw the good thing was the different residual of this loss function on training and test set was not bad, not too significant. And of course, you try different loss function, which is very typical in a deep learning paper. People want these kinds of evaluations and ablation studies, and you can find in our paper that there's a classic L2 loss. You'll see there the consistency loss by itself, and the rightmost column is a combination of consistency and collision loss. And the beta parameter, the convex combination, we basically did it. You can see here like at 0.75. So we put like 75% weight to the consistency loss and 25% weight to the collision loss. So this is one experimentation we have done. Different number will come up, but you can again see, how the functions are really behaving right in different settings here, right there. So other point is, the penetration. As I said, guaranteeing absolutely collision free. You want to touch the friction, but no penetration is still a hard problem with deep learning methods. And at least you see, if you just do the consistency loss, penetration is a little bit on the orange on the left. But if you combine them with the collision loss, that goes on significantly. So here are some examples. So these are synthetic data sets. We voxelize them. You can see the voxelized shapes. And so these objects you see, these 4 different objects, different poses. So this was not in our training data set. These are totally, the new test data set that we have not seen, and we do it here. And this is just comparing with like the best synthetic method. Again, one of the better synthetic methods, grasp it. Clearly you see the numbers. So this is what synthetic method would have done, which is in some way the state-of-the-art method. And you can see, what our pose method does. So, the results are, you can see the numbers for yourself and see, our numbers are of course higher. We can't be as good as grasp it right now, the training, but we're getting close to it. Let's just put it this way. But these are all the different shapes. You can see we tried the hammer, banana, airplanes with high genus. We tried a lot of complex objects, even the torus with something. And you can see, that this is the examples of other example here, and this is the method here. And you can see, our method can really handle this method so quite well. So this is also very promising. And again, more examples, because any deep learning method has to do a lot of evaluation. We got lots of data sets. And again, you can see the graphs being computed here in the synthetic. We integrated with the shadow hand. You can see all kinds of mustard oil bottle, cans, apples, sugar cubes, and cups, and different objects. They're all new objects, and our method does quite well. So let me play a video here, and you can see it's acting. The video is played at 2.5 times. Of course, the actual grasping doesn't work as fast. This is 2.5 times slower than real world because the hand doesn't move as quickly. But you can see, how we put the neural network integrated with the shadow hand, and got the model of the object done, and it works reasonably well. That we are able to compute reasonably stable grasp. Of course, all the hardware are dealing with these big hands. That's a whole story. My students spending long nights and dealing with hardware. That's a separate big problem. But you can go and grab this this plastic banana that what you see in homes, and again you can see stapler. So we tested quite extensively, and the fact we tested a lot of synthetic and real world objects, including this. You can see genus 1 torus-like shape of the duct tape, and it can figure it out and do a pretty good job. So this was quite promising. So this is the first part. The second part is dealing with what we call differentiable grasp planning. Differentiable has been a hot topic in learning. And you got, in this case, I inputted a bunch of input images. You use ResNet. And again, you compute the friction cone and you compute the differentiable loss. So what does differentiable grasp planning, why do we want it? We at least had seen a lot of differentiable ideas being used other learning methods, but not so much in the grasping till about 1.5 years ago. And you differentiable loss. So at the bigger sense, it's an end-to-end algorithms. But the idea is that, we use the classic forward, backward order differentiation for each of the components. Remember I showed you this kinematics, this collision, and the grasp metrics. We use Q1. Now, one idea was to come with a metric which is differentiable. So we extended the Q1 metric from Ferrari and Canny, make it for better generalized Q1 metric and make sure differentiable. Secondly, we made sure is that we have this sensitivity analysis optimization formulation, which can perform the derivative computation, like the first order. How do we do it? This is designed for multi-view methods, and actually over supervised baseline, having the differentiable component give us 22% higher success rate. So this generalized Q1 metric, I will not give the details of that, but it's basically extend the Q1 metric, and especially the coarse-grained metric here, but it really has locally differentiable even for an exact graph. That we proved that. It's based on some optimal conditions. There's a classic paper by Joel Burdick in 1993. We built on that, the optimality condition, perform sensitivity analysis, and really get good results this way. So again, for the lack of detail, I'll just show you the 3 components. Is the loss function, there's the quality loss function, collision loss function, and the data on top of the differential metric, how we combine them. So the thing we realize in this quality function is, is like the exponential damping of the quality metric. That's the key observation we really observed, that Q1 is our generalized Q1 cost metric, extension of Ferrari or Canny, but we take into account the exponential decay as a E minus Q1. And the consistency and self-collision loss are kind of similar to what we presented for the previous one. So besides the differentiability of formulation, here we add this quality function in this differentiable grasping method here. And the generalized metric, as I said, one of the idea was to make sure, because having perfect touching gripping without penetration is not easy. So we try to make sure even if an exact grasp is not perfectly touching, you can still define the differentiability. And as I said, the key idea was this contact range exponential decays, which we did in this quality metric shown right here. So this is what it comes up to be here, and this is how different metric comes out there. Again, this is the classic metric. Again, for the lack of time, I will not go into the details of that, but we take the range function here, take the top term, and actually in the generalized metric, we extend this by adding this, you can see this exponential component. This is what really the change we have done. And this is a metric we show has differentiable property with respect to an inexact graph. That's what really makes us enable us to do this differentiability criteria right here. So this is the overall metric, just extension of Ferrari and Canny to generalized metric. Again, the bigger term extension is in this term to do these computations, and we get its upper bounds right here. So this is the different formulations here, which is again the paper has all the details. You can see it. The collision loss is slightly modified again based on the pre-version and the differential formulation based on this exponential formulation again with the beta term and the DPI, the distance term here, which is shown right here again based on the formulation. My apologies for going through details, but give you a high-level idea of what's going behind the scenes right there. And the self-collision, again, we want to grab them and as well as avoid the self-collision. So you can see we take a lot of sample points on the surface of the gripper and literally, avoid collision with them. So the two versions of this method we did. First thing, it enables us to compute a totally self-supervised graph learning. So if you have even no labeled data, on the top row, you got the initial rows of these objects, and on the bottom row, we compute them. So this is purely a self-supervised version. It works well, but at least, this is probably one of the first self-supervised high-def graph learning. But in this case, you can see, this thing, but also we found out, well, self-supervised is good, but if you have a small label data set, like a small supervised data, we can do like combination of the previous version, which is self-supervised and small label data set. That's what we have done. So our best result, I'd say, is still taking the differentiable grasping, have the basic self-supervised pipeline, but at the end, we do bring a small supervised grasping data set, and you get those results on the right-hand side. So again, you'll see even more complex shapes in this version than the previous version. And again, all implemented on the shadow hand, and this is all novel object. Nothing like this with database training in the small supervised data set, but you can see we can do complex objects again. And again, this is the same, we mounted the arm, the shadow hand on the UR10 arm, and you can see these are in some way probably more complex objects than I just showed you, just 10 minutes ago in the supervised learning method. You quite see the pipeline is slightly slower, but we were quite happy that the method was working. This is the objects in our lab right now. Of course, we need a lot of real-world testing with lots of real-world perception problems. But you can at least see this is till about last summer was the state of the art in high-def grasping using this learning methods, supervised and differentiable. And then, at least in this case, we don't need a lot of label data set. That's what differentiable grasping buys out right here. So this is it. Let me just try to conclude and see if you have time for a few questions. So I present you some ideas of high-def grasping. First was graph poses high neural networks. And the two problems we addressed was specifically to high-def grasping, the ambiguity problem and the collision avoidance problem. I presented both our consistency and collision loss function to deal with that. And we also generated a data set, especially, we went for lots and lots of poses and lots of best graphs. So literally we had a very rich synthetic data set to make it happen, which clearly took a lot of time. And then we introduced one of the first version of deep differentiable graph planner using the classic notion of forward-backward automatic differentiation. Currently, all the differentiability properties, what we call the generalized Q1 metric. We have a basic unsupervised method, but we can also do a small data set and do a supervised version, which gives only 2% improvement. While the results are promising, there's still, high-def grasping still is a challenging problem. It's going to keep us busy for a long time. Clearly, we tested on simple benchmarks in our lab. If you go to the Amazon kind of packing problems, there were many more challenging. We didn't have models of them. And also, I think we need more benchmarks. I think most of benchmark for low, but what is high-def benchmark for learning methods? We just tested the shadow hand in our lab. That's what we had. I'm sure many of you have much better hardware in your lab will do it. And then there's a whole discussion of metrics. As I said, something we use Q1 because we found it simple and good and we could generalize it. But I'm sure some of you got objections to the limitation of Q1 metric, the other metrics. And the question remains is that for the first supervised learning method, we could do it. But for the second one, can we prove the differentiability property? And I cannot promise that. That depends on what metric you have. And especially in exact graphs, in the first method, we voxelize the object with some segmentation and this thing. In second one, we assume you're given a lot of depth images, and lots of depth images. And if you're given partial perception data, ultimately, you want to end-to-end pipeline, which is right now, perception done with one deep learning pipeline, grasping is done with them. Can we combine them and overcome these problems? And finally, with all the deep learning methods, including ours, the parameters, the most dominating parameters we found was how do we perform relative weights between the consistency and collision loss? Most of the results I show with 75% weighted consistency loss. So this is where things are there. There's still a lot of work to be done, and I don't know how much time I have for questions, but I'll be glad to take any questions or any feedback on the talk.
Thank you very much, Dinesh. Very nice task. We have indeed a question from the audience, and it's about cross-quality metrics are well established for rigid objects. How do you think it could be extended to deformable, e.g. textile-like objects? And most of all, how to use them then?
Yeah, that's a great question. You're absolutely correct. All our results are for rigid objects, for high DOF. And deformable object by itself, honestly speaking, cloth, folding cloths. I don't have especially if I want a metric which is differentiable, I don't have a good answer right now. So could we extend Q1 or something else? It's a good question. I haven't tested well enough and we don't have a good enough answer. So I would say that is still an open question at the moment.
Thanks. Maybe we can discuss something like that also in the discussion round. We just got another question from Martin Sundermeyer. Can the network predict multiple different graphs per object, and how much do they vary?
Yeah, so definitely, just like, remember network was trained on, let's say, taking 100 different graphs. So yes, network could compute, if you change the condition slightly, pose a little bit, it could output a different graph. And, depending on the noise. How much do they vary? We have not tested well enough yet. But I cannot rule out the fact that you make a small perturbation in the input. Remember, you're given the depth images or some noise comes in the input, because the network was trained on a large number of synthetic graphs. So in theory, it can lead to a different output. Yes, that's definitely a possibility. And that again is something, how to make it robust, because we don't want behavior. That is also a good point there.
Thanks. Then I have a last, more curiosity. You presented this beta, which was set to 0.75. Can you give a feeling how sensitive this method is to this beta? If you tune it differently, will it still work kinda, or how sensitive is this weighing of the two losses?
Yeah, so if I pointed the paper, we address some of those issues. Again, if it's a small change, but if you go from 0.75 to 0.25 or 0.35, you can expect very different outputs. So I think, again, this is all this, what you're asking are all this holy grail question in any machine learning solution, where finding rigorous bounds and guarantees is always hard. So yes, for large beta, it can vary, but small beta, if you look at the paper, we have some experimental results on how beta affects the results.
Nice. Thank you very much. And we're going to hear more from you during the discussion round.
Yeah, they'll be at 30 minutes from now, right, I believe?
Yeah, after Jeanette's talk.
Yeah.
Great. Look forward to it. Thank you.
Thanks a lot for the talk. And now it is my pleasure to introduce Jeanette Bog, who is an assistant professor of computer science at Stanford University. And she was a group leader at the Autonomous Motion Department of the Max Planck Institute for Intelligent Systems until September 2017. And before joining the Max Planck Institute in January 2012, Jeanette was a PhD student at KTH in Stockholm. And she also studied at the Chalmers in Gothenburg and at the Technical University in Dresden, where she received her Master in Art and Technology and their diploma in computer science, respectively. And Jeanette has received several awards, and most notably the 2019 ICRA Best Paper Award, the 2019 IEEE RAS Early Career Award, and the 2017 IEEE RAL Best Paper Award. And research focuses on perception and learning for autonomous robotic manipulation and grasping. So thanks for being here, and the floor is yours.
Thank you, Martina, for the kind introduction, and thank you for the invitation. Really appreciate it. And tell me if you don't see my slides, but I hope it works out.
Yep.
Yeah, so today I thought I'm going to talk about bridging topology and geometry and deformable object manipulation. And I specifically focus on linear deformable objects. These are hard enough, but I just want to give you a feel for why this is an important problem. So the ability to manipulate ropes and similar objects and tying knots with them has quite a few important applications in our lives. So when people are injured or are in surgeries, Doctors need to stitch the wounds with medical sutures, and this is a basic skill for surgeons. And automating this step would allow the surgeons to focus on more challenging things and potentially save more people. Rescue workers heavily depend on ropes and metal rods to rescue people from high-risk environments. And we could put the Boston Dynamics robot, for example, or any kind of these walking robots in these high-risk jobs if the robots know how to use these ropes, for example. So let me first start with addressing like one particular problem, or focusing on one particular problem, which is the perception part of manipulating a rope. And here's the first example application that we want to achieve that I will use through the first part of this talk. So what we want to do is that given a goal image, we want to replicate it with a different whatever rope that you see. So here you have the robot basically starting from some rope that looks also completely differently from the one that the target image or the goal image is given. Then it basically brings it into the right shape. And so I will start with talking about how we achieve this. So first of all, this is quite a challenging task because there are lots of sources of uncertainty. So the sources of course, a rope has a very high dimensional state. And there's lots of sources of uncertainty coming just from perception for inferring that state from images. So there could be occlusions during manipulation. The rope could have varying appearances, and also the environment may have completely different looks. There might be clutter in the environment, and so on. So another source of uncertainty for this kind of task is in the dynamics of the rope. So it's actually quite hard to predict, not only quite hard, but also quite expensive to predict what a rope will exactly do or how it will deform once the robot grasps it and moves it around, right? So this is also very hard to model and introduces uncertainty in this process. But we want to achieve this task that I showed you before of bringing a rope that is in front of the robot into a particular goal shape that is shown to it in form of the image. And so that task, because there is so much uncertainty, requires continuous replanning and real-time feedback on the state of the rope with respect to the goal state. And so we use a state space representation of the rope. So basically the position of each of a number of points on this rope. And other people have used learned latent representation, but we actually decided for the state space representation because it allows for easier planning and easier inclusion of physics priors. And so this is really an overview of the approach here, where we assume we have some perception model that can give us this state space representation. And then this is fed into a dynamics model to basically optimize a sequence of actions for the robot to actually achieve that goal state. And so one of the main challenges, or one of the core challenges, as I mentioned, is how to robustly perceive this rope despite all the aforementioned challenges. And the main contribution of this particular work I'm going to talk about first in this talk is this perception system. And so what is at the core of this perception system is a differentiable renderer with self-supervising with a self-supervising objective function. So this renderer gets as input an image that you see here on the top. And the output of this perception network is, which I will actually not go in detail to, that one also has a bunch of contribution, but let's just say it's a perception network that takes the input image and outputs the state of this rope. So now we render this state in this simple grayscale image that you see here, denoted PUV. And given this rendered state, we can now form a mixture of Gaussians of the foreground and background model here, and then compute the weights for this, given the compute the weights for the new image or for the current image, given this Gaussian mixture model. So that's what you see here described as the PUV nu, okay? So now using this rendered foreground background model and the foreground background model according to this GMM, we can now backpropagate and either adjust the rope state or fine tune the network weights online. And then therefore basically come up with a better estimate of the rope state. And so what is important to note here is that this model doesn't assume anything about what specific color or appearance a rope has, or the background even has. This the only assumption, or the main assumption that we make here is that there is a good contrast between the foreground and the background color, but the actual parameters of the appearance are transient parameters that are captured in this GMM. Okay, so now here's a visualization of how well this method actually works. We just started with some qualitative examples using a manual initialization, and we compare our method that has this expectation maximization loss actually with an L2 loss that just looks at appearance in the image. And you can see from top to bottom an increasing, or actually from left to right, you can see an increasing amount of difficulty in terms of visual complexity of the scene. So the first row, you have like two examples where there's like basically just a rope on a uniformly colored table, more or less, and it works quite well. But then in the second loss, you already have the robot actually doing manipulation and therefore occluding parts of it, or you have an appearance that's actually split into red and green. You have examples where you have multiple ropes, where you have other distractor objects in there. And we also took like data sets here on the top right is like the data set from Berkeley that we haven't recorded ourselves, and our method works on this one. So this is just like a qualitative impression that I can give you of what this method can actually do. And one question I always get is like, can it handle intersection? And yes, it can, because we actually use a tracker. So a filtering method basically is underlying, and therefore can actually basically estimate the state of the rope online. And so what we get is essentially what I've already showed you before. So here again, we give the robot this goal image that is done with whatever rope, and then it has to bring this rope that is in front of it into the particular state. And what you see here, what is kind of interesting is that it really doesn't just attach the end effector to some point that it wants to move, but it uses the rope dynamics that are actually quite complex and under-actuated to achieve as much deformation towards the goal as possible, right? By not directly attaching itself to the points it wants to move, it actually uses the dynamics to get closer. Yeah, so, and also observe that the rope is being tracked while it's actually occluded and all of that, right? Okay, so this was kind of like just a brief outline of this work that we had published at ICRA 2020 and in RAL. And just to summarize the contributions of this work, basically the main insight that we use is that representing the problem in state space makes planning, especially, and including dynamics models, actually easier. And for the algorithmic contribution, we proposed this differentiable renderer that I briefly showed you for self-supervised learning and robust state estimation. So we also didn't need any kind of hand-labeled data that was collected in the real world. This was done in a self-supervised manner. And the result you've seen as a system for manipulating deformable objects, or in this case, deformable linear objects into a given goal state. All right, so this is the work that basically solves, in a way, the perception problem for us of these deformable objects. And of course, it was still only doing the manipulation of a rope kind of in the 2D plane, and brought this rope into the shape, into this 2D shape in a way. So what we wanted to do next is really to do knots, like to basically have the robot perform knotting tasks, which are, of course, not only visually more complex, but specifically more complex in terms of planning and execution of this, of whatever the plan is. So again, like one of the challenges is that a rope is very high dimensional in both in state and in action spaces. We are actually, you could model, for example, by finite elements, and you could have like, I don't know, 100 degrees of freedoms, for example. It could be infinite, actually. On top of this, knot tying is more challenging than, for example, what I showed you before, because knots are abstract topological concepts, and there's no analytical function that really defines the distance of the current geometric state that a rope has to the final topological state that you want to achieve, right? So, for example, for these, if you consider the two rope states on the left, which function can tell us that the bottom one is closer to making the intersection shown on the right, right? Or, and I want to also mention here that this intersection, you know, it's a representation of the topological state, not of the geometric state. So what makes things worse is that knot tying requires a long sequence of actions, and therefore motion planning needs to plan over a long horizon. And there's, of course, an exponentially large search space for finding the right plan. Right, as you see here. All right, so there is, of course, some related work that has already looked into this problem. Here's, for example, a work that applies sampling-based motion planning to knot tying. This work by Saha and Isto uses tree search, and they use knot theory to prune out unpromising branches, but we still found that it takes hours to just find a single plant. And a more recent work generates visual plans by embedding images into a plannable latent space using causal infogans. And the latent space has a simple dynamics model, and plans can be generated by A-star search. But the method has not really been demonstrated for knot tying. And also, again, like this is a latent representation, and it's harder to actually include more realistic dynamics into it. Okay, so an alternative way is to learn trajectories of knot tying by imitation. And this work by Vandenberg and Miller learns and improves human demonstrations for a particular knot. But the learned trajectories cannot be used for other initial thread configuration or different knots. So it's kind of like hard to generalize. But the idea of using imitation learning is actually also quite interesting. So we propose a method that takes advantage of knot theory, sampling-based motion planning, as well as learning-based methods. So we can kind of take the best pieces of each of these works. And so knot theory helps us to compose knotting tasks into steps, as I will explain later. And each step is a topological action. And this decomposition makes each step shorter, thus easier to solve. And moreover, motion policies for each step can be reused for different knots. And in fact, when humans teach knots or knot tying skills, such as the instruction GIF on the right, we use very similar decomposition according to the topological plan. So, right, so this were just the points that I just made. And then we learn probabilistic motion policies for each step using reinforcement learning and imitation learning. And initializing the motion policies with imitating demonstrations helps bias exploration of reinforcement learning. And reinforcement learning allows unsupervised interaction on more diverse rope configuration and improves generalization on top of imitation learning. So at inference time, the motion policies for each topological step is used in a tree search to plan for the entire net. So we would always find a solution, although the learned policies are not necessarily perfect or failure-free. So here's an overview of the solution that we are proposing, and it has 3 levels. On the top level, we start from an untangled state. And the goal of the rope, as you see on the left side, and the goal topology is given. We decompose a knotting task into steps by searching for a path in this graph defined by topology. And on the second level, we use learned motion primitives for each of the steps. So the motion primitives take the geometric configuration of the rope as input and predict distributions of robot motion trajectories that accomplish the required topological changes. And then during planning, we validate the success of the predicted robot motion in simulation and to record the motion of the rope. And then on the bottom level, we try to produce the same rope motion on the real robot. And in this work that I just showed you before, we have developed a perception model that can estimate the geometric configurations of rope from images. And a neural network rope dynamics model that is 40 times faster than the simulator, which I had not talked about before, but I'm happy to talk about it later if anyone has questions on this. So we use this perception model in visual tracking and model predictive control, or the perception model we use in visual tracking, and then the neural network dynamics model we use within model predictive control to produce the desired rope motion and tie a knot. So our method is able to plan for an overhand knot within 1 or 2 minutes and execute the plan on a real robot. So here you basically see the setup that we have is just like the one before. And then here you see basically the motion plan that was generated. And on the top right, we show the RGB image to the robot. And in the middle is the estimated rope configuration. And the orange arrow is the action that is being executed. And the motion plan is adjusted between topological steps, as shown here, to improve robustness to the dynamics difference between simulation and the real robot, because the rope will not exactly do what you wanted it to do according to the plan. So we finally get this overhead knot. Okay, so with our method, the motion primitives trained by tying an overhand knot can be used to plan a pentagon-like knot from the overhand knot. In this example, the motion primitives find a motion plan within a few minutes, right? So this is this promising extrapolation that we were hoping to see. All right, so to explain the technical details now, we need to introduce the concept of topological states and topological actions. And the topological states describe self-intersections in the 2D projection of a rope. The order of encountering intersections while traversing the rope, as well as the vertical ordering of which segment is on top of the other, are recorded as the topological state. Okay, just like it's visualized here in this little animation. So topological states are abstractions on the geometric states of rope. And so imagine the geometric state space of the rope extends over the entire screen, right? And then topological states partition the continuous state space into these cells that you see here. And geometric states in each cell all have the same topological state. For example, this pair and this pair. And when we cross boundaries, intersections are being formed in the rope state or removed, which are basically these topological actions that we're trying to learn motion primitives for. So going back to the graph, in the system that I've shown before, we used, this is the graph we used on the first level of our proposed system. And the graph nodes correspond to the cells and edges. Are the topological actions connecting neighboring cells. The first level of topological planning tells us the cell we need to traverse and walk through. For example, we may need to travel from the light blue cell to the dark blue cell in order to go from an untangled state to this particular rope state that we want. Okay, cool. So now we have this plan. And in the second level, we want to find the robot motion trajectories for each of these topological actions that are conditioned on the geometry of the current geometry of the rope. And so in other words, we want to find a trajectory in this geometric state space, so the pink line here, that goes through the two cells and satisfies the kinematic constraints of the rope and the robot. So what we will do is we will learn a distribution of robot motion trajectories that can succeed at this desired topological action. And it has to be conditioned on the initial geometric state of the rope. We limit the space of robot motion trajectories to splines with 3 control points. One example here is shown in green on this rope. And the robot will grasp the rope at the first control point, move along the spline, and release the rope at the third control point. That's how we parameterize the actions. And the choice of letting the robot move along splines reduces long horizon RL problems to basically banded problems and avoids instability issues with common RL algorithms that are more like feedback policies. And since there are many topological actions, we want to learn models that can generalize across those. And therefore, we define topological motion primitives as the function that takes as input the rope geometric state and the topological action parameters, and then it outputs a distribution over these splines. And so remember, the splines are the trajectories that the robot end effector has to follow for doing that topological action. So we designed a joint representation of rope geometric state and topological action parameters as input to the motion primitives. And the representation helps the motion primitives to learn similarities of motion trajectories we observed among human demonstrations of different topological actions. And it facilitates generalization across different topological actions. So I kind of have like 3 minutes left, as I see in my talk. So I'm afraid I may not be able to explain all the details of this. It's actually quite complex. But maybe I try. Let me first explain the categorization of the topological action and their parameterization. So there are 4 categories of topological actions. These are called Reidemeister moves. We just called them here R's. So it's like these Reidemeister moves 1, 2, 3, and then also a cross action. And within each categories, there are many different actions. And here are just some examples. And the 4 actions on the left are all one actions. The first parameter is all 0 here, which indexes which segment is used to form a new intersection. And the second parameter that is just highlighted right now is the direction of the new loop shown on the top. And the third parameter is the sign of the new intersection shown on the bottom, so whether it's on the top or on the bottom. And the 2 actions on the right are both cross actions, and they're like kind of similar parameterizations. So we exploit symmetries between different actions. And so one is spatial symmetry of the dynamics. So we can use this and reduce topological actions by just mirroring and all of these things. I don't want to go too much in detail. And the second type of similarities is in the locality of motion policies. Humans actually have a very specific strategy to do this. For example, they usually grasp the middle of a segment that will be on top and move towards the middle of the segment that will be underneath. And we basically encourage this kind of behavior also by having designed a specific neural network. And I think I just don't have the time to actually go through this. So it's pretty complex, but to encode this state. And I would just encourage you to check out the paper for more details. But basically, the output is this distribution of splines. And by using some geometric transformation and the 3-part representation that I just showed you, we can learn to solve all the topological actions. Yeah, as you can see here, this is kind of like a nice visualization of how we group them together. And it's kind of slow. Let me see if I can speed this up. Mongyun, who made these slides. I just want to make a shout out to her, how much work she put into this. Okay, so so we have like the 4 motion primitives that now encode many different topological actions, that also helps in planning. And I also have to let that play. Sorry for this. I can't speed this up. All right, so this is how we do the training. It's based basically on QTR, and we add basically an actor network because we found that CEM cross-entropy method is insufficient in the 6D action space that we are actually looking at, which is the spline space. And the actor network predicts this Gaussian distribution that initializes the CEM process. All right, so we train this also with demonstrations, and then we basically, for each motion primitive that is trained, we will chain them together according to this topological path that the research found, and fine-tune them jointly. And by doing this, we encourage the motion primitives to generate motions that not only succeed at the current topological action, but also makes the next topological action easier in that plan. That turned out to be actually pretty important to do, right? So of these 3 different geometric options, the middle one is really preferred. And so then we do this tree search. As I told you, we are actually rolling out a bunch of options here, and maybe don't like a specific one because it's not really useful, and finally complete this tree search. So for experiments, we trained and evaluated 8 topological actions that are highlighted in this figure. And we just, I just want to show, like, these are the 2 hypotheses that we tested in our experiments. And one thing we found is basically that basically for unseen starred configurations, a naive baseline does really poorly. And imitation learning helps somewhat, but really combining these 2 and using RL to fine-tune the demonstrated trajectory makes a huge difference. We also evaluated whether the actor is actually useful, and it is. Big surprise, maybe. And then one thing that was also extremely important was to fine-tune each of the motion primitives through the entire sequence of the plan, because as I showed you, how well a motion primitives actually is executed depends on the geometric state it starts to. So it really depends on the prior motion primitives. So fine-tuning it within an end-to-end within an entire plan was really important. Okay, so to summarize, we approach this complex manipulation problem of knotting by first decomposing this complex knotting task into stages, and each stage will be easier to learn, and these stages can be composed to solve different knotting tasks. When learning for motion primitives for the topological actions, we observe similarities of motion policies from humans and facilitate learning of this similarity by designing the joint representation of the rope's geometric state and the topological action parameters. And for imitation learning and reinforcement learning, we use both actor and critic networks to improve the success rate. Joint fine-tuning of the topological motion primitives further improved search space. So thank you very much for your attention. I really would like to thank all my students, specifically these 3 who done this work, and I would also like to thank my funding sources.
Thanks a lot, Janet, for the really nice talk. And there is a question on Slido, and Naga is asking, how have the contacts been included in the model? Is there any minimum number of contacts that are needed to perform a knot? And how the number of contacts influences the action?
Mm-hmm. So I'm not 100% sure I know exactly what is meant by contact. I'm just going to assume here that this person means the number of intersections. Is that I'm just going to answer it like this. I guess you cannot ask for a clarification. So the number of intersections that we try to achieve with this method is basically that coming from the goal knot, right? So you have a topological, you're given a goal knot, and that one has a topological concept, and so it has basically defined how many intersections there will need to be. And in principle, there is no limitation in our method that would say, oh, we can only do so many knots. What happens is basically that your tree search is going to be deeper, right? And but that will become more expensive the more intersections you have to form, so the more topological steps you have to make. The motion primitives themselves, they actually generalize to these different knots, as we have shown, right? Like we went from we basically went from a simpler knot to a more complex knot using the same motion primitives.
Okay, thanks. I guess that answered the question because we didn't get any clarification, so I think it's fine. And so I was just wondering, I have just one quick question. So it's mostly about the state representation. So in your work, you have an explicit state representation. So you're basically taking these key points on the rope. But I was wondering if you considered that this approach can be used also with different kind of objects. So for the rope, it's quite easy to imagine how to get this explicit state representation. But can this be applicable also with other kind of objects?
Yeah, that's a very good question. Maybe I can stop sharing also, but it's a very good question, and I'm thinking specifically just going to 2D pieces of cloth, right? And they're already, that kind of representation doesn't scale super well. So we haven't yet started working on this, but we have thought about maybe two different ways on how to move towards a more complex object than a linear object. And one would be to maybe just represent the contours of the 2D cloth, for example, instead of maybe the entire mesh. And the other one is to think about different resolutions of the mesh of a 2D cloth, right? Like, what do you really need in order to do folding, for example? Probably not as high resolution as necessary. But yeah, we haven't really further thought about this, or we don't have results yet, basically.
Okay, thanks. And I think we can discuss more in detail these aspects during the discussion round. So now we can move to the discussion round. And thanks a lot for the talk. It was really nice. So now it's time for the open discussion round, and we have here Dimitri Berenson from the University of Michigan, Wenzhen Yuan from the Carnegie Mellon University, Dinesh Manocha from the University of Maryland, Janet Bog from Stanford University, and we also have Rika Antonova, that is an organizer of the workshop from Stanford University. And Rika will be mostly in charge of moderating this open discussion round, but I want to remind the audience to ask as many questions as possible, and we monitored both the question and answer here on Zoom and also the Slido channel. So please, Rika, you can take the floor.
All right. Thanks all for the talks. It was very interesting to listen, and I'm glad the audience was engaged asking questions too. So for the discussion round, we'll start with 2 questions that were suggested by the organizers, 2 topics, I guess, and then we'll also perhaps have a 3rd topic that we could pick out from the audience. So the audience, please feel free to suggest the topic to consider in the Slido Q&A. So the first one was simulation and transfer to reality. Can we leverage simulators for real world applications? So to start off, there are a number of simulators right now, right, that can model to various degrees of fidelity and stability and success deformable objects like ByBullet, Mujoko, all have added support for that. They are available. SOFA, which is a more, I guess, simulator that is more focused on perhaps medical robotics, NVIDIA Flex, and the newly introduced SoftGym have kind of basic environments for dealing with ropes and a bit with cloth. Unity has also a few plugins like ObiCloth. Perhaps there are others. So now in all of these things, there are, of course, severe limitations. And so I'm wondering if one of the things that we could start off is maybe a few people who have used simulation for their work. What is the top limitation that you would single out to say that, okay, this really impedes my ability to use a certain simulator, or this just impedes my ability to say that these simulators have a promise to be useful for real world applicability? Whoever wants to start first, whoever has been annoyed with a simulation of deformable objects the most.
This is Dinesh Manoja. Can I go first?
Yes.
Okay, great. So this is a very big question. I tell you, so I have dealt with simulators in 2 different domains for the last 30 years. If you go to the engineering community or robotics, we want what we call physically very accurate simulators, FEM and high friction and quite a bit of that. But if you go to like the gaming and graphics, and you mentioned Unity and VR application, in that community, people have developed what they call plausible. They visually look okay, but many times they're not physically accurate. Now, in our community, like in my own case, we use GraphSpit because that was available, and it seems to work well. But the bigger question that in my mind, we don't have a good answer to it. We're doing sim to real, and we're doing all this synthetic data set or other kinds of learning methods. What's the level of fidelity we have? Can we, many times we use game like Unity simulators, or sometimes we use very expensive, very accurate simulators. There's a trade-off between the accuracy and running time. I don't think we have a generic answer. Can we get a Unity type approximate simulators are very accurate. And if you look at the learning papers, you're seeing people reporting results with both of them. But what is the level of simulation fidelity we need for learning is an open question. And it's also possible, maybe in one case of what network I use, this particular fidelity is okay. But so some other application like locomotion or some other robotic application, different fidelity is okay. So I think there's still a big open question for the community. That's my take on it.
Yeah, I'd like to follow up on that. So I agree with Dinesh that this question of accuracy and how the simulator is used is crucial. And the way I see it, there are kind of 2 ways of using simulation for the kind of work we do. One way is to run it in these massive kind of cloud computers or whatever, just generate tons and tons of simulations to learn some kind of general policy over, let's say, rope or cloth or something like that. And another way to use simulation that's prevalent is to assume the simulator is basically a stand-in for the real world object, so that when I'm running my control or planning online for some given object, then I can just call my simulator to tell me how that object will move. And to me, these are 2 actually very different applications and make very different assumptions about the qualities of the simulator. In the massively kind of parallel, get a huge data set world, I would argue we don't need especially accurate simulators unless we're doing something very, very minute, and we have to be very careful about how we manipulate. We would just need kind of fairly accurate simulators that are very numerically stable. That's a huge issue. And also, we can tune the parameters to generate a bunch of different behaviors over different kinds of stiffnesses and so on with the object.
Whereas online, I feel like we do not actually have simulation technology that can autonomously do system identification and accurate simulation for a real world deformable object. So for instance, simulating a cloth, many packages exist, but simulating this particular cloth that I'm wearing right now, I don't know anything that can look at this and do SysID and then have an accurate simulation.
So perhaps to go into this, how to do this particular object simulation, do you think there would be possibilities for doing something like real to sim? So if you have a simulator which is somewhat flexible, right? I think the differentiable simulation maybe comes in as a topic, but it doesn't have to be differentiable. It could be black box and we estimate its parameters with other methods. Would it be possible to perhaps develop a bit further the methods that would take a few hardware like observations of like the actual cloth or maybe like your robot trying to wiggle this cloth or stretch this cloth on hardware, and then put it into the simulator, turn a bit of the optimization, and then do something good with this? Do you think that's a possibility? How would we explore that?
So my response is, well, is it a possibility? Of course, yes, definitely. But there are reasons that's really, really hard to do. So when you go sim to real, you go from huge amounts of data to less amounts of data, right? So you're already pre-training on tons and tons of data. Now you can apply, maybe fine tune on a smaller amount. When you go real to sim, real means less data in robotics, unless you're Google and you have an ARM farm. It means you've got much less data, right? So you're trying to identify these parameters or whatever they may be of the deformable object from a small amount of data. And you can probably do that, but what I'm worried about is that the model that you fit to this data will only be valid given what you've shown it, and what you've shown it is very little. So unlike in simulation, where you can test over so many different conditions and get tons of data, you're not going to have that data in the real world. So your model has the danger of overfitting, and then as soon as you try to do something different, suddenly the model breaks down.
So let me add, Dimitri, I think you made a good point. This is a great talk, but sim to real and real to sim. So I feel the term sim to real has become more popular in the last 6-7 years. There's a huge activity on data sets because of machine learning. But I would say real to sim has been in the published community, again, with my graphics hat, I would say, people have been doing for 15 years because what we call data-driven simulation. There's a lot of like fluid effects, you want to simulate complex bubbles or some big waves. Folks had no good synthetic models even, and they would take a lot of captured data and generate synthetic animations from that. So, but they remember the end goal for the real to sim, that community was to generate some visually plausible result for the gaming or VR experience. So I think at the end of the day, it really boils down to what your goal is. So there may not be one generic answer, but I would say real to sim, what we used to call in graphic data-driven simulation, is a pretty popular topic, and it's widely used in all the commercial products, actually.
Right, so very interesting points. And maybe, I don't know, when Jen, you unmuted, maybe you can also comment as you go on how we have, and whether we do have a potential for having sensor information being simulated. That is currently kind of not present at all for deformables in simulators.
Sure. So I would like to say something from this different perspective. I'm not a big user of simulation, but I'm trying to be a contributor to a simulation. So one thing my group is focusing on now is to build a simulation model for the gel size sensor we are using now. And we are publishing our first paper on this conference. So if you are interested, welcome to our presentation on the force and tactile sensing session. So of course, like this is only the first step of our simulation work. So we also have some recent work, and we are continuously developing our simulator, but like the simulation model for the sensor. So, but our goal is to develop a model that you can use in your simulation environment, either Majoko or PyTorch or the PyBullet or some other environment that we hope you can use the simulated gel size sensors in your in that environment when your robot is interacting with different kind of deformable objects. Of course, in the near future, we also hope to generalize our model to other tactile sensors as well. So hopefully people will get a chance to play with different sensors to see that what happens if you use this sensor for your task, what happens if you use the other sensor for your task, or even what happens if you create a new tactile sensor which doesn't really exist. So whether that will help with your task. So I think it's very interesting to hear the discussion from Dinesh and Dimitri that, like you said, that it's a big challenge if since this is very hard to match the models with the real model of the deformable objects. But my understanding is that like we can add lots of varieties on the objects used in simulation environment. But as far as we have good perception, we can quickly build a model based on the perception and the manipulation interactions. So probably we can come up with a good manipulation strategies on those objects. So here I'm trying to contribute and make a simulation model for tactile sensing that you can all play in simulators.
Can I ask a follow-up question, Wenjin? So what are your thoughts on how close is it to the real sensor? Like, or if you're saying you are maybe simulating different kinds of haptic sensors, which one are hard and which ones are maybe easy to simulate, and which one has the smallest gap between sim to real? What is your thoughts there?
That's a good question. So currently our focus is with gel size sensors. So that is relatively a complicated tactile sensors in many sense, since like it has a soft surface. So the deformation or interaction between soft objects is very hard to simulate. So we're working on that, and frankly speaking, our current effort is kind of limited to the rigid object contact. So like if you're contacting some soft objects, such as like I showed in my presentation, like the example of pressing on a avocado and trying to estimate the hardness of the avocados. So I haven't really think a lot about that yet, since we don't have a good model of the soft objects overall. But for some like some objects is more similar to a rigid objects. For example, like one thing we have been trying to working on recently is cable manipulation. Like what happens if we ask a robot to grab some cable to insert or to do a routing or go through a hole. So the contact area is generally like a cylinder area, like the contact between the cable and the grippers. So for that part, as far as our big simulation environment has a good understanding about what's the geometry it is. So we can deal with the geometry pretty well, and the signal we get nowadays is already pretty close to the real sensors, real signals we get from the gel size sensors. But also we do have lots of challenge, like there have been lots of discussion in the sensor community that whether we can design more complicated sensors, sensors with more complicated structures, but hopefully could be smaller, can fit on a curved surface or smaller surface. So in those cases, actually there are more noise introduced in the sensor itself, and how to model the noise of those sensors could be a challenge. So on the other hand, so there are lots of more commonly used, I would say more traditional tactile sensors, which aim at detecting the normal force distribution with like a spatial resolution of several millimeters. So I expect most of them are relatively easier to simulate for building the model. But yeah, we look forward to see how it works out.
So it could be also the problematic piece is that they are easier to simulate, but maybe they're less relevant for the highly deformable objects or central objects like cloth, right? So it's if you are estimating something that is deformable, like you were saying, avocado or sponge or something like this, where you still can feel forces, then that's good. And once you go into like, you really need to get into a certain configuration to feel forces, like you're holding on to two pieces of an object and stretching it to the limit, then maybe like that's the only way that you can sense something, where it's just pressing on the cloth is not giving you anything. So I was wondering, maybe there's some, I don't know, alternative sensors in the sensor community that we don't yet know about that could be applicable and relatively easy to simulate. If you have comments on that, something that, I don't know, something that maybe we haven't, that hasn't been useful, let's say, for rigid objects, but could be an interesting thing for deformable objects, and is also like easy to model, if that something like this comes to mind.
I know that there's lots of simulation models for vision, so you can add a simulated camera, especially I know robotics people are very interested in the RGBD information for simulating point cloud. So I think that is a very important tool. So especially if like we are considering clothes or cables, where the global information, global shape of the objects is very important. I think that could be very important, helpful. And also it represents majority categories of the perception tools used for deformable objects manipulation nowadays. So I think that is a good place to go. So other than that, I know that recently there are also like some people thinking about like seeing through tactile sensor, like the one developed also at CMU by Professor Chris Atkinson's group, called finger vision. So the idea is that they want to combine touch with vision exactly on the fingertips. So their sensors can actually see through the finger, can see what is happened in front of the finger, and also can detect some of the contact information. So to many extents, like this is very similar to the concept of proximity sensing. It's a kind of sensor like can feel the objects before contact, but feel the object is very close to the sensor. So traditionally, people are trying to use like infrared sensing or like radars to detect objects close to the sensor, but also nowadays people propose to use vision. So I think the good thing is that like with this kind of sensor for doing manipulation, you can get a finer information about the objects closer to the sensor, to the grippers, so that this is also possible to simulate like in a way similar to the like point cloud modeling.
Okay, yeah, that does sound quite promising. I was wondering, for perhaps people who are interested in the vision aspect of it, how far along do you think is the possibility of simulating RGBD data kind of for deformables? Because we're seeing sort of in the sim-to-real sort of world, like a big rise of the, okay, now we have scalable, even kind of like visually realistic worlds, right? And that is becoming a reality now, but can we have depth data? Can we have like noise models that are reasonable for it? And what do you think about deformables? Like, what is the potential there?
So let me explain. This is a very good question, RGB sensor. So I think one community that are looking a lot into this is now is autonomous driving. The autonomous driving people, I saw some announcements, some work at Argo had done with, Deva Ramana's group. They're doing long range sensors. So I've seen a lot more work because there's a huge commercial impetus, there's a huge business model to support that sensor development, that they use mostly LiDARs and probably cameras, and also they use RGBD cameras. But in that community, I've seen a lot of good developments in those kind of simulators.
Yeah, we've had some experience simulating RGBD data for the purpose of sim-to-real. And the hardest thing to simulate are the real sensor noise weirdnesses of the Kinect, right? Everybody probably knows about the trails you get on the edges of objects and how specular properties of objects can disrupt the Kinect. That's hard to simulate, but there are some tools available for that. People have been working on that. I don't know the reference off of the top of my head, but I think we did end up using some published work that tried to model that kind of stuff for the Kinect, at least the sensor trails part. And that really did help. It was important. What's that?
Maybe you used my code.
Yeah, it could be Jeanette's code. I don't remember.
The one I re-implemented was Blender. It was like a Blender plugin, and that one had a pretty good, not the specularities, but just generally all the quirks from the Kinect sensor were kind of implemented there, and I just re-implemented it in C++. So I don't know. Maybe use that.
Oh,
it's no support anymore, though.
Right.
But I would, yeah, sorry to interrupt. I would say actually, depth sensor is depth data. I don't know if you agree, Dimitri and others, is not such a big deal. I would say depth data, even if you're not capturing like all the quirks, it transfers much better to real world than RGB. RGB is much harder to do for the realistic and really well, yeah. I would say.
Yeah, I guess the way we were looking at it was, in our work, we basically treat things that are out of distribution with respect to the perception we've learned as the object is different, right? So if that out of distributionness is disrupted by the sensor quirks, then our kind of object is different detector, is going to turn on erroneously. So for us, we kind of treated RGBD just as, 4 channels, and we didn't really try to figure out which one was more or less reliable. But I would agree in general that depth data is a little bit more forgiving than RGB.
All right. Well, that sounds hopeful. Since also that maybe Jeanette, you had another comment.
Yeah, I have like just one follow-up question on your question. Actually, I would say this is the depth data that it's more forgiving. Is true for rigid or deformable object. Or Rika, were you thinking of something specific that makes it harder to simulate visual
maybe
deformable objects? Because I was thinking,
yes.
Like, is there a difference? I would say no,
yes.
but I'm not sure.
Right. There might not be a difference with everything, but I was thinking of some specific case. So for example, grasping rigid objects with a regular parallel gripper, right? The biggest problem we found is when we wanted to grasp everyday objects, if they're very thin, their perception gets into the noise of Kinect, right? And then we moved on to trying to deal with cloth, which if you spread it out, it is very thin, right? And at the point where that gets, all of your object basically gets into your sensor noise. Now that's a problem. So that's one case that I was thinking. So like, for example, for a piece of foam that keeps its shape, right? That's not a problem if sort of the issues that arise are the same, right? But if the objects you're dealing with are very thin and get into the sensor noise a lot more often, then filtering out that noise would be a nightmare. So that's what I was thinking about here.
I see. You're thinking of these thin structures, like just wrinkles and stuff like this and folds and everything. Yeah. That makes sense. Yeah, that's true.
So that could be, yeah. All right, cool. So let's see. Now we can move on to actually segue into what is robust enough to deal with various problems, right? We had this second sort of topic direction on methods for evaluation. How can we compare different methods that are proposed? And having watched the IROS, I think it was last year, and I think a few of the panelists here were participating there, there was this topic that arose about the benchmarks. And I think the consensus was kind of that it is hard to design a benchmark which would capture the richness, like a benchmark task that would capture all the richness that we want out of experimenting with deformable objects. We haven't yet defined like concretely what are like all the spectrum of problems. So some of the suggestions were something like maybe we could share a common set of objects. I think Dimitri was suggesting that, and kind of like have models of them and kind of like pay attention to them, but not define concrete tasks. And I think Wenxian was pointing out that maybe we also kind of define more precisely what we mean by different types of deformability. And then Jeanette was saying it would be good to have common access maybe to a hardware platform that was similar so that people can experiment on the similar hardware, but they could also still define their own tasks. So that was sort of the quick summary of the benchmarks or not to benchmark or not to benchmark. But I was thinking in terms of evaluation, can we step back a little bit and think about, well, why do we need the evaluation like in the first place? What is it that we're not actually like want to check mark on, did I beat everybody on this benchmark or not? What we want to find out is what are the methods that are useful and for what kinds of tasks, right? So in that vein, right, how can we evaluate, or even how can we like make sure that we can share the current methods that, let's say we present at the conferences, right? And communicate that they are ready to be used by other labs. Now, the difficulty with that is that we don't really have a concrete kind of taxonomy of what methods are applicable to what concrete situations for deformable objects. So basically, how do we handle that? So the pose this question for discussion is, how do we do evaluation in a sense that it's informative? So like, which method would be applicable outside of the, author's labs circle and on other hardware as a component in another system for another set of tasks? How do we communicate this? How do we evaluate this? How do we structure this?
Well, in some sense, what you're kind of driving at is the heart of the scientific replicability crisis, right? This is not just in robotics. This is in, I think started in psychology, but now in physics, results are not replicating, and it's a little bit of a crisis in the standards that we use to say something as a scientific contribution. And I think in robotics, it's much the same, right? I mean, you can define benchmarks and you can, create simulation benchmarks. I think there's a lot of value in that, but is it going to work on a slightly different simulation? We never know until we try. And that's kind of annoying in robotics, that we always have this issue that we don't know if it works until we actually try it. But on the other hand, we work in such a complex field where so many different factors are involved that, being able to actually generalize across any one of those factors is hard enough, but multiple factors simultaneously, like different robot, different material of the object, different stiffness of the object, it's a lot of axes to generalize over all at once. So maybe, I guess what my summary of my response is, we gotta set our standards lower. Okay, everybody wants to, just publish a paper now. Oh, all cloth folding is solved. All rope manipulation is solved. Guys, it's not going to happen with one method. I'm sorry, it's not. So, like, we just have to be a little bit more modest in what we're trying to do, and understand that we're not going to have like a thing that says this is guaranteed to work for my application. You're going to need to try it. It's better to try things that do well on benchmarks and have good theoretical properties than to try things that won't. Yes, but you're still going to need to try a few things, and you're probably going to need to develop on them.
Okay, I think that's useful suggestion, in a sense, also making more concrete and more explicit, like what sort of settings has this been already tried on, so that another lab could gauge themselves whether their setting is close enough. So that could be useful.
I guess one thing to list or to categorize work on is always just to look at the abstractions and representations that are used, right? So, for example, I'm just going to pick one example from my own work, which is what I just showed, right? And there we use, we parameterize the actions to be end effector positions. So and now whatever arm you have at your lab, right, doesn't matter, because the only thing you want to do is to servo that trajectory of the end effector. Who cares about your kinematics? That's one thing. The other one is Dimitri is gonna respond to that. I saw it. The other thing is the sensors, right? Like, what's the input? Some papers just don't have these very clear input-output descriptions, right? And a list of abstractions. I think if you wanted to do something like that, like actually say, here's something you can use, and here's why, then the input, output, and representation would be useful. But yeah, Dimitri, what's your response to that?
Well, so I like abstractions too, and they're very important. Like you can't do anything without them. To just, well, I mean, I guess you can do pixels to torque stuff, but that has its limits. So you're referring to the kinematics, and the reason I just jumped up on that is because we ran into exactly this problem. So initially, when we were doing some of the work I presented, we were just planning for the end effector positions of the robot, and it was holding a rope. And you can kind of do this and moves the rope around, and you're like, okay, cool. Now let's put it on the robot,
and we'll just use IK to track those end effector positions. I mean,
well, I didn't say you should use IK to track the end effector positions.
Well, so, okay, fair enough. But the problem was that what we found out when we put this on the real robot was that the end effector position actually did affect the thing we were doing, because sometimes the geometry of the gripper would kind of catch on the rope, or the rope could snag on it in certain orientations. Definitely the reachability of the robot has a huge impact on where you can and can't go. You know, we weren't working with heavy objects, but also the heavier the object is, that also constrains where in end effector space you can go, because the robot arm, the more outstretched it is, the more you know, torque is required. So again, I'm not trying to say we shouldn't use end effector positions. We still do that, but we just add more sauce to like.
Yeah, I mean, this was just an example, right? Like, let's say an end effector position that is the output of your method is easier than joint angles or joint torques, right? To transfer to other. It's not the, you know, the end of this question, but I would say it's better. The abstraction matters. That's all I wanted to say, and it was just an example. But if you wanted to facilitate this transfer to other labs, then just stating these things clearly would be good, I guess, which is what papers are supposed to do, right?
Yeah.
Right. Yeah, so that's a good point. Basically, maybe also explicitly kind of striving to make it a little bit more generic than it just needs to be for a paper, so that another lab that works with a different robot and has a different representation, but the high level representation can match, they can also benefit from it. All right, and I guess to close that, like, would it be useful to maintain some sort of categorization or like a summary of what are the different methods that are current, or you know, like from the older times, where is the code and all that? Or do you feel that the field is still kind of like, there are too many things going on, and at this point it wouldn't be useful to even have a web page with all the links kind of to summarize this, or to try to categorize this? Not formally categorize this, but just say like, oh, I work with cloth. What are the things going on there? I want vision for cloth. I just wanted an off-the-shelf vision for cloth. Well, off the shelf in quotes, right? Because I work on something else. I work on whatever control or something like this. Do you think this would be useful? Can we set up something like this? Or do you think we should just like step back and wait a few more years?
I think this would be super useful. I'm just not sure how practically it's going to be handled, right? There has to be someone who's really motivated to keep this up to date and to test all these things somehow, right? And then there has to be this benchmark.
I wasn't thinking like testing. I was thinking just like listing, right? So like pointing at the paper results, or the, you know, the talk summary or something like this. Not really like we have tested it in our lab sort of thing. That would be a huge amount of effort.
Yeah. Okay, fine. Let's not use that. But yeah, I'm just wondering like who would do that, right? Like it's like someone, it must be a deformable object influencer or something like that, who lots of people follow. Yeah, I just don't know how, you know, how practically.
Right, this would be implemented. Okay, so I get the to-do is to find a deformable object influencer, and then after that point we could propose this.
Yeah, I think what we're discussing about, it's all about incentives, right? Like it's all about setting up the right incentive structure. So for example, if there was some external incentive that gives you as a researcher in some way benefits for optimizing for your algorithm porting to other labs, like as it is, then, you know, then it would happen. But I feel like the incentive structure is not set up. The same with your suggestion, right? Like, what's the incentive of this influencer, right? Like to put in this work of keeping track of it, right? Fame, I don't know. Maybe there would be some companies who are sending samples of deformable objects. I don't know, you know. So I think it's all about incentives.
Yeah, that
they are
makes
not
sense.
set up for this stuff.
Right. So we'll see. Maybe somebody with the right incentives arises. All right, so then to kind of close off, so we were saying we'll monitor Q&A from the audience to see if we have a third topic. We ran a little bit kind of over time from the previous scheduling, so we'll have kind of a short maybe summary. And I think one question that I see here in Q&A, which is kind of like more global, is saying, what are the main challenges and bottlenecks for achieving good performance in manipulation of deformable objects. So maybe just like very briefly, currently in what you have seen so far, what do you feel is either a bottleneck or like a great opportunity that maybe, you know, people will start looking into more in the upcoming, I don't know, few years, just from your experience or from your perspective? Maybe each of the people on the panel could just have a brief note about that.
Maybe I can start. I mean, kind of everything is a bottleneck, right? But I would say choosing the right abstractions, like that question that Martina asked me, which I think, yeah, I think it was from Martina, right? Like, okay, how do you represent all these different pieces of cloth and all of this in order to make it perceivable and then plannable and generalize and all of this? I think that's a big question. I think there's a lot of work to be done there. And then what I'm always interested in is this whole field of soft robotics. So if you have a robot that actually has a soft material or is made of soft material, how do you control and how does it do proprioception? Do you even need it, or to what extent do you need it? These are all very interesting questions and a little bit different from manipulating deformable objects with a robot, right? It's more about how do you control this robot itself. And the other thing I had something else. Oh, and the other thing I'm always seeing is like this, actually trying to real applications. Like I've seen a lot of work on assistive dressing and things like that, which is so hard. I mean, you have a deformable object, a human, and you have to dress it with something deformable. That's so hard. Yeah, I don't know. I find this at least a very challenging problem, but yeah.
I think we're all pondering now how to do it with a soft robot. All right, so then maybe, I don't know, yeah, Dimitri, maybe you have some.
Yeah, well, I just want to say, I don't know if participants can see the chat window, but I just posted a link to a survey that just came out about, you know, what's going on in deformable objects. I just wanted to comment that it's interesting to, of course, keep a website and so on, but there has to be some effort to manage the flood of information, right? So these kinds of survey papers kind of package it up into like these kinds of people are doing this and that. That would have to be a continual effort, which is not easy. So I just wanted to mention that. In terms of bottlenecks, yeah, I agree with Jeanette. Everything is bad. I mean, not bad, but a bottleneck, right? We need better robots. We need better algorithms of perception. We need better control. We need better planning. We need better sensors. Everything is bad, right? But if I had to say, okay, well, what's really holding us back? I would have to say, I mean, obviously, you know best what you're working on, but it's the ability to generalize from small amounts of data with some kind of existing priors. We are not good at that, right? We really lack the algorithms to do that right now. And for the kinds of applications I look at, which are not so much in the factory domain, but more, somebody's home or whatever, we can't get lots of data for like some object that we just pick up. And so we have to use some kind of prior information and then a little bit of data to do things. And that's really hard. So I see that as a main bottleneck right now.
I think everything you said is great. I would probably say, given the graphics community actually spent a lot more on deformable simulation. And as I think Dimitri already mentioned, cloth is something which is finally getting to be there. I myself work a lot of cloth. There's also a lot of work on things like smoke and fluids. So they're deformable objects, and then they're really deformable, highly deformable objects. There's probably much more work in the graphics community, especially data-driven simulation methods and a lot of validation. So I think the robotics community probably can benefit. Now, of course, the goals are different. Graphics get away with a little bit of visual simulation, but there's a lot more things they have done on data-driven simulation method, which I think robotics community can really benefit from there. Because if you can simulate highly deformable cloud, turbulent fluids, and very, very challenging situation, on the robotics, we can't even like you can't do a good job folding a simple piece of cloth, and they're dealing with very high different cloth. So this kind of cross-pollination can really help us a lot, especially as we combine data, learning, and simulation all together.
Great, thanks for this positive kind of compliment to everything is a bottleneck sort of thing. All right, and Wenjing?
I think what everyone said is very good. So I really understand we also have a big problem about how to generalize from a small data set. So this is actually connected to the other question, is how to find the good representations of the data. So on the side of perception, so I'm really blessed to have this good system. We have good sensors, we have lots of information. We found that so there's no theoretical problems on the perception side at this moment. So, but finally, we want to build a robot system. We want to build a system that the robots can manipulate, can interact with those deformable objects. So what I work on is only one side of it is on the perception side. So finally, we need to connect this perception side with the entire robot system. So the question is, what this connection could be like? So I show you an example, like for the objects made of deformable materials. Probably the most important things you want to get on the perception side is how soft this object is. So that is only a single number. But if we are considering some more complicated objects like clothing, fabrics, so it has so much varieties in the properties of them. There are so many different ways to describe them. So what is a good way we use to describe this kind of material? How can we use the information from perception as part of this manipulation framework? So what's this interface should be like? So this is a question. Actually, I don't have answers. So I try different ways. I try supervised learning ways, like based on human perceptions, ask a human's intuition about how would you describe a fabric, and ask a human to label the fabrics based on that. Also, my colleagues try some more hardcore way, like send the fabrics to a mechanical labs where they do lots of mechanical tests on the fabrics. It's very costly, and also actually we don't really know whether it's really help better than human perception. Also, in another work I haven't got a chance to show today, we did some unsupervised learning. So it's only based on the perception side. We connect vision and touch information. We try to learn some shared descriptors that can be get either from vision and from touch, where we hope can describe some invariant description of the fabrics. Although we don't really know what it is, but we found that there are some similarities of the material itself regarding to this representation description. But that is not connected to the manipulation side finally. So I think finally we hope the entire community can work together, can have more communication about what is the best representation, what kind of representation we really want to get from the perception side in order to make the entire system work well.
Yeah, that sounds like a very important point. If we wanted to have some modularity, right, and some labs or people would be experts in perception, exporting kind of their algorithm, if there's kind of a miscommunication on, well, what is the representation that this is able to handle, or the controller learning algorithms on the other side can't use it very effectively, right, then this is a bottleneck, I guess. All right, great. So thank you very much for contributing your thoughts to this. And I hope that, yes, the community of, that's interested in deformable objects and manipulation and representation of them and so on keeps growing within robotics. So hopefully we'll see more of workshops like this in the future and maybe even conferences.
Before we close, I just wanted to highlight there was one more slide question about adding deformable manipulation as a keyword. Similarly to getting a track dedicated to this. And this goes out to the more senior people if they are editors at some point, maybe push for that. This workshop was actually born of when we identified the need of finding papers about deformable manipulation and in all kinds of tracks. And in this workshop, we tried to kind of focus it a bit. So if you have the possibility to influence that a bit, I encourage you to use your power for the good of the deformable object community.
I want to thank all the organizers. This is a lot of effort on your part. So thank you. It was a learning experience for us.
Thank you very much.
Thank you for being here. So I think we can close our workshop, and it was really a pleasure to have all of you. So really many thanks. And I want also to thank all the spotlight presenters and all the people that were here. And of course, I also want to thank the organizers, and I hope you enjoyed this workshop. I think it was really great, and your talks were really great. And so that's it. Thanks, everyone, and I hope we'll have another workshop like this. So I don't know if the other guys want to add something. And of course, thanks, Rika, for moderating this discussion round.
I want to say thank you so much for organizing this and keeping this going. You know, the frequency of workshops on deformable object manipulation has increased a lot, and I think it's really driving a lot of research and interest in this community.
Let's hope it keeps catching on. Yeah, I think in that sense we can close the workshop. Thanks again to everyone, and yeah, have a good day.
Yep.
And I'm gonna end the session, and then we're gonna end the stream, and yeah, and hopefully see you guys around the conferences at some point in person again. In this spirit, take care and goodbye.
Bye. Thanks.
Bye.